Hi everyone, welcome to Neetshala Organic Chemistry Revision Lecture Series. In this series, we will be covering all the chapters of organic chemistry for NEET examination. So let's get started. Before we begin, do not forget to like, comment your queries, suggestions, and doubts below. Share it with your friends and also subscribe to Neetshala YouTube channel, and also you could be a part of the Telegram channel for all the updates related to the upcoming videos. So let's start. Today we will be having the part 1 of the organic revision lecture series, wherein we will be covering about alkenes. Now what are alkenes? Alkenes are a class of saturated hydrocarbons. They are a class of saturated hydrocarbons which is having a general formula of CnH2n plus 2. This is the general formula for alkanes, where N is going to be the number of carbon. So let's move on. In this chapter, we will be mainly discussing the structure of methane. Then we will be discussing about the IUPAC nomenclature, isomerism, preparation of alkanes, and the properties of alkanes. So let's discuss about the structure of methane first. Now, if I'm checking the structure of methane, I can understand that it is tetrahedral in structure and it is having a hybridization of sp3. So if it is sp3, we can say that the bond angle between carbon and hydrogen is coming out to be 109.5 degree. Now what is the value of carbon-carbon bond length? If I take higher alkanes, we have carbon-carbon bond length, and that carbon-carbon bond length is coming out to be 154 picometer, and carbon-hydrogen bond length is coming out to be 112 picometer. So that's all about the structure of methane. Now let's move on to the IUPAC nomenclature. So here I have taken the example of C6H14. We are going to construct the isomers of C6H14 and we will name those compounds according to the rules of IUPAC nomenclature. So let's get started. Let's make the isomers one by one. Before that, what are isomers? Isomers are basically the compounds which have the same molecular formula but have the different structures. So if I take C6H14, we can arrange it like this. This is the first possibility. We can arrange 6 carbons in a straight chain. Then it is known as normal hexane. Second, we can arrange 5 carbons in a row and we can keep 1 carbon as a substituent. Now that substituent cannot be placed at the first position, because if I place it like this, now this is going to be my longest chain. So that is same as the first one. So we will neglect this chain because we don't want repetitions in isomerism. So we are going to remove it from here and let's add it to the second position. So this is going to be the second compound, that is known as 2-methyl pentane. Now what is the third possibility? Third possibility is we can place it at the third position. Now what are we getting? Now we are getting 3-methyl and the parent hydrocarbon is pentane, so we can name it as 3-methyl pentane. Now we are going to remove one more carbon from the main chain and we are going to add 2 substituents. Again, we cannot add it at this and this position. This is not possible. So we can eliminate that option and we can place it over here and here. So this is another possibility. So we have a methyl group at the second position and also at the third position. So we can say it is 2,3 dimethyl and the parent chain over here is butane. So it is 2,3 dimethyl butane. Now what about the fifth one? Fifth one is where I am going to place both substituents on a single carbon. So that I can place it either here or I can place it on this carbon. Both are the same. So we will get 2,2-dimethyl butane as the next isomer. So these are the different isomers of C6H14. Let us now study the preparation of alkanes. Now we can prepare alkanes from a variety of compounds like alkenes, alkynes, haloalkanes, alcohols, aldehydes, ketones, carboxylic acids, and amines. Now, in this chapter, we will not be discussing about amines because from amines we will be preparing from Grignard's reagent, and Grignard's reagent we will be dealing separately in the chapter haloalkenes and haloarenes. So, let us start with alkenes. Now, if we have to prepare it from unsaturated hydrocarbon, that is alkene or alkyne, then we have to use addition of hydrogen. And addition of hydrogen, as you know, the process is called as hydrogenation. For hydrogenation, we can use a variety of catalysts like platinum, palladium, or nickel. Now, platinum and palladium is usually taken at the room temperature, but nickel is taken at relatively higher temperature and pressure. And if we are using nickel for the process of hydrogenation, then it is known as Sebastian-Sanderson's reaction. Sebastian-Sanderson's reaction. Now, the most important point to note is that platinum, palladium, and nickel should be finely divided. Finely divided so that it has very large surface area for carrying out the reaction. Now, let us see how the reaction is carried out. As you can see over here, we have ethene here, CH2 double bond CH2. We are going to add hydrogen on both sides of the double bond, that is over here and also over here. Now, how is the mechanism? First of all, we have CH2 double bond CH2. This is going to undergo homolytic fission so that both the carbon will get one hydrogen each. So we have CH2 single bond CH2. This carbon is also having a dot, that is, it has one electron, and this also has another electron. Now let us take hydrogen, H2. H2 will also undergo homolytic cleavage and it will form two hydrogen free radical. So one hydrogen free radical will come over here and another hydrogen free radical will come over here. So let us join these two with a single bond, and now what we're getting, this is known as ethane. So we got ethane here, and this is the method of hydrogenation. So what was the mechanism that was followed? The mechanism that was followed is nothing but free radical addition reaction. So let us take propene. We just have to remove the double bond, and to the either sides we have to add hydrogen, so we will get propane. Now what if we are given an alkyne such as propine? So in that particular case we have to do the process of hydrogenation twice. When we are doing the process of hydrogenation one time, we will be getting alkene, and when we are doing it again, we will be getting it as propane. So now let us see a question based on this. So as you can see over here, look at this question. So how to add the CH3? This is a classical example for AIMS level of questions. We have to remember that if we are considering stereochemistry, we have to understand that addition of hydrogen is syn addition. Syn addition का मतलब है कि hydrogen is added to the same side, either towards the observer or away from the observer. Here we can see that the hydrogen is added in such a way that it is facing the observer, and here it is added in such a way that it is moving away from the observer. So these are the two different possibilities in which we can add hydrogen, and we will be getting two different compounds in the ratio 1:1. So that is why it is a free radical addition and also a syn addition if we are considering the stereochemistry. So let us take another example here. So what to do? We have to break this bond and we have to add hydrogen. Now that hydrogen can either be facing towards the observer, or another possibility is it can move away from the observer. Now let us take the second class of compounds, that is alkyl halides. How can we prepare alkanes from alkyl halides? We have two methods. Method number one is reduction. For reduction we will use zinc and dilute hydrochloric acid. So if I am taking CH3Cl plus H2 in the presence of zinc in acidic medium, that is in the presence of dilute HCl, what is going to happen? This hydrogen is going to split to give hydrogen free radical, and one of the free radical is going to react with a chlorine free radical that is generated from this molecule to form HCl, and it is going to the other hydrogen free radical is going to react with the CH3 to form CH4. So we get CH4 and also we get HCl as the product. Now, there is a limitation for this reaction as well. What is that limitation? The following reaction cannot be used for fluorides because of its very high bond dissociation enthalpy. So let's move on to the next compound, next reaction. How can we prepare it from Wood's reaction? Now, what is Wood's reaction? Wood's reaction, what we are going to do is we are going to take two molecules of either the same alkane, so alkyl halide, or we can take two different alkyl halides. So case 1, let us take the same alkyl halides. So let us take CH3Br plus. We need to take a metal, that is sodium. So we will take two molecules of sodium and we will take another molecule of the alkyl halide, that is CH3Br. So we can remove this NaBr like this, and we can join this CH3 and CH3. So that is the mechanism. So if we have one carbon over here in the reagents, or we can say in the reactants, if we have one carbon, we will get one alkane which is having double the number of carbon, that is we will have two carbon. Now if we have two carbon in the reagent, then we will have four in the product. Now if I am taking two different alkanes, alkyl halides, like CH3Br plus 2Na, and this sodium should always be placed in dry ethereal medium. Now why not wet ethereal medium? Because if we are placing it in wet ethereal medium, then it can lead to explosion, because sodium is very rapidly reacting with water to form heat. So let us take two different alkyl halides now, CH3Br plus 2Na plus let us take CH3CH2Br. So let us remove the NaBr first of all. Let us remove the NaBr. Now here we are going to get three major products. How three major products? We have one compound having one carbon. So in the product we should double the number of carbon. So we will get CH3CH3. Second, we are going to take this compound and we are going to double the number of carbons. So we will get 4 carbon containing butane, CH3CH2, CH2CH3. And these are the expected products. We have another product that is formed by combining this CH3Br and this CH3CH2Br. We can see that this compound has only one carbon and this compound has only two carbon. So we have to add this 1 and 2. We get 3 carbon containing propane also. So what are the three main products that we get over here? Let us take the general reaction now. Rx plus R dash X plus 2 molecules of sodium in dry ether. In dry ether, it is going to give us RR plus R dash plus RR dash. Now what is the mechanism followed in Wood's reaction? In Wood's reaction, the mechanism followed is going to be again free radical mechanism. Free radical mechanism. Now in this mechanism also, in this process also, there are some unwanted products. Let us see what are those unwanted products. We have a possibility for generation of carbocation. So let us take an example. If I take CH3Br, it is going to form CH3 free radical and also Br free radical. Now if I take CH3 CH2Br, it is going to give us CH3 CH2 free radical. Right now there is another possibility, like we have CH2 and I can write a hydrogen over here, and there is a possibility for cleavage over here, right? So that cleavage will result in a free radical on the carbon, and here already we have a free radical. So this hydrogen is moving out as H plus, Now there is a possibility of forming a double bond between these two. So CH2 double bond CH2 can also be formed, but this is going to be a minor product, right? So alkenes is also formed in Wood's reaction, but as a minor product, and in organic chemistry usually we do not represent these minor products. So let us now look at the next reaction, but before that, let us see some of the related reaction. Like when we learn about Wood's reaction, we are also supposed to learn Fittig reaction and Wood's Fittig reaction. In Wood's reaction, we have taken alkyl halides, but in Fittig reaction, we will take aryl halides, and in Wood's Fittig reaction, we will be taking alkyl halide and also aryl halide. So two compounds we will be taking over there. So let's move on to the next one, that is conversion of alcohols to alkanes, aldehydes to alkanes, and also ketones to alkane. For all these three conversions, we can use red phosphorus in the presence of iodine, and this is going to act as the reducing agent. It is a weak reducing agent which can convert alcohols to alkanes, aldehydes to alkanes, and ketones to alkanes. But for these two, we generally use Clemenson's or Wolff-Kishner reduction rather than red phosphorus and iodine. So let us see Clemenson's reduction. In Clemenson's reduction, what is happening? We have an aldehyde or ketone. So the CO group is converted into CH2 group by using the reagent zinc amalgam in the presence of HCl. So we need acidic medium for carrying out Clemenson reduction, and in Wolff-Kishner reduction we are taking a ketone or an aldehyde. We are going to react it with hydrazine in KOH at high temperature. We will be getting alkane. So here also the same bond cleavage is going to happen. CO is going to convert to CH2. So as we can see, there is addition of hydrogen and removal of oxygen. So both of these are going to be reduction reactions. Now, here we can see that Clemenson reduction is active at acidic pH and Wolff-Kishner reduction is active at basic pH. So if we have any like acid sensitive groups like OH will react with H plus, right? So if we have any such acid sensitive groups, then we cannot use Clemenson reduction because it will misguide the reaction and we will get some other product which is not required. So let us see one question related to this. As you can see over here, we need to carry out the following conversion. What is the reagent that is required? So here we have OH. OH, as you know, is an acid sensitive group. Hence, it is going to react with the H plus and it will convert it into water. H plus plus OH minus will form water, right? So this is a mild oxidizing agent, so we cannot use this also, and hence we cannot use this also because it will form some other products, not the desired product. So we have to use only Wolff-Kishner reduction in the presence of acid sensitive group. Now let us see what will happen in this particular question. Here we can see that we have bromine. Here you can see bromine over here, and bromine is not a base sensitive group, but we have an adjacent hydrogen, right? This adjacent hydrogen is an alpha hydrogen, and alpha hydrogen is always an acidic hydrogen. So this acidic hydrogen can react with the OH minus if we are carrying out the Wolff-Kishner reduction, and it can form an alkene, and that is not the desired product, right? So we cannot carry out this particular reaction, that is Wolff-Kishner reduction, when there is compounds containing alpha hydrogen, because alpha hydrogen is an acidic hydrogen and that will misguide the reaction. So this is the limitations of these two reactions, that is Clemenson's reduction and Wolff-Kishner reduction. Now let us move on to the next topic, that is preparation from carboxylic acids. Now if we have to prepare it from carboxylic acids, we can use two methods again. One is known as decarboxylation and another is known as Kolbe's electrolysis. Now what is decarboxylation? For decarboxylation, we can react the acid with NaOH and CaO. The mixture of NaOH and CaO is known as soda lime. It is known as soda lime, and this is taken in the ratio 3:1. 3:1, where 3 parts of sodium hydroxide and 1 part of calcium oxide is taken. Now, when we are reacting, it is decarboxylation. Always remember, D means removal. So, decarboxylation means there is removal of one carbon dioxide, or we can say one carbon molecule, and that is moving out as Na2CO3 over here. Usually, we can take it as one carbon containing compound is moving out. It can be the carbon dioxide or any other compounds like these, Na2CO3. So as a result, if we have 4 carbon, or we can say n carbon in general, if we have n carbons in the reactant side, so n carbon in the reactant side, we will have n minus 1 carbon in the product side. And what will be the reagent? The reagent is going to be an acid, and the product is going to be an alkane. So the process is decarboxylation. Now this type of questions are expected from here. This is an NCERT example. Now what is this question? Sodium salt of which acid will be needed for the preparation of propane? So first of all, we will take an acid and we will react it with NaOH so that we get the sodium salt. Now this sodium salt is treated with the soda lime mixture, and as a result of that, it is eliminating a molecule of Na2CO3 and we will be getting the product. So let us see what is the product that what is the salt that is required over here. So here it is given that the product is propane. So product will have 3 carbon. So how many carbons will be present in the reagent? It will be n plus 1. So that is coming out to be 4. So we have 4 carbon in the reactant side. So since we have 4 carbon in the reactant side, it is going to be butanoic acid. Now let us see the second method, that is known as Kolbe's electrolysis. Now Kolbe's electrolysis is again a free radical mechanism. So let us see how the process is carried out. So here we are going to take an aqueous solution of the sodium or potassium salt of a carboxylic acid, and we are going to carry out its electrolysis. This electrolysis will give rise to an alkane which is containing even number of carbon atoms at the anode. So let us take the process in detail. Suppose I have CH3 COONA. This is a sodium salt of a carboxylic acid. This on dissociation will give us CH3 COO minus and Na plus. Now this is a cationic species and this is going to be an anionic species. Now if you could remember from the electrochemistry chapter that cationic species will move towards the cathode and will reduce, and the anionic species will move towards the anode and will oxidize. So let us take the cathode reaction. Since we are taking the aqueous solution of the salt, there will be water also, right? So water will also move towards the cathode. So there is H2O giving rise to H plus plus OH minus, and Na plus is going to take up one of the electron to form Na. But remember that there is some OH minus molecules which will react with some of the Na plus molecule also. So a few amount of base is also produced, that is NaOH. NaOH is also produced along with the sodium atoms that is formed. So the solution overall is going to be basic. Now let us see what will happen at the anode. At anode we have CH3 COO minus. So this will undergo oxidation. Now we have 2 electron here, right? We have a negative charge, and negative charge means we have 2 electrons. So we are going to convert it into a free radical. So we have CH3 free radical plus there is elimination of CO2 happening over here. So if I take 2 molecules of CH3COO minus, we will get 2 molecules of CH3 free radical and 2 molecules of carbon dioxide. So now these 2 free radicals of CH3 is going to react with each other and is going to form the desired product, that is ethane. So let us see how that happens. We have CH3 free radical reacting with CH3 free radical to form C2H6. Right? So this is what is happening in the Kolb's electrolysis. So here we can see at the anode oxidation is happening. So what is happening? Two electrons are being removed. So from two molecules, two electrons are being removed. So the negative charge of the oxygen is converted into free radical. Now there is elimination. So there is cleavage here, and ultimately there is elimination of carbon dioxide. And two molecules of methyl free radicals are reacting to give the desired product. At anode we can see two reactions. One is OH minus formation. Some of the OH minus will react with the Na plus in the solution to form NaOH as well. Now we cannot prepare methane from Kolbe's electrolysis because we do not have any compound which is having any carboxylic acid having less than one carbon, right? We need compounds which is having less than one carbon to prepare methane, and that is not possible. Hence we cannot prepare methane, but we can prepare from ethane onwards, and usually we prepare for even number. Now let us take a flowchart to understand Kolb's electrolysis in a little more elaborate way. If we have a monocarboxylic acid like propanoic acid, we will get alkane on carrying out the Kolb's electrolysis. But if we have a dicarboxylic acid like succinic acid, let us take it out. What is happening when we have succinic acid? So in the case of succinic acid, we have COOH, CH2, CH2, COOH. This is the formula for succinic acid. So the first step is we have to convert the hydrogen into sodium. This is the first step. So we have to remove the hydrogen and we are going to add sodium. Next step, we have to form the ions. So we can remove the sodium and we can add negative charge. Next is oxidation. When we are carrying out oxidation, we are going to remove the COO and we are also going to remove the COO minus. So ultimately, this much part is removed and now we are left with a CH2 free radical, and also we have a CH2 free radical over here. These two free radicals are going to react to form a bond, so we will be getting an alkene. Now let us take another example, that is CH double bond CH double bond CH, single bond COOH, single bond COOH. This is known as fumaric acid. So if I am carrying out the same process for fumaric acid, there is elimination of two molecules of carbon dioxide. Two molecules of carbon dioxide is eliminated because in the first step we are removing the hydrogen. So now there is a free radical formed over here and there also a free radical. So there is a triple bond formation. So from dienoic acid we will be getting an alkyne. So here we will be getting an alkyne if we are using dienoic acid, and if we are using a dicarboxylic acid there will be an alkene. So once again, a quick recap for the trick for Kolb's electrolysis. If we are asked a question from Kolb's electrolysis, without doing the mechanism, we can do it directly. Like we have CH3, CH2, COOH. We have to prepare alkane. So what to do? We just have to remove this part. Just form a free radical. Take the another molecule. If that is also same, then let us take it as same. Now join these two with a single bond. These two free radicals are joined with a single bond. Now we get butane. If we took 2 carbon containing molecule in the reagent side, we will be getting 4 carbon containing product side, right? So that is all about the Kolb's electrolysis. So that is the end of preparation of alkenes. So let us just quickly recap the preparation of alkenes. We have discussed the preparation of alkenes from alkenes. From alkenes we can use hydrogenation, that is addition of hydrogen. From alkynes also we can do it the same method. Haloalkanes we can use reduction using zinc and HCl, and another method is Wood's reaction. Wood's reaction, what is the reagent? It is sodium in dry ether. What is happening? If we have CH3Br, that is going to react with another molecule of CH3Br, will form CH3CH3. So general reaction is RR plus 2 molecules of sodium plus R dash X, sorry, Rx plus 2 molecules of sodium plus R dash X will form RR plus R dash plus R dash R. Now from alcohols we can use red phosphorus in the presence of iodine. From aldehydes and ketones we can use Clemmensen reduction or Wolff-Kishner reduction. From carboxylic acid we can carry out decarboxylation, or we can use Kolb's electrolysis. Now let us see the conformations of alkanes. Here we will be just discussing a brief introduction of conformation. We have a separate video on isomerism wherein we will discuss about this in detail. Now, what is conformations? Conformations means these are the spatial arrangement of carbon atoms. It is the spatial arrangement of carbon atoms which is formed by the rotation of a single carbon-carbon bond. That means if I have a carbon-carbon bond like this is a carbon and this is also a carbon, I'm going to rotate this bond, and the rotation of this bond will result in different structures, or we can say different spatial arrangements. These spatial arrangements are called as conformers or rotamers. Now, what are the two conformers of ethane? For ethane, we have an eclipsed configuration and a staggered configuration. Now we can see over here that the staggered configuration is more stable than the eclipsed configuration. In eclipsed configuration, we have to remember that the dihedral angle, that is the angle of turning, is 0 degree or approximately 0 degree, and in the case of staggered configuration, the angle of turning or the dihedral angle is coming out to be 60 degree approx. Let us move on to the physical properties. In physical properties, first one important is the nature. So as we can see over here, C1 to C4 are gases, C5 to C17 are liquids, and those which are higher than 18 carbons, they are going to be solids. So this state is important. And second important thing is related to their solubility. We know like dissolves in like, so we can say they are soluble in organic solvents. Now, next one is boiling point. So boiling point, we have to remember just 2 points. That is, boiling point depends on the length of the carbon, or we can say number of carbon in the chain. And second factor that is considered is branching. When the number of carbon increases, boiling point also will increase, and when the branching increases, boiling point will decrease. So let us take a table here. As you can see over here, we have butane, 2-methylpropane. These two are having same number of carbons, right? These two are having same number of carbons, but what is happening to the boiling point? Butane is having a higher boiling point than 2-methylpropane. Why? Because branching is present in 2-methylpropane. So always remember, branching will decreases the boiling point and number of carbons will increase the boiling point. So if you are asked to compare the boiling point, first factor that we have to consider is the number of carbon chain, and if the number of carbons in a chain is same, then we have to consider the branching. So now let's move on to the reactions of alkanes. We have the following categories of reactions in alkanes. First one is substitution reaction. Second is oxidation reaction. In oxidation, we have complete, incomplete, and controlled oxidation. In controlled oxidation, we have reaction with copper, reaction with KMnO4, reaction with MO2O3, and also we have reaction with manganese acetate. Then we have isomerization, aromatization, and finally we have pyrolysis. So let us take this one by one. First one is known as substitution reactions. Now what is substitution reactions? Here one or more hydrogen atoms can be replaced by halogens or nitro group or sulfonic acid group. This is known as substitution. Now halogenation can take place at higher temperature, or it can take place in the presence of diffuse sunlight or in the presence of ultraviolet sunlight. Now the lower alkanes are not usually going to undergo nitration and sulfonation reaction. This is also important. So let us take the chlorination here. Now what is chlorination? We are adding chlorine, or we are substituting, we can say, we are substituting chlorine one by one. Here we have a 4 hydrogen, so we are removing one of the hydrogen and we are going to substitute it with a chlorine, so we get CH3Cl. Now if I am adding, or we can say if we are substituting one more molecule of chlorine, we get CH2Cl2. If we are substituting one more chlorine, we get CHCl3, and if we are substituting one more chlorine, we will be getting CCl4. Now let us see the priority orders. Now this is an important concept because if we get a difficult question, this is important. If we have a primary carbon, if we have a primary hydrogen, we can say the hydrogen which is present on a primary carbon is known as primary hydrogen. So the primary hydrogen has a selectivity value of 1, secondary will have a selectivity value of 3.8 and tertiary is having a selectivity value of 5. Now what does this mean? Let us take an example to understand what is the selectivity order and what is the significance of this selectivity order. Why do we need this selectivity order and all? Here we can see a compound. Let us look at this question. Identify the major product when this particular compound is subjected to chlorination. So here what we have to do, we have taken the compound here, and what we are going to do is we are going to categorize the hydrogens as primary, secondary and tertiary. This carbon and this carbon is same. We can say they are equivalent. But this is also a primary carbon, but this is not equivalent to this. So this is a primary hydrogen. So let us put how many similar type of hydrogen are there here? 6. So let us take their priority order or the selectivity order as 6. Now this one has 3 hydrogen of the same type and their overall selectivity order is 3. Here we can see this is secondary. Secondary will have approximately 4 as the selectivity order. So let us have 8 here because we have 2 hydrogen. So the selectivity order is 2 into 4 is equal to 8. Here also we have the selectivity order as 8. This is a tertiary hydrogen, so its selectivity order is coming as 5. So overall we can say that we have different hydrogen and we have assigned these selectivity values for each of these hydrogen. Now, which is having the maximum selectivity value? The maximum selectivity is 8 and that is for a secondary carbon, or we can say secondary hydrogen. So now in this particular molecule, the chlorine will substitute first the secondary carbon, or we can say it will substitute the secondary hydrogen, not the tertiary, not the primary, because chlorine does not have a very specific nature. It can substitute either in the primary or in the secondary or in the tertiary. It depends on the selectivity order, that is 5 is to 3.8 is to 1. Which is greater, it will go and substitute over there. Like it is like a person, if he gets MBBS then also he will study, and if he does not get MBBS then also he will study. That is the nature of chlorine. But if we take the case of bromine, the story is different. In the case of bromine, if he get MBBS then he will study, but if he don't get MBBS he will not study. He is very particular, so he will go and react only if there is a tertiary compound. So there is order tertiary greater than secondary greater than primary. Now fluorination is too violent to be controlled, and iodination is very slow and it is almost a reversible reaction, and hence it is carried out in the presence of oxidizing agents like HiO3 or HNO3, so that we can remove the excess of Hi that is formed, because this Hi is going to convert the reaction in the opposite direction. It is going to carry out the reaction in the opposite direction also, but that is not desirable here, right? So since it is not desirable over here, we are going to restrict that by adding HNO3 or HiO3, which are oxidizing agents. Now the mechanism is very simple. It is a 3-step mechanism. We have initiation, where we have generation of free radicals. Now the free radicals are combining with each other to form different other free radicals. That is known as propagation. Here we can see there is formation of CH3 free radical and Cl free radical, and the final step is known as termination. In termination, 2 free radicals are going to combine to form a molecule so as to stop the chain growth. So this is known as chain termination reaction. So this is about chlorination. Now let us take the second reaction, that is combustion. Now combustion is basically reaction with oxygen. So when we are reacting a methane or any other hydrocarbon with oxygen, we will be getting carbon dioxide and water. And how to balance this equation? If we learn this equation, it is well and good. We can directly substitute. Otherwise also we can directly balance it by the normal traditional method of balancing, the trial and error method. Now if we are carrying out incomplete combustion, we will not be getting carbon dioxide. We get water, but we will not get carbon dioxide. Instead we get carbon in the solid form. Now this is known as carbon black, and that is used for the manufacture of ink, printer ink, black pigments, and also it can act as filters. Now the third one is controlled oxidation. Controlled oxidation, we have 4 conditions here. First one is by using copper. If we are using copper, we can convert an alkane to an alcohol, corresponding alcohol. Now what is the meaning of corresponding? Corresponding means if we have one carbon in the reactant side, we will have one carbon in the product side. The same number of carbons in the reactant and the product side, that is known as, we can say, corresponding. So here we get corresponding alcohol. Second compound, we have used MO2O3, so that will convert it into so here we have methanol, sorry, we have methanol here, so it is converting it into corresponding aldehyde. Now we have alkane, which is reacting with manganese acetate, so we are getting acid here, carboxylic acid here. Now this is the most important reaction. We have a tertiary alkane that is converted into a tertiary alcohol by using KMnO4, and here we cannot use primary and secondary, we will just use tertiary alkane to convert it into tertiary alcohol. Let us move on to the next reaction, that is isomerization. Isomerization is the production of isomers of a particular compound. We have reagent here, anhydrous AlCl3 and HCl. So if I am treating a particular compound with anhydrous AlCl3 and HCl, we will be getting its corresponding isomers. These two are the major products, and then we have the minor isomers also. Next, aromatization. In aromatization, if we have 6 carbon containing or more than 6 carbon containing compounds, they are treated, they are heated at 773 Kelvin and 10 to 20 atmospheric pressure in the presence of oxides of vanadium or molybdenum or chromium supported over alumina to get dehydrogenated and cyclized to benzene and its homologues. Homologues means derivatives. That means if we have a 6 carbon containing molecule, we will carry out the aromatization. What are the reagents used for aromatization? We have Cr2O3, V2O5 or MO2O3. We will get benzene. Now if we have toluene, we can prepare it from a 7 carbon containing alkane, and that is going to be heptane. Now let us look at the reaction with steam. If we are reacting it with steam, we will be getting CO plus H2. This is known as water gas. And this water gas can be used for the preparation of dihydrogen gas, which we will study in inorganic chemistry. Moving on to the last reaction, that is pyrolysis. What is pyrolysis? We have a larger alkane which is heated to form smaller homologues, or we can say smaller fragments, and these fragments can either be alkanes or it can be alkenes. Now this is following again free radical mechanism and preparation of oil gas or petrol gas from kerosene oil or petrol, that is involving pyrolysis. So that is the advantage of pyrolysis. For example, dodecane, as we can see over here, this is a bigger alkane that is also undergoing pyrolysis, that is giving a mixed chain of heptane, pentene and other products are also formed in the reaction. So this is all about the theory of alkanes. Now let us do the problems related to alkanes. Let us now do the problems related to alkanes. Question number 1. CH3, CH2, CH3 and CH3C triple bond CH can be distinguished by, if we are using Bayer's reagent or tolerance test or Br2/CCl4, all of these are going to react with the tertiary only and not the primary. So all of these can be used to distinguish these two. So the answer is option number 4. Question number 2, CH3COOK on Kolb's electrolysis. We have to remove this and we have to form the free radical, and we will be getting CH3 single bond CH3. We have to double the number of carbon. Indicate the expected structure of the organic product when ethyl magnesium bromide is treated with heavy water. So this is a reaction of Grignard reagent. If you know about Grignard reagent, let's just do this. Otherwise, just don't get tense, because we have a separate video for Grignard reagent which will be uploaded soon. So we have taken C2H5 MgBr. This is reacting with D2O. So this is going to give us D plus and OH minus or OD minus. And this is going to be the positive side and this is going to be the negative side. The positive side is going to react with the negative side to form C2H5D. So the product is going to be C2H5D. The answer is option number 4. Now here is today's DIY. You have to write down What are the reagents which are used for the following conversions? Comment all the 6 answers in the comment section below. And the top 3 names will be published in the next video. Now let's do another question. A mixture of ethyl iodide and N-propyl iodide is subjected to Wood's reaction. The hydrocarbon that will not be formed is. So we have to find which is not formed. Ethyl iodide contains 2 carbon, so we have to double, that is butane is possible. N-propyl iodide, so we have to double 3, so we get 6, so hexane is also possible. And if we are adding these two, we have 2 carbon here and we have 3 carbon here. Adding, we get 5 carbon, so 5 carbon containing pentane is also present, but propane is not present, so that is going to be the answer for this question. N-hexane on heating in the presence of Cr2O3 will give benzene because the process is aromatization. So let's move to the next process. Next question. Hydrocarbon which is liquid at room temperature. We have studied C1 to C4 are gases and C5 to C17 are liquids. So we have pentane as the answer. Which of the following isomers will have the highest boiling point? As we can see, all of these are isomers, and if we have isomers, then we have to consider the long chain. So we are going to consider the first one as the answer. On electrolysis of sodium succinate, the alkene that is obtained is. What is the alkane? We have CH2COONA. Sorry, CH3COONA, CH3COONA. So we are going to remove this part and we are going to join this with the double bond. So we are getting the ethene over here, and the nature of the solution after electrolysis is going to be basic, which we have already discussed in the theory. Next question. The boiling points and densities of N-pentane, isopentane and neopentane decrease in the order. Highest will be for N-pentane because no branching is present, then comes isopentane and then comes neopentane. So it will be 1 greater than, 2 greater than, 3. So the answer is option number B. Which of the following is the correct sequence of steps in the chain reaction? Initiation, propagation and termination. Answer is option number D. Sodium salt of isobutyric acid on heating with soda lime. Sodium salt of isobutyric acid. So we have CH3, C, CH3. So we have a hydrogen here and we have COONA. So this is going to be eliminated and another same molecule should be added over here. So we have CH, CH3 and we have another CH3. Next question. To carry out the following reactions, we can carry out in the presence of concentrated H3PO4. This is also used. What is X in the following sequence of reactions? X is CH3COOH. Let us take how it is. We have CH4 as the final product. So what will be the corresponding reagent? It will have one more carbon extra, that is CH3COONA. So if we have to subtract Na, we will be getting CH3COOH. We just have to carry out in the reverse order. In chlorination, the relation rate of abstraction of hydrogen in tertiary, secondary and primary carbon are respectively 5:3.8:1. In iodination, for the preparation of iodomethane, the compound used is HiO3 and HgO. So the answer is option number 3. Now this one is again a question which is based on Grignard reagent, we can say. So here also we have, this is the positive sign and this is the negative side. Here we have D plus as the positive side and OD minus as the negative side. So the negative side is going to react with the positive side and the positive is going to react with the negative side. So we have deuterobenzene is the answer. So let us look at this particular question. What is it stating? We have to find what is the compound A. So this is basically decarboxylation. So we have to check by reacting it with NaOH. Every compound, near to every compound, we will write NaOH and we are going to remove an Na2CO3. So we will get the desired product in these two cases. So the answer is option number 4. Name the alkane which cannot be prepared by Wood's reaction, and the alkane which cannot be produced by Wood's reaction is methane. And this is an important question as well. Now let us discuss the next question. Sorry, this is the last question of our discussion. So with this we are ending our first video where we have discussed about alkanes. So in the next part we will be discussing about alkenes and alkynes, that is tomorrow. So stay connected with at Neetshala. You can also join the Telegram channel for all the notes and updates. So stay safe and happy learning. Hi everyone, welcome to Neetshala Organic Chemistry Lecture Series Part 2. In this part, we will be discussing about alkenes and alkynes. So let's get started with alkenes. First, let us study about the preparation of alkenes. We can prepare alkenes from a variety of compounds such as alkynes, haloalkanes, vicinal dihalides, also from alcohols and carboxylic acids. So let us see what are the different methods of preparation of alkenes. First method of preparation is from alkynes. How can we prepare alkenes from alkyne? We have two different reagents to study over here. One is known as Lindlar's catalyst. Now, what is Lindlar's catalyst? Lindlar's catalyst is basically palladium in the presence of carbon or quinoline. Quinoline, which is basically a sulfur compound, are poisons, which is deactivating the charcoal. And this is used for the preparation of cis-alkene from an alkyne. So if we are treating alkyne with Lindlar's catalyst, we will be getting a cis-alkene, matlab hydrogen will be substituted to the same side of the plane. And we have another reagent which is sodium in the presence of liquid NH3, and this will give us trans-alkene, and this reaction is known as Birch reduction. This reaction is known as Birch reduction. So we have to remember this in mind, that Lindlar's catalyst will give us cis form and Birch reduction is going to give us trans form. So now let us move on to the second method of preparation, that is from alkyl halides. Now whenever we have an alkyl halide such as these, and if we are treating it with alcoholic KOH, which is also known as alcoholic potash, so at that time what is happening, a process which is known as beta elimination is going to happen. Now what is beta elimination? As we know, the carbon to which the main substituent is attached is known as the alpha carbon, and the carbon which is just adjacent to the alpha carbon is known as the beta carbon. Now what is happening is that when we have a halo acid like this, a halogen acid like this, beta elimination will happen. Now what does that mean? One of the substituent, that is the major substituent from the alpha carbon, and one of the substituents from beta carbon will be removed off, leaving behind two free radicals, and these two free radicals are going to join to form a bond, and we get an alkene. So what is the mechanism of dehydrohalogenation? Dehydrohalogenation means from the alpha carbon we have to remove the halogen, and from the beta carbon we have to remove a hydrogen. So this is the process of dehydrohalogenation, and dehydrohalogenation is an example for beta elimination reaction, which is followed through free radical mechanism. Now let us see some important note over here which is given in NCERT. We can get the order based question from here. What is that? First one is the order of reactivity of halogens towards beta elimination reaction. It is iodine, then bromine, then chlorine, and least is fluorine. And when we consider the alkyl group, the reactivity of the alkyl group towards the beta elimination reaction is following the order tertiary, followed by secondary, and finally we have the primary. So this order is important for exams. Now let us see the third method of preparation, which is from vicinal dihalides. Now how can we prepare alkenes from vicinal dihalides? Here, what are vicinal dihalides? Vicinity means neighboring positions. So in the neighboring positions, we are having halogens substituted. So when we are treating it with zinc metal, what is happening is that these two halogens are removed off, and that is going to join with the zinc to form ZnBr2. Again, we are left with free radical over here and also a free radical on the carbon, second carbon. So between the free radicals of the first carbon and the second carbon, there is formation of a double bond. So that will result in the formation of an alkene. So we can say that dehalogenation is a process which is used for vicinal dihalides because we have to remove two halogens, and it is also following free radical mechanism. Now let us see the next one, which is from alcohols by acidic dehydration. Now acidic dehydration, what do you mean by dehydration? Dehydration means it is the removal of something. D means removal and hydration, so it is removal of a water molecule, and this is carried out in the presence of H plus. It is carried out in the presence of H plus, that is why it is known as acidic dehydration. Now what is happening if we have an alcohol of the formula CnH2n plus 1 OH? If that is the alcohol, what is happening? One of the hydrogen from this part is moving out and the OH is also moving out. So what is happening? We get an alkene of the formula CnH2n. So I will write a general reaction for this. So we have CnH2n plus 1 OH. This is undergoing the process of acidic dehydration to give us CnH2n. So we are eliminating a molecule of water. OH is coming from this side and one of the hydrogen is coming from the alkyl part. So this is an example for acidic dehydration, and again acidic dehydration is also an example of beta elimination where OH is moving on from the second carbon and hydrogen is coming out from the first carbon. So let us see the example here. Here we can see the OH on the alpha carbon, and this OH is removed out along with the hydrogen in the adjacent position, that is in the beta carbon. So these two are removed, resulting in the formation of free radicals here, and they are going to be joined with another single bond, so we get a double bonded compound, that is ethene. And what is the reagent that is commonly used? We are using concentrated H2SO4. It is a strong acid. With this, we complete the preparation. We have already studied the preparation of how we can prepare alkenes from carboxylic acid. So comment below which is the carboxylic acid which is used for the preparation of ethene. Now let us move on to the physical properties. There is not much thing to discuss in physical properties because the physical properties of alkenes are comparable with alkanes. So let's just go through this and let's see if there is any important stuff here. Alkenes as a class resemble alkanes in physical properties except in the types of isomerism and the difference in the polar nature. First three members, that is C1, C2 and C3, are gases. Next 14 are liquids and the higher ones are solids. So we have to study which are the gases. We have ethene and propene. Also we have butene, these are the gases, and then we have the liquids, and from 15 onwards we have the solids. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless. So every gases are colorless and ethene is an exception because it has a faint and a sweet smell. Now they are insoluble in water but are fairly soluble in non-polar solvents like benzene, petroleum, ether, like we have studied yesterday, like dissolves in like. And they will show a regular increase in the boiling point with increase in the size, that is every CH2 group added increases the boiling point by 20 to 30 Kelvin. Like alkanes, the straight chain alkenes have higher boiling points than isomeric branched chain products. So like we studied yesterday, boiling point is directly proportional to the number of carbon atoms, and it is inversely proportional to the branching. The same thing is followed here also. Let us now move forward to the next part, that is the chemical properties. Now the reactions of alkenes are basically divided into four categories. First one is addition reaction. In addition we have electrophilic addition and free radical addition. Very rarely it will show substitution reactions as well. We have oxidation, ozonolysis, and substitution in this chapter. So let us start with the most important reaction, that is ozonolysis. Now what is ozonolysis? Ozonolysis is a process of addition of ozone molecule. So we are adding ozone molecule, that is O3, into an alkene. This will result in the formation of an ozonide. So let us consider this as a hut, or we can say this is a home, and these people are going to destroy every homes. So these are our terrorists. So these terrorists, that is zinc and water, they are going to destruct the home. So we can say home is our war zone. So what we need to do is, first we need to create a home. How can we create a home from an alkene? We can create it by adding of ozone molecule, and once we get the home, we are going to destroy the home by using a terrorist. And who is the terrorist? It is zinc and water. We will get some new homes, and whatever remains or remnants of the terrorists attack was there, that we are going to remove, and we are going to create a bond between the remaining. We're going to create a bridge in between all the unwanted stuffs here. That is what we are doing in the process of ozonolysis. So let us do the process. Let us take an example for ozonolysis. If we have CH3, CH double bond, CH2, we are going to add oxygen. So we will put one oxygen at the top of double bond, one oxygen just below the carbon on the left side, and one oxygen just below the right side carbon. And we will just join the bonds like these. We will create a hut, and now we are going to add zinc and water, as a result of which what is happening, there is a cleavage of bond that is happening like this. From the roof to the base the cleavage is happening, and now we are getting two different compounds. Now we will put a double bond here, so we get CH3CHO, which is an aldehyde, and we are getting HCHO, which is methanol, again an aldehyde. So we have got two aldehydes over here. So this is the process of ozonolysis. Let us take another example. This is 2-methyl propene. 2-methyl propene is undergoing the process of ozonolysis. So here also we have to put the oxygen one above the double bond, one below the left side carbon, one below the right side carbon, and form an ozonide. And here we have a CH3, and here we have a CH3 again. We are going to cleave the bond from the roof to the base again, and here we have a ketone. So if we have 2CH3 attached to the carbon onto which the double bond is attached, then there is a possibility that we get a ketone. So here we are getting a ketone, and the other one is going to be an aldehyde. Right, the other one is going to be an aldehyde, and on the left side we have a ketone. So that is why we have HCHO, which is an aldehyde, and this particular ketone is also formed over here. Let us move on to the next reaction. Now let us move on to the next reaction, that is the addition reactions. First addition reaction that we are going to discuss over here is the addition of dihydrogen. So if we have to add dihydrogen, we can use platinum or palladium or nickel. So when we are adding hydrogen by using platinum, palladium or nickel, we get alkane, and if we are doing the same reaction on an alkyne, then we will be getting an alkene initially, and again on hydrogenation we get an alkane. Now let us move on to the addition of halogens. Halogens का मतलब dihalogens, that is X2. So when we are reacting it with X2, what are we getting? Let us see the reaction. We are using carbon tetrachloride as the medium for the addition of dihalides. So one of the bromine is going to be adding to one of the carbon, and another bromine is added to another carbon, so we get a vicinal dibromide. And now let us move on to the next compound, the addition of the next compound, which is hydrogen halide. Now hydrogen halide, when we are adding, we have some conditions. What are those conditions? If it is symmetric alkenes, it is okay, we can add it in any fashion. Hydrogen towards one side and bromine towards the other side, like this. There is no problem for that, and even this is an symmetrical alkene. So in the case of a symmetrical alkene, we can put hydrogen on one side of the double bond and bromine on the other side, because even if we read from the front side or even if we read from the opposite side, it is the same. So that is the reason why there is no problem in the case of symmetrical alkenes. But what happens in the case of unsymmetrical alkenes? Let us see. In the case of unsymmetrical alkenes, if I put hydrogen over here and bromine over here, I will be getting a compound like this. And if I am putting hydrogen over here and bromine over here, then I will get a compound like this. Now the problem is, which of these is the major compound and which of these is the minor compound? How do we judge that? For that, we have a rule which is known as Markovnikov rule. So let us learn a very interesting story of Markovnikov. Markovnikov, let us consider that he is the villain of our story here, right? So he is a very rich person and he does not want any poor person to become rich. For that, what he is telling, if he is the king of any country, he will say that give the poor all the burden and make the rich much more richer. This is what he said through the rule which is known as Markovnikov rule. Now the country is organic chemistry and the people are the alkenes. So let us take an alkene to understand what is this particular rule. If we have CH3, single bond CH, double bond CH2, we can see that this side of double bond is deficit of hydrogen because it has only one hydrogen, and the other side, that is the right side, is having two hydrogen. So which is the poor side and which is the rich side? This is going to be the poor side and this is going to be the rich side. Now according to Markovnikov, we have to add the H to that side which is excess of hydrogen. That is, hydrogen should be added to the right side and substituent should be added to the other side, which is the poorer side. This is what is known as Markovnikov's addition. Now the most important thing is the mechanism of Markovnikov's addition. Markovnikov's addition follows carbocation mechanism. Now what is that mechanism? Let us learn about that now. Let us first dissociate this HBr. It is not going to give us hydrogen free radical and bromine free radical. Rather, it is going to give us H plus and Br minus. Now, first let us take the carbocation. First we have to prepare a carbocation and then only we can substitute the negative part, right? So first let us create the carbocation. For that, let us treat the alkene with H plus. And when I am treating the alkene with H plus, two possibilities can be there. Either we can substitute it on the right side and get a primary carbocation, and another possibility is that we can substitute it on the left side and we can get a secondary carbocation. And as we know, the secondary carbocation is more stable as compared to the primary carbocation. And since it is more stable, we will follow this one and not this. So to this we will add the Br minus. So the bromine will substitute to the second position and it is going to be the stabilized product. So we are getting 2-bromopropane as the major product, right? So now let us move on to anti-Markovnikov's addition, also known as peroxide effect or Kharash effect. Now always remember, Kharash effect or peroxide effect will happen in the presence of a peroxide. And this Kharash is a very good person. He wants the poor to become rich and rich to become poor. So what is happening? We have to add hydrogen to that part which is deficit of hydrogen, and the substituent should be substituted to that part which is already having enough of hydrogen. So let us see a mechanism. Let us take benzoyl peroxide. Let us take benzoyl peroxide. This is an organic peroxide, and we are going to undergo the homolysis, and we will be getting free radicals. Benzyl peroxide के free radicals मिलेगा, और we are going to remove this carbon dioxide molecule to get C6H5 free radical and CO2. Now two such C6H5 free radicals are formed. One of these is going to react with an HBr to form C6H6 plus Br free radical. Now it is this Br free radical that is going to attack onto the alkene. So can I say that this benzoyl peroxide is a free radical generator? Yes, it is a free radical generator which helps in the generation of a free radical, that is Br free radical. Now this Br free radical is going and substituting on the alkene, and now we may get two different products. One is a primary free radical of alkene and another is a secondary free radical. Now as we know, secondary is more stable, so we are going to substitute the H plus over here, because bromine already gets substituted first and then only a hydrogen is moving. So now we are getting two products here, and here one is secondary secondary free radical and another is a primary free radical. And since secondary is more stable than primary, we are going to react that particular free radical with another molecule of HBr to give us CH3 CH2 CH2Br. That is the final product. So what we have to remember over here, the most important thing to remember is that in Markovnikov's addition we are following carbocation mechanism, and in anti-Markovnikov's addition we are following free radical mechanism. And what is the conditions for anti-Markovnikov addition? We have either H2O2 written at the top, or we have organic peroxide like benzoyl peroxide. Now let us see what is a question, what is the type of questions which we can expect over here. Now we don't have to write the mechanism every time for questions like these. Suppose we have hex 1ene, that is CH3 double bond CH2, that is going to be repeated 3 times, and finally we have CH3 6. Yes, so we are going to add HBr according to absence of peroxide, that is anti-Markovnikov's addition. So this is the poor side and this is the rich side, poor side and rich side. If we are not following the Markovnikov's addition, we will add the substituent over here. This is CH2, so we will add the substituent over here. Br is added to this side and hydrogen is added to this side. And if we are following Markovnikov's addition, then we will add the substituent over here and we will add the hydrogen over here. So this is about the Markovnikov's and anti-Markovnikov's addition. We have another examples of this as well. One is the addition of sulfuric acid, and we can also add sulfuric acid in the same method. We are taking H plus and HSO4 minus. This HSO4 minus is adding to the alkene by again Markovnikov's addition. Addition of water is also in accordance with Markovnikov's rule, where we have H plus and OH minus. So this OH minus will substitute to that side which is having less hydrogen. Now moving on to the next reaction, that is oxidation. So now let us discuss oxidation. In oxidation we have to remember a reagent which is KMNO4. Now KMNO4 can be dilute, it can be concentrated. First we are going to take dilute KMnO4, which is basically cold dilute aqueous solution of potassium permanganate, is known as Bayer's reagent, and this Bayer's reagent is used for the test of unsaturation. How can it be used for the test of unsaturation? Is because this is changing its color. It will fade the purple color, and as a result of which the purple color solution which we have initially is going to be changing to a colorless solution, a faint colorless solution. So let us take an example. We have CH2 double bond CH2. We are going to treat it with dilute KMnO4. At that time, what is happening? If we have dilute, we are going to get diol. So we can remember it like this. Dilute gives diol. So we will get ethane 1,2-diol, which is also known as glycol. Now let us take another example. CH3 CH twice CH2. Sorry, CH3 CH double bond CH2 plus dilute KMnO4. What is it going to give? To this position also we get an OH, and to this position also we get an OH. So it's a very simple fact that if we are using dilute KMnO4, we will be getting a diol. So I will write that trick here. Dilute gives diol. Now let us see what happens in the case of concentrated. In the case of concentrated KMnO4, or in the presence of acidic potassium dichromate, what is happening is that the alkenes are oxidized to ketones or even to acids, depending upon the nature of the alkene and the experimental condition. Like over here, we have substitution of methyl groups on the carbon. So whenever we have methyl groups, more than one methyl groups which is substituted on a carbon, there is a possibility of ketone. And the other part which has just a hydrogen, that is going to give us carbon dioxide. And in the case of but2-ene, what is happening is that this part does not have any substituent, like two substituents of carbon is not present anywhere. So here one of the substituent is hydrogen and another is CH3. So what is happening, this is going to cleave like this, and this side is going to get oxidized, double oxidized, so it is going to give us CH3COOH. Now how to do this type of problems? We have a short trick for that. If we have substituents like this, two alkyl groups which are substituted on the carbon, that is going to oxidize to give this, that is ketone. On the other hand, if we have one of the hydrogen and another is a alkyl group which is added to the double bonded carbon, then we will be getting carboxylic acid. And if we simply have an alkene, then it is oxidized to carbon dioxide. So this is an important memory aid which will help you in solving the questions related to addition of KMnO4. Now let us move on to polymerization. Now polymerization is a very simple process. We have to just create a chain of monomers. A chain of monomers is going to give us polymers. The same reaction we will study in the chapter of polymers, and polymers is very important because it will help in preparation of many of our day-to-day needs. And some conditions are also given here: high temperature, pressure, and catalyst. The catalyst which is used is this, plus C2H5 thrice plus TiCl4. This is going to be the catalyst which is used, and the name of this catalyst is Ziegler-Natta catalyst. So now let us move on to the part of alkynes. Now first we are going to discuss about the structure of alkynes. We know that alkynes have a triple bond. Triple bond means we have one sigma and two pi bonds, and these two pi bonds are mutually perpendicular to each other. One is aligned along px axis and another is along py axis, as a result of which we will be getting two mutually perpendicular pi bonds. The electron cloud between the two carbon atoms is cylindrically symmetrical about the internuclear axis, and the structure is a linear molecule. We have to remember the hybridization. Hybridization is sp hybridization. We won't get questions based on this, but just remember the strength of carbon-carbon bond. It is 823 kilojoule per mole, and that is more than that of carbon double bond carbon and carbon triple bond carbon. Sorry, carbon single bond carbon. So this is the important fact. And another important fact is the hybridization, that is sp hybridization, and the number of pi bonds and the number of sigma bonds. Pi is 2 and sigma is 1. This is what we are supposed to know from this particular topic. Now let us see the preparation. We can prepare it from calcium carbide and from vicinal dihalides, from alkyl halides, Kolb's electrolysis method. So let us see it one by one. First method of preparation of alkyne is by the hydrolysis of carbides. So if I take calcium carbide is hydrolyzed to give us ethine. And remember here there is 2 carbon in the carbide, so we will be getting an alkyne with 2 carbon. And if I am taking a carbide with 3 carbon, as you can see over here, then we are going to get an alkyne which is having 3 carbon. So this is the trick that we can remember. If we have a 2 carbon containing carbide, we will be getting an alkyne with 2 carbon. And if we are taking a carbide with 3 carbon, we will be getting an alkyne with 3 carbon. Next is dehydrohalogenation of dihalide, that is this. So what are we going to do? In the first step, we are going to remove an HBr such a way that we are going to remove this bromine and hydrogen from here in the first step. And in the second step, we are going to remove bromine from the first carbon and hydrogen from the second carbon. That means we are carrying out 2 steps of beta elimination or 2 steps of dehydrohalogenation, and that will result in the formation of alkene. Now, dehalogenation of a tetrahalide. We are removing these 2 Br2 again by the process of dehalogenation, that is again a beta elimination method, and doing it twice by using zinc, we will be getting alkyne. Another is from alkyl halide. We can react the sodium salt of alkyl halide with another alkyl halide. Sodium salt of an alkyne is reacted with alkyl halide to give us NaX is also removed out, and we will be getting RC triple bond C single bond R. The last method is Kolb's electrolysis method that we have already studied. If we have a dienoic acid, the salt of this dienoic acid on electrolysis will give us alkyne. And another example is given over here. We can directly convert it into alkyne from carbon, that is by using an electric arc at a very high temperature of 1475 Kelvin. So these are the different methods of preparation of alkynes. The most important ones is the first one, and also the Kolb's electrolysis is very important. These 2 are the most important ones. And since NCERT also mentions vicinal dihalide, so this is also an important and an easy method. Now let us move on to the physical properties. Again, the physical properties of alkynes follows the same trend as that of alkanes and alkenes. First 3 members are going to be gases, next 8 are going to be liquids, and the higher ones are going to be solids. All alkynes are colorless. Ethyne has a characteristic odor. Other members are odorless. Alkynes are weakly polar in nature. They are lighter than water and they are immiscible with water, but they are soluble in organic solvents like ethers, carbon tetrachloride, and benzene. Their melting point, boiling point, and density increases with increase in molar mass, just as we have seen in the case of alkenes and in the case of alkanes. Now let us move on to the chemical properties of alkyne. The first one that we are going to discuss is the acidic nature of alkyne. So here let me take an example to illustrate this. If we are reacting NaNH2, which is a strong base, NaNH2 is a strong base, so when it is reacting with C2H2, it will liberate hydrogen gas. It will liberate hydrogen gas. So this particular reaction indicates that this C2H2 is acidic in nature. This will indicate that it is acidic in nature. Now, this is one explanation for acidity of alkyne. Another explanation is by the percentage as S character. Now, how do we predict the percentage S character? Let us see. Let us calculate over here. We have the hybridization of C2H2 as sp hybridization. sp hybridization means there is 50% s character, which is very high as compared to that of sp2 and sp3. Since it is very high as compared to sp2 and sp3, this is going to be the most acidic group of compounds. So we have an acidity order here. This is the acidity order. So we can see that more the s character, more is the acidity. So if we are asked to compare the acidity of different compounds like the one which was asked in 2017, what we have to do is step number one is take out the hybridizations. More the s character, more is the acidity. This is the first comparison. And if we have two compounds which is having the same hybridization, then lesser the number of carbon, more is the acidity. So this is the important point to note. Acidity is directly proportional to hybridization, or we can say percentage s character, and it is inversely proportional to number of carbon. So this is the most important point. Using this, we can solve any questions related to acidity orders. So let us see the reactions also. The reaction is, it is reacting with sodium and also sodamide. The same reaction is going to give us. So that is going to give us monosodium ethanide, and also we will get hydrogen gas, like we are doing with any of the metals, right? If we have sodium and sodium is treated with any acid, it will give us hydrogen gas plus a salt, right? So here also the same mechanism is followed. We have sodium and we are going to treat it with C2H2, then it is going to give us HC triple bond CNA plus hydrogen gas. So the same reaction is happening in both cases. The analogous reactions is happening in both cases. Hence we can conclude that alkyne is acidic in nature. Now let us move on to the addition reaction. Again, the same mechanism is followed over here. We have Markovnikov's rule applicable in the case of alkynes as well. Let us see the addition of dihydrogen. Again, the catalyst used is platinum, palladium or nickel. So in the first step, we will be getting an alkene, and now we have to carry out the hydrogenation in alkene to get an alkane. Coming to the addition of halogens, we can add it in the first step to get a substituent like this. We will get an intermediate like this, and again on treating it with Br2, we will be getting a tetrabromopropane. First we got a propene, and again on halogenation, or we can say again on addition of halogens, we will be getting tetrabromopropane. And now we have addition of water, and this is a very important reaction. We had nearly 3 to 4 questions in the past years, so this is very important. We have to treat the alkyne with water in the presence of Hg2 plus and H plus at 333 Kelvin. So when we are doing the following conversions, what is happening is that the OH will be substituted to that part which is having lesser number of hydrogen. Okay, so here, as we know, it is a symmetrical alkene. Since it is a symmetrical alkyne, so we have no problem. We can add H to one side and OH to another side. Then it will undergo keto-enol tautomerism, as a result of which it is going to form the keto form, that is this. Here, if I consider another example, which is an unsymmetrical alkyne, what we have to do? First step is we have to add hydrogen to that part which is having excess of hydrogen, and OH to that part which is having deficit of hydrogen, and then we have to carry out the keto-enol tautomerism, and as a result of keto-enol tautomerism, we are getting a ketone. So if we have hydrogen, then it is going to give us an aldehyde, and if we have methyl groups on both sides, we will be getting a ketone. Now we have polymerization. Polymerization is of two types. We have linear polymerization to give us compounds like polyacetylene. If we have C2H2, this one polymerization will give us polyacetylene. And cyclic polymerization is carried out in the presence of red hot iron tube. This is going to give us benzene. So this is important. This was asked, similar type of question was asked in Neet 2019 Odisha paper as well. So these are the reactions of alkyne. With this, we are concluding the theory part of alkynes. Let us now quickly discuss some of the important questions which is related to alkenes and alkynes. Question number 1. An alkene A on reaction with ozone and zinc in the presence of water gives propanol and ethanol in equimolar ratio. Addition of HCl to alkene A gives B as the major product. Structure of the product B is. So here we have to use two reactions at the same time. So it's a very important question which is asked in NEET 2019. Let us see how to solve with such type of questions. An alkene A is reacted with ozone and zinc in the presence of H2O. That means we have the process of ozonolysis. The products of ozonolysis are given, that is propanol. So let us arrange propanol like this: CH3, CO, CH3. And I am going to arrange ethanol as CH and CH3. Now let us put the other oxygen so that we can get an ozonoid like structure, and let us bring our terrorist here, and so that they create a war and destruct the home. Now we have the war zone, we are going to remove the war zone. All the war zones are removed. Now both the enemies are on the either side. Now let us separate them using a bridge, and the bridge is a double bond. Now we get a compound like this. What is the next step? We have to add HCl. Hydrogen should be added to this side according to Markovnikov's addition, and chlorine should be added to this side. So option C is going to be the answer. Sorry, we have to carry out the opposite way. Chlorine will come to this side and hydrogen will come to this side according to Markovnikov's addition. So the answer is option number C. Now let's move on to the next question, which is a theoretical question. We have to create cis-alkene. Cis-alkene is created from alkyne, so we have to use Lin-Las catalyst, that is hydrogen in the presence of palladium or quinoline. Now here what we have to do, we have to calculate the number of sigma bonds which is present in the product A. So what will be the product? The product is not benzene. We will be getting 3 CH3 groups as well. This is the product that we are getting. You have to calculate what is the number of sigma bonds over here. So that is a DIY for you. We have to calculate what is the number of sigma bonds. You have to comment the answer below. Comment. Now let us do the next question. The question which I have told you before. What is the correct order of acidity? First will be alkyne. So either this can be an answer or this. So we have to consider the second one. Once we consider alkyne, next we have to consider the number of carbon. 3 carbon containing alkyne is also there. 2 carbon containing and 3 carbon containing is there. So 2 carbon containing will be more acidic because it is inversely proportional to the number of carbon. So this is going to be the answer. First 2 carbon and then 3 carbon, and then comes alkene and finally comes alkane. Now this is a complete the reaction type of question. So let us see how to solve this question. First step, we are going to treat it with NaNH2 in the presence of liquid ammonia. So when we are treating it with NaNH2 in the presence of liquid ammonia, we get CH triple bond CNA. That is, a sodium gets substituted at this position. Now that is reacting with CH3CH2Br according to the question. So what is happening? NaBr is eliminated out and this alkyl part is substituted over here instead of sodium. Now we are going to carry out the reaction with NaNH2 again. So it is substituted to the other side, that is this side. And now again we are adding CH3CH2Br, so that is getting substituted in the place of sodium. So this is the final product that we are getting. Easy question. Now which of the following reagents will be able to distinguish between 1-butene and 2-butene? It is NaNH2 because NaNH2 will react with terminal alkenes only. It will react with terminal alkynes only, and so it is going to react with 1-butene only, and 2-butene will not give the reaction. So this is a question from NCERT. An alkene A on ozonolysis will give us a mixture of ethanol. So let us make the structure of ethanol here. CH3 and H, and pentan 3 on, so it is C, C2H5, C2H5 and C double bond O. So this is the structure of the two compounds that is given in the question. We have to find what is the structure of alkene. So create an oxenoid and do the cleavage, remove all the war zone, and now what we have to do, we have to just create a bridge. So this is the alkene that we are getting. Find out the structure of the alkene, which on ozonolysis will give us these products. Now whenever we have carbon dioxide in the question, always keep the carbon dioxide in the middle like this, and C6H5, C6H5CHO. So let us keep it like this. We will put an oxygen here, and this oxygen is attached to a carbon, and on the carbon we have C6H5 and a hydrogen, and on the other side we have CH3 and a hydrogen here. So we have to remove this oxygen, we have to remove these oxygens as well, right? And now what are we getting? We have CH3, CH, double bond C, double bond C, H, C6H5. This is the compound that we're getting. We're getting an alene type of compound. Let's do the next question. Propanol and pentan 3 on are the ozonolysis products of propanol. So it is going to be CH3, CH2, CHO. And we have pentan 3 on. So we have C double bond O, C2H5 and C2H5. Create the ozonoid, break the bonds, remove the war zone, and now create the bridges. So this is the compound that we're getting. An alkene A contains 3 carbon-carbon bonds, 8 carbon-hydrogen bonds, and 1 carbon-carbon double bond. A on ozonolysis gives 2 moles of an aldehyde of molar mass 44U. So let us take the homologous series of aldehydes. The first member is HCHO. Obviously HCHO will not have 44U. But if we consider CH3CHO, we can identify that its mass is 44U. So we can say that the aldehyde of this question is CH3CHO, and we are given 2 moles of this aldehyde. So let us take 2 moles here. That is CH3, C double bond O single bond H, and another molecule of, so I will put the hydrogen to this side, and we have C double bond O, H and CH3. Let us create the ozonoid, cleave everything, and we will rub off the unwanted people, and let us create a double bond in between them. So now we are getting this particular alkene. So here we can see there is 3 carbon-carbon bonds here, and we are having 8 carbon hydrogen bonds and 1 carbon-carbon double bond. The catalyst which is used to reduce an alkyne to alkene is, the answer should be Lindlar's catalyst, right? Now let us move on to the next question. We have this compound, we have to add this. What is the example? It is an example of nucleophilic addition. This is a rare case where we have nucleophilic addition, so we have to study this. It's important. Now this is a question based on Kolb's electrolysis and also decarboxylation. We have acetylene, sorry, not Kolb's electrolysis, it is based on KMNO4. So this on oxidation, this bond is going to cleave and we will be getting acetic acid, and this acetic acid is now undergoing decarboxylation, so it will give 1 carbon less, so we will get CH4. Question number 17, Mg2C3. Mg2C3 will give us a compound that will have 3 carbon. So the compound C will be having 3 carbon. So this is wrong. Now C has a terminal CH3 group, so it will give tolerance test. But we have to find C. I am talking about A. So let us first treat it with sodium. So when we are treating it with sodium, we get this compound. And finally, when we are treating it with CH3Br, we will be getting this compound. So this is not having a terminal alkene, so it will give us tolerance test. It does not contain an acidic hydrogen, so it will give us tolerance test. That is incorrect statement, right? That is the incorrect statement. Now let us move on to the next question. So here we have to add Hi. So this is basic mechanism type of question. We have to add hydrogen to that side which is deficit of hydrogen. Sorry, it is according to Markovnikov's addition. So we have to add hydrogen to that side which is having more hydrogen. And which side is having more hydrogen? Here both sides are having same, so we have to look for stability. Now when we are considering stability, we can say we have to add the iodine to this side and hydrogen to this side, because the number of hyperconjugation structures is more in the case of this side. So the answer should be 2. Now this is the last question for today. The minimum heat of hydrogenation is in. So first of all, we will write down the products A and B. A is coming out to be the cis form, and A is coming out to be the trans form because we have used Birch reduction, and B is going to be the cis form because we have used the Lindlas catalyst. And since we know transbutane will show minimum heat of hydrogenation because trans is more stable as compared to cis form, so we can say the answer should be 1. Now this is a very simple question. In which of the following reactions Markovnikov's rule is not observed? As we can see here, this is peroxide, and here also there is peroxide. So whenever peroxide is there, Markovnikov's is not followed. We have Karash effect, so it is 4. Now this is a question for you to think and be patient and do this question. You have to carry out ozonolysis at 3 positions of the double bond. Right? So here we have to take both the isomers of benzene and carry out the process of ozonolysis. And when we are taking the ozonolysis, we get all these products. So take your own time and do this process. Although it looks a bit confusing, but make a beautiful diagram and then it will be easy for you to solve. So this brings us to the end of this lecture. So we have completed alkanes, alkenes and alkynes in the 2 parts. In the next part, we will be discussing about the aromatic compounds, and we will be also discussing some of the important questions from NCERT exemplars as well as NCERT exercises based on the chapter hydrocarbons, and we will be finishing off this chapter. So see you again in the next lecture. Till then, goodbye and happy learning. Hi everyone. Welcome to Neetshala Organic Chemistry Revision Lecture Series Part 3. In this part, we will be covering the topic of benzene, and we will be also completing the chapter hydrocarbons. So let's get started with the topic of benzene. The first part is the structure of benzene. Now everyone knows that benzene can exist in 2 resonance forms, and these 2 forms are known as the Kekulé structures of benzene. So since the pi electrons of the benzene are always rotating from one position to other position, so we can represent it in the form of a circle. So this will say that the electrons are moving in the form of a circle from one position to the next position, and from there to the next position, and so on, so as to become stable. Now, what is the impact of this particular delocalization of the pi electrons on the bond length of benzene? So let us see it one by one. X-ray diffraction data reveals that benzene is a planar molecule. It is not a non-planar molecule, it is a planar molecule. Now, if we have any one of these structures correct, then what happens? We have the correct bond length of C single bond C and C double bond C. But since we do not have a particular structure as the exact structure of benzene, so we observe that the carbon-carbon bond length in benzene is intermediate of that which is expected from the normal carbon single bond carbon bond and carbon double bond carbon bond. If I take the carbon single bond carbon bond in other molecules, it is 154 picometer, and carbon carbon double bond is coming out to be 133 picometer. But the bond length of carbon carbon bond in benzene molecule is intermediate between these two, that is 139 picometer. So this is the most important observation which we can expect, or we can conclude from this particular Kekulé structures. Now, the absence of pure double bond also has another impact, that is, benzene shows a slight reluctance to show addition reactions under normal conditions, because it has somewhat a single bond character and also somewhat a double bond character, right? And due to the presence of this, it shows a slight reluctance towards addition reactions. Now let's start with the preparation of benzene. We have three methods of preparation of benzene as mentioned in NCERT. So let us look at the first method, that is the natural or the commercial method of preparation, that is from coal tar. Second is by the cyclic polymerization of ethine. These are the chemical methods. We have one more coming up. So first let's discuss these two. The cyclic polymerization of ethine, which we have already discussed in the previous lecture, where we have an ethine molecule. We will take three such molecules, and this is treated with red hot iron. This is treated with red hot iron or copper at 873 Kelvin to convert into benzene. And we have also discussed a question based on this in the previous lecture. Now let us see the decarboxylation of aromatic acid. We have already studied how the process of decarboxylation is carried out in normal acids, right? In the straight chain acids. But now we have the aromatic acid over here. So again the same thing, we have to treat it with soda lime. Soda lime, as you remember, is a mixture of NaOH and CaO. So we are going to remove the Na2CO3 part, that is NaO from NaOH and NaOO from the other part, so that Na2CO3, the complete part, is going to move out, and this hydrogen which is left, that is going to be substituted onto the benzene ring, and we get the benzene here. This is the second method of preparation, that is decarboxylation of aromatic acids, which follows again the free radical mechanism. Now the third one is the reduction of phenol, and this reaction is important. It has been asked in Neet and also in many other competitive exams as well, and it is quite easy. If we are adding zinc dust, if we are adding zinc dust to phenol molecule, we will be getting benzene along with zinc oxide. So this is the third method of preparation of phenol, and this completes the methods of preparation of benzene. Now let us see the next topic, which is the properties of benzene. First, let's discuss about the physical properties of benzene. Benzene or any other aromatic hydrocarbons are always non-polar molecules, and they usually exist as a colorless liquids, or they can also exist as solids, like the naphthalene balls which we use. They are solids and they have a characteristic aroma. Now, the naphthalene balls is used in toilets and also for the preservation of clothes because of its unique smell of the compound and its moth repellent property. So this is important about naphthalene balls. And these aromatic hydrocarbons, they are immiscible with water. They do not usually get solubilized with water, but they are miscible, or we can say soluble, in organic solvents. So we can say again that the like dissolves like. Now when we are heating the benzene, we can say that we are getting a sooty flame with a soot deposit in the base. Now let us look at the chemical properties. Now usually the arenes are showing electrophilic substitution reaction, but under certain controlled conditions we have addition as well as oxidation, even substitution reactions as well. So let us discuss about the electrophilic substitution reactions first of all. Now in electrophilic substitution reaction, we have to substitute an electrophile. Now here the questions can ask regarding the reactions, and also they can ask questions related to the electrophile. And also they can give a set of reactions and ask which of the following is not following electrophilic substitution or which of the following is following electrophilic substitution. These are the possible types of questions which we can expect from this particular topic. So let's get started with the very first part, that is nitration. Now always remember, if we have benzene, we have 5 types of electrophilic substitution reactions: nitration, halogenation, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. These are the 5 different types of electrophilic substitution reactions which are undergone by benzene. So let us start with the very first reaction, that is nitration. In nitration, what is happening? We are adding a nitro group to the benzene ring when benzene is heated with a mixture of concentrated nitric acid and concentrated sulfuric acid. And this mixture of concentrated nitric acid and concentrated sulfuric acid is known as a nitrating mixture. And one important point is that here the generation of electrophile is important in this particular reaction. This paragraph, which is given after the mechanism, is very important because this had a question in Neet previously. We have to remember that for the formation of nitronium ion, first step is what is happening is we are taking the sulfuric acid and we are going to react it with HNO3 also, right? So at that time what is happening is that this oxygen has lone pair of electrons and it is going to donate it to this particular hydrogen because this bond is slightly showing a tendency to move towards the oxygen atom over here. So what is happening is that there is formation of this structure and also we have a formation of HSO4 minus. So here the nitric acid is going to act not as an acid but it is going to act as a base. So this is important for the generation of electrophile. In the case of nitration, nitric acid in the nitrating mixture is going to act as a base. This has been asked in NEET previously, so this is important. Now let us see the nitration reaction. We have to treat benzene with concentrated HNO3 and concentrated H2SO4. So this is the base and this is the acid. As a result of treating these two, we will be getting the electrophile, and electrophile are positively charged species. So we can say that NO2 positive is the electrophile, and this NO2 positive is going to attach to the benzene and it is going to form nitrobenzene along with the elimination of a water molecule. Now let us see the second type of electrophilic substitution reaction, which is known as halogenation. What is halogenation? Arenes reacts with halogen in the presence of Lewis acid. Now what are the Lewis acid? We have anhydrous FeCl3, FeBr3, or even we have AlCl3. These are the Lewis acids, the anhydrous Lewis acids which we are taking for the process of halogenation. So when we are using these particular Lewis acid, what is happening is that we can get the corresponding electrophile, and the electrophile over here can be Cl plus or it can be F plus. So in general we will write it as X plus. This X plus, where X is a halogen, is known as halogenium, or we can say in the case of chlorine it is known as chlorinium ion, right? It is known as chlorinium ion because it is a positively charged species and it is not a negatively charged species. So we are getting chlorobenzene as the product when we are treating it with Cl2. Moving on to the sulfonation. Now when we talk about sulfonation, we are adding an SO3H group to the benzene ring. For that we will use the fuming sulfuric acid, or even we can use oleum to some extent. So if we are using this, that is fuming sulfuric acid in the presence of benzene, then we will be getting benzene sulfonic acid, as you can see in the reaction. So here the electrophile that is formed is SO3H group. This is getting attached over here. Now let us see the Friedel-Crafts alkylation reaction. Alkylation means we have to add an alkyl group. And from where can we add an alkyl group? Alkyl group can be added into the benzene ring if we treat it with an alkyl halide, and if we have to do the acylation reaction, then we have to add an acyl group. For that we will use an acyl chloride as the reagent. This is important. For alkylation we will use alkyl chloride or any alkyl halide as a reagent, and in the case of Friedel-Crafts acylation reaction we will be using acyl chloride as a reagent. Now what is happening over here? Here the electrophile that is formed is CH3 plus, and that is going to get attached to the benzene, as a result of which we are getting the desired product. Now in Friedel-Crafts acylation, what is happening? We are getting COCH3 group, and this COCH3 group, COCH3 plus, that is going to get attached to the benzene molecule. As a result we will get the corresponding molecules like acetophenone. But there is another case over here. If we are using the excess of electrophilic reagent, it can lead to further substitution reactions, and if we are using Cl2 in excess in the presence of anhydrous AlCl3 and dark and cold conditions, then the chlorine will be substituting all the positions of hydrogen, and we will be getting a compound like this, which is known as hexachlorobenzene. So this is an important reaction. Now here is a question given here. Why do we get isopropyl benzene on treating benzene with 1-chloropropane instead of N-propyl benzene? So let us take the molecule 1-chloropropane and another is isopropyl 1-chloropropane is treated with benzene. So let us take the reaction. 1-chloropropane means we have CH3, CH2, CH2Cl. So if I am removing the chlorine, I will get the carbocation as CH3, CH2, CH2. We are not going to do by mechanism, we are just going to do it in a general method. So we will be getting CH3, CH2, CH2 free radical, with a positive sign. That is, it is a primary carbocation. Now let us check whether there is any other possibility for getting stability. Yes, if I am removing one hydrogen from here and if I am keeping it over here, there is a possibility for a secondary carbocation, right? So we are going to carry out a process which is known as 1,2 hydride shift. And as a result of 1,2 hydride shift, now one of the hydrogen is going to shift from here, and this is going to get a CH3. The negative charge from this carbon is going to be removed, and we have the negative charge, which is positive charge, which is coming over here. So this is what we are getting as the final product, as the final carbocation. Now it is this particular carbocation that is reacting with a benzene. So we have benzene and we have CH3 and another CH3. This compound is known as isopropyl benzene, which is also known as cumene. About which we will study in detail in the chapter of alcohols, phenols and ethers, because from cumenes we can prepare phenol. Now let us move on to the next topic, that is the mechanism of electrophilic substitution reaction. Now for the entrance point of view, mechanism is not much important, but still we should have a general idea about this mechanism. According to experimental evidences, the SE, or we can say the substitution electrophilic reactions, they are following a 3-step mechanism. Step number 1 is generation of an electrophile, and once the electrophile is generated, now there is a carbocation intermediate formation, and this carbocation intermediate is called as a sigma complex. This is important. And finally, this sigma complex is highly unstable, so it is non-aromatic as well. So if we have to make it stable, we have to convert it into an aromatic form. For that we have to remove a proton, and that removal of proton will form the carbocation intermediate. And finally the other part will come and join, and it will become a stable molecule. That is the process. So let us take an example. During chlorination, alkylation, and acylation of benzene, anhydrous AlCl3, being a Lewis acid, helps in the generation of Cl plus, R plus, RCO plus, that is known as acidium ions, by combining with the attacking reagent. So we have chloronium ion, we have alkonium ion, and we have acidium ion, which is formed as the electrophile when reacting with a Lewis base, which is known as AlCl3. So this is the process in which we can get these electrophiles. But in the case of nitration, as I have already told, we have H2SO4, which is acting as the acid, and HNO3 acting as the base, as a result of which we are getting NO2 positive in the second step of the reaction, right? So we are getting NO2 positive as the electrophile. Now we have the benzene ring, which is attacking the electrophile, which is attacking the benzene ring, right? So we have an sigma complex which is formed over there, that is basically the adenine ion, and this tries to get stabilized by the resonance structure. These are the resonance structures, but it loses the aromatic character because of the delocalization of the electrons, stops at the sp3 hybridized carbon, because to the position where the electrophile is substituting, that carbon is an sp3 carbon, and since it is an sp3 carbon, the aromatic character is stopped because the resonance or the delocalization of pi electrons happens only with sp2 carbons, right? So here we have an sp3, and as a result of which the process of delocalization will stop over there, and as a result of which it is going to be unstable. So to become stable, it have to regain the sp2 character. For that, it is going to remove this H plus, and that is known as deprotonation, right? It is known as deprotonation. So the sigma complex will releases a proton from the sp3 hybridized carbon on attack by AlCl4. So for the process of deprotonation, again we are going to use AlCl4 or HSO4 minus, that is the Lewis acid which we used before, and as a result of which we get some byproducts also, and we will get the major desired product. So this is the mechanism of electrophilic substitution reactions. Now let us see the second class of reactions, which is known as addition reactions. Now what is addition reactions? We are adding, right? We are adding some reagents, and here we have to study two addition reactions. One is of hydrogen and another is of chlorine. So when we add hydrogen to benzene, we will be getting cyclohexane, because all the double bonds will be broken, and to both sides we will get hydrogen added up. As a result, we will get cyclohexane, and we also have to study the catalyst which is used in the process, which is nickel. Now let us see the second reaction. The second reaction is we have to add chlorine molecule. So we will use UV light, and chlorine gets substituted at all the 6 positions, breaking all the double bonds, and we get benzene hexachloride, that is BHC, which is commonly known as gemaxine. So this is gemaxine molecule, benzene hexachloride molecule. Now let us see the combustion reactions. When heated in air, benzene burns with a sooty flame, as we have already discussed, and that will result in the formation of CO2 and H2O. So this is the combustion reaction. As in the case of general alkanes or alkenes, the same process is happening here also. We get CO2 and H2O in the complete combustion process. Next, we are going to discuss the directive influence of a functional group in monosubstituted benzene. So here we have to study about the ortho, para, and meta substituents. So let us take one by one. The first one is ortho and para directing group, and what effect are they having on the benzene ring. Now we have an OH group here, right? Compounds like, or we can say functional groups like these, in addition to the halogens and OH group, they are an example for orthopara directing group. Now what do? They are activating the ring, right? But halogens are deactivating the ring slightly. However, they are also orthopara directing group because they exert more electron density in these two positions, that is in the ortho and para positions, right? So These are the groups, and the groups names are important, and we have to study whether it is ortho para directing, whether it is activating, or whether it is deactivating. If it is bringing electrons to the ring, it is known as activating, and if it is taking away from the ring, it is slightly deactivating. Now let us take meta-directing group. We have NO2, CN, CHO, COR, COOH, COOR, and SO3H group. These are known as deactivating groups, and they will exert less electron density on the ortho para positions, and they will exert more electron density at the meta positions. Hence, the electrophile attacks on comparatively the electron-rich meta position. As a result, meta substitution will happen, and in the other case, ortho or para substituted products are obtained. We will study about this in detail when we discuss the coming chapters as well. Moving on to the last topic of this chapter, that is carcinogenicity and toxicity. Now, there are some compounds which are carcinogenic in nature, and they are aromatic as well. Now, what is carcinogenic? Carcinogenic means they have cancer creating, they are cancerous cells creating compounds, and they will have more than two benzene rings attached in the form of compounds like these. These are some of the examples of compounds. What do? They will cause us mutation, and they could also result in addition or substitution of genes in the DNA, and ultimately it will cause us cancer. So let us look at the examples one by one. The first one is 1,2-benzanthracene. Number 2 is 3-methyl-chloranthracene. Third one is 1,2-benzpyrene, 1,2,5,6-dibenzanthracene, and the last one is 9,10 dimethyl 1,2-benzanthracene. So these 5 names are important, and their structures are also important. They can ask in the exam. This one has 4 benzene rings. This one has 1, 2, 3, 4 benzene, and we have a cyclopentane ring. Here we have 5. Here also we have 1, 2, 3, 4, 5, and here we have 4 with 2 methyl groups. So this is all about the chapter, and now let us discuss some of the questions related to benzene. This is a question asked in Neet 2018. The compound C7H8 undergoes the following reactions. We have to say what is the product C. Now we can see C7H8 means we have to add a CH2 group, CH3, C6H5 plus CH3. That means it is a phenol molecule, right? It is a toluene molecule. So we got a toluene molecule. So to this toluene molecule, we are going to react it with Cl2 and heat it. So if we are reacting it with Cl2 and heating, we won't get chloro substituted products. What is the reason? Because the reagent is absent. We do not have anhydrous AlCl3 written here. We do not have anhydrous AlCl3. We simply have Cl2. If we simply have Cl2, and if we are applying light or UV rays, then what is happening? It is going to substitute the hydrogens. The basic alkyl substitution happens, and as a result of which we get CCl3. Now this CCl3 is a meta-directing group, so the Br2 will be added at the meta positions, and now we have to react it with zinc and HCl, so this will add hydrogen to the compound, and we will be getting this final product as 1, that is meta-bromotoluene. Let us move on to the second question. The electrophile which attacks in the Friedel-Crafts acylation is acylium ion, that is this. Now let us see the sulfonation of benzene. The reagent used is, in sulfonation we are using SO3 as the electrophilic reagent. They have asked for reagent and not the electrophile. If they are asking what is the electrophile, then answer should be 1. Electrophile is 1, but since they have asked for electrophilic reagent, we can say this is the answer. Benzene undergoes substitution reaction more easily than addition. What is the reason? It is because of the delocalization of pi electrons. Next question, C6H6, which is benzene, is treated with a compound Z in the presence of AlCl3 to get toluene. So we have a benzene ring, and to this benzene ring we have to add a CH3. So for that we can use an alkylating mixture. An alkylating mixture consists of AlCl3 and CH3Cl. So CH3Cl can be used. Chloromethane is the answer. Now this is the last question. Toluene is reacting with K2Cr2O7 in the presence of H2SO4 to give us a compound Y. What is Y? This is a strong oxidizing agent, so it will convert the CH3 group into COOH, so we will be getting benzoic acid as the final product. So these are some of the important questions related to benzene, and with this we are completing the chapter hydrocarbons. So we will be having an assignment first. What is the assignment? You have to practice the MCQs from NCRT Exemplar. From NCRT Exemplar, and comment your scores. Like, you take it as a test and comment your scores. How much MCQs were you able to attempt correctly, how much you made mistake, and also mention the question numbers which you have doubts. In the end of the course we have a separate lecture for all the NCRT exemplar questions which you people are having doubts. So let us discuss all those questions. So for that, you do it as a test first of all and analyze your performance, and whichever questions you have doubt in NCRT exemplar, please comment it in the comment section below. Now, before we conclude today's lecture, we have some important announcements. Basically, we have three important announcements. Number one, today is 3/7/2020, and yesterday Dr. Ramesh Pokhriyal sir, the respected MHRD minister, has made the following tweet. Today, they are looking at the prevailing circumstances and requests received from the students and parents appearing for JEE and Neet examinations. A committee consisting of DG NTA and other experts have been advised to review the situation. They haven't yet discussed about postponement or cancelling the exam, but they are going to review the situation. That is what we are getting from the MHRD minister today. So we can hope for the best for today. So let's wait and watch, because we are going to get the report by today or maximum by tomorrow from the HRD ministry and also from NTA regarding if there is any change in NEET examination date or not. And second important announcement is, as per your request, we are going to start up the inorganic chemistry revision lecture series soon. But before that, don't forget to like, share and subscribe on the YouTube channel, and also support us in the Play Store by giving your valuable feedbacks in the Play Store. The link will be given below. So with this we are concluding the chapter, and next chapter we will be taking up the most easiest chapter of chemistry, which is environmental chemistry. We will be reading complete NCRT and we will be covering all the possible MCQs which can be asked from that chapter. This will be the first time in YouTube that we will be having a complete NCRT reading of this particular chapter. So let's do this in the next day. So till then, happy learning and keep revising. Hi everyone, welcome to the Organic Chemistry Revision Series powered by Neetshala. In this lecture, we will be discussing the chapter Environmental Chemistry from the point of view of NCRT and also for the examination of NEET. So let's get started with the chapter Environmental Chemistry. Environmental studies, as you know, deals with the social, economical, biological, physical and chemical interrelations with our surroundings. Now in this unit we will be focusing mainly on the chemical aspects in the topic, that is environmental chemistry. Environmental chemistry deals with the study of the origin, transport, reactions, effects and fates of the chemical species in the environment. So let's explore further with environmental chemistry. In this chapter, the main focus is on environmental pollution, the types of pollution, and finally we will be dealing with green chemistry. So let's get started with the first topic, that is environmental pollution. Environmental pollution is the effect of undesirable changes in our surroundings that can have harmful effects on plants, animals, and human beings. Now, what is a pollutant? A pollutant is any substance which causes pollution. Now these pollutants can either be solid or liquid, or they can be gas also. if they are present in greater concentration than in natural abundance. And these can be produced either due to human activities or it can be produced due to natural happenings, like in the case of forest fire and things like that. Do you know an average human being requires nearly 12 to 15 times more air than food? So even small amounts of pollutants in the air becomes significant as compared to the similar levels which is present in the food. So air pollution is more critical, right? The pollutions, now we can divide it into two on the basis of the microbial action. The first one is known as degradable pollutants and the other is known as non-biodegradable pollutants. If we take the case of dichloro-diphenyl trichloroethane, which is DDT, that is an example for non-biodegradable pollutant. Why is it not so? Because it is unable to be degraded by the bacteria and other microbes. Now, these in the process of environmental pollution, the pollutants, they originate from a particular source and they are transported by different means like air, or even it can be transported by water, and it is dumped into the soil by the human beings. So these are the different ways in which pollution are caused. So let's move forward. Let's move on to the first type of pollution, which is known as atmospheric pollution. The atmosphere that surrounds the earth, that is not of the same thickness at all heights. It is basically made up of some concentric layers of air or regions, which we can say of different density. So if we take the lowest layer, that is known as the troposphere, and troposphere will extend only greater than 10 kilometer from the sea level. So if this is the sea level, the distance between the troposphere and the sea level is 10 kilometer. This is 10 kilometer. And if we move 10 to 15 kilometer away from the troposphere, then it is known as stratosphere. So the next layer is the stratosphere. Now these are the two important layers where pollution is happening. So let us see what is happening in the troposphere and also in the stratosphere. So first of all, let's understand the features of troposphere and stratosphere. We have studied the height or the altitude at which both of these layers are present. Troposphere extends up to a height of 10 km from the sea level, and above the troposphere between 10 to 50 km lies the stratosphere. Now, troposphere, as you can see, is a turbulent, it is a dusty zone, and it consists of air, water vapor and clouds. So the winds and the movement of clouds happens in the troposphere, whereas stratosphere contains dinitrogen, dioxygen, ozone and very little water vapor. So ozone, the good ozone, is present in the stratosphere. Now let us see about tropospheric pollution first. Tropospheric pollution occurs due to the presence of undesirable solid or gaseous particles in the air. So let us classify these gaseous particles into oxides of sulfur, oxides of nitrogen, oxides of carbon, hydrogen sulfide, hydrocarbon, ozone and other oxidants. And particulate pollutants includes dust, mist, fumes, smoke, smog and so on. So let us look at each of these in detail. So the first one is the gaseous air pollutants, wherein we are going to discuss about many oxides. The first one is oxides of sulfur. Now oxides of sulfur are produced when sulfur containing fossil fuel is burnt. The most common species is going to be sulfur dioxide, which is poisonous to both animals as well as plants. So even a very low concentration of the sulfur dioxide can cause us respiratory diseases. Now examples for these respiratory diseases includes asthma, bronchitis, emphysema, etc. Sulfur dioxide can also cause us irritation to the eyes. It can also cause us tears and redness in the eyes. Also in plants also it is affected, so it is leading to the stiffness of flower buds, which eventually leads to the fall off of the flower from the plants. Now SO2 can convert into another poisonous gas, that is SO3, but it is a slow process. So it is catalyzed by ozone. The ozone which is present in the higher levels of troposphere and also in the stratosphere can help in the conversion of SO2 into SO3. And also if it is reacting with the water or even in the presence of hydrogen peroxide, it can give H2SO4, and that is released back into the earth in the form of acid rain. Now let us move on to the oxides of nitrogen. Now the main oxides of nitrogen includes NO2 NO3 and so on. So let us take NO2 because this is the major pollutant. Now dinitrogen and dioxygen are present in the air, but these are not much reactive. But under certain conditions, like when there is a lightning, or even in the automobiles when they are combusted, what is happening is that they can react. So at high temperature, that is reacting to form NO. Now this NO is reacting initially instantly with oxygen to give NO2. Now the rate of production of NO2 is faster when nitric oxide, that is NO, reacts with ozone. So this particular oxide is produced in the presence of ozone, that is in the troposphere. So tropospheric ozone is not so good because it helps in the production of many poisonous and pollutant substances, right? Polluting substances. So that is why the tropospheric ozone is also known as bad ozone. So let us now see some of the harmful impacts of this NO2. If we are seeing the traffics of Delhi or any other metropolitan cities, we can see that there is an irritant red haze, right? So this red haze is due to the oxides of nitrogen. And also the higher concentration of NO2 can damage the leaves of the plants, and it can also retard the rate of photosynthesis. Now, nitrogen dioxide is again a lung irritant, and it can also lead to acute respiratory diseases in children. Again, it is harmful to the living tissues, and also it is harmful to the various textile fibers and also to certain metals as well. So now let us look at the third important pollutant, that is hydrocarbons. Now hydrocarbons are produced by the incomplete combustion of fuel. It is produced by the incomplete combustion of fuel, and as we have studied in the chapter hydrocarbons, majority of them are carcinogenic. That means they causes cancer. So that is toxic to humans because it causes cancer. And what effect are they having on plants? They are having a majority of effect in the plants. First, includes the breakdown of the tissues. Second is the shedding of the leaves. Third is the shedding of the flowers, and the fourth is the shedding of the twigs. So it is having harmful effects both in plants as well as in animals. Let us now move forward to the next oxide, that is oxides of carbon. Carbon mainly has two oxides. The first one is known as carbon monoxide, and the second one is known as carbon dioxide. So we can see carbon is forming two oxides. One is carbon dioxide and the other one is carbon monoxide. So which law of chemical combination is obeyed over here? We can see that the mass of the carbon is constant, so the mass of oxygen is following a simple whole number ratio. So the law of multiple proportion is followed over here, right? We can just relate it with some of the basics concepts also. So let us see the oxides of carbon. The first one is carbon monoxide. Now carbon monoxide, as you have studied in biology, it is a very serious air pollutant. Now why is it a serious air pollutant? Because it is blocking the hemoglobin, or it is reducing the oxygen carrying capacity of the hemoglobin. What happens is that the carbon monoxide will react with the hemoglobin. It will bind to the hemoglobin and it will form carboxyhemoglobin. Now hemoglobin likes this carbon monoxide very much that it does not leave it very easily. It gets strongly bind to the hemoglobin, and as a result of which no more oxygen can bind to this RBC, or we can say the hemoglobin molecule, right? So this can have serious impact on the health of the individuals, like it can lead to headache, it can lead to weak eyesight, it can also lead to nervousness, cardiovascular disorders, and that is the reason why people are advised not to smoke. And even in the pregnant woman, it is very important that they should not use smoke or cigarettes. The reason being, the increased carbon monoxide level in the blood can result in premature birth, spontaneous abortions, and also in deformed babies. So this is the harmful impact of carbon monoxide. Now let us talk about carbon dioxide. Carbon dioxide is released into the air by respiration, burning of fossil fuels for energy, and by the decomposition of limestone during the manufacture of cement, that is CaCO3 on decomposition will give us CaO plus CO2. This is the reaction. Now, it is also emitted during the volcanic eruptions. Now, this carbon dioxide gas is confined only to one layer, that is troposphere, and its percentage is just 0.03 percentage. Now what happens is that the excess amount of carbon dioxide which is present in the atmosphere is fixed by the green plants, or it is removed by the green plants, and that is going to maintain an appropriate level of carbon dioxide in the atmosphere. But what happens is that green plants require carbon dioxide for photosynthesis, and in turn they will emit the oxygen, and as a result they are going to create a balance between carbon dioxide and oxygen. But if there is increased fossil fuel burning and if there is increased deforestation, what is going to happen in the presence of these things? The carbon dioxide level in the atmosphere is going to increase, and that is going to result in global warming. So let us look further. Let us see what is global warming and greenhouse effect. About 75% of the solar energy which is reaching the earth is absorbed by the earth's surface. And this is very important because this trapped sunlight produces heat, and that heat is required for the earth's surface, for heating up the earth's surface to increase the temperature of the earth's surface. Rest of the heat radiates back into the atmosphere. Some of the heat is trapped by certain gases such as carbon dioxide. We can see over here carbon dioxide, methane, ozone, chlorofluorocarbon compounds, and water vapor. So these are known as greenhouse gases. So which are the greenhouse gases? It is carbon monoxide, methane, ozone, chlorofluorocarbon, and water vapor. So they will also help in the heating of the atmosphere, and this can ultimately result in global warming. Now, let us study about natural greenhouse effect. Natural greenhouse effect means our earth is like a greenhouse. You might have seen the greenhouse, right? It's a glass jar where the plants are grown. So once the sunlight or once the radiations enter inside, it is not going outside. That is, it is trapped inside the greenhouse. So the same thing is happening in the earth also. Due to the presence of these greenhouse gases, the temperature of the earth remains nearly constant. But what happens is that due to human activities, what has happened is that this ability has led to a disaster. This is leading to the global warming because the carbon dioxide has increased, so it can trap more and more sunlight. As a result, the temperature of the earth is increasing slowly. The annual temperature or the mean temperature of the earth is increasing slowly, and this has resulted in a phenomenon which is known as global warming. Now, this global warming will also result in certain diseases. That is, it will help in the proliferation of certain disease-causing microbes, and as a result of which it can result in diseases like dengue, malaria, yellow fever, sleeping sickness, and so on. Now, let us move forward. Let us talk about acid rain. Now, you already know that our water, that is rainwater, it has a pH of 5.6. Now what is the reason for that? It is mainly due to the H plus ions which is produced, right? This H plus ions which is produced by the combination of water and carbon dioxide. So when water and carbon dioxide is reacting, it will result in the formation of H2CO3, and this H2CO3 will dissociate to form H plus and HCO3 minus. So this H plus is responsible for the acidic nature of the rainwater. Now when the pH of the rainwater is dropping below 5.6, then it is called as acid rain. Now, acid rain is basically the ways in which the acid from the atmosphere is deposited on the Earth's surface. Oxides of nitrogen and sulfur, oxides of nitrogen as well as sulfur, are acidic in nature, and hence they can be blown by wind along with the solid particles in the atmosphere, and finally they can settle down either on the ground, right? It can settle on the ground of dry deposition, that is dry oxides of sulfur and nitrogen can be present, or it can be present in the water, fog, or snow. It can be precipitated down in the form of water, fog, or snow. Then it is known as wet deposition. So this point is important. What is dry deposition and what is wet deposition? Dry deposition means the oxides of nitrogen and sulfur are carried away by winds and it is falling on a certain surface. And what is wet deposition? Wet deposition means the oxides of nitrogen and sulfur, they are dissolved in fog or mist or rainwater, and it is reaching the surface of earth. This is known as wet deposition. Now, acid rain is a byproduct of variety of human activities that emit the oxides of sulfur and nitrogen in the atmosphere. As mentioned earlier, burning of fossil fuels containing nitrogen and sulfur, such as coal and oil in power stations and furnaces, or even petrol and diesel in motor engines, these are responsible for the production of sulfur dioxide and also nitrogen oxides. Now, these SO2 and NO2, after oxidation and reaction with water, they are going to form major acids such as H2SO4 and we have HNO3. Similarly, we have the ammonium salts. The ammonium salts are also formed and can be seen in the atmospheric haze, that is in the aerosol of fine particles. So the aerosol particles of oxides or ammonium salts in the raindrop can also result in wet deposition. SO2 is also absorbed directly on both solid and liquid surfaces and is thus deposited as dry deposition. So ammonium salts is basically seen as wet deposition and sulfur dioxide is basically seen as dry deposition. Now, what are the harmful impacts of acid rain? Acid rain is harmful for agriculture, trees, and plants as it dissolves and washes away the nutrients which is needed for the growth. It causes respiratory ailments in human beings and animals. When acid rain falls and flows as groundwater to reach rivers, lakes, etc., it is going to affect the plant and animal life in the aquatic ecosystem. It is also going to corrode water pipes and that can result in the leaching of heavy metals such as iron, lead, copper, etc. into the drinking water. And it can also damage the prestigious monuments like the Taj Mahal, right? So these are the harmful impacts of acid rain. So now we have a case study of Taj Mahal and acid rain. The air around the city of Agra, where Taj Mahal is located, contains fairly high levels of nitrogen as well as sulfur oxide. Now this is basically due to the large number of industries and power plants around the area. Use of poor quality of coal, kerosene and firewood as fuel for domestic purposes add up to this problem. So as a result of this, what happens is that the calcium carbonate, that is marble, which is the major component of Taj Mahal, is going to react with H2SO4 to form CaSO4 plus H2O and CO2. This is causing damage to this wonderful monument that has attracted people from all around the world. As a result of which the monument is slowly disfigured and the marble is getting discolored and it is losing its luster or the shyness. Government of India has announced an action plan as early as 1995 to prevent the disfiguring of this historical monument. Madura refinery has already taken suitable measures to check the emission of toxic gases. Now we have a plan which is known as Taj Trapezium, which is cleaning the air in the areas around the Taj Mahal. That is basically in the towns of Agra, Firozabad, Mathura, and Bharatpur. Under this plan, more than 2,000 polluting industries lying outside the trapezium, that is the Taj Trapezium, would switch on to the use of natural gas, or it can use liquefied petroleum gas instead of coal or oil. So coal and oil are prohibited now and they can use either natural gas or they can use liquefied petroleum gas. Now a new natural gas pipeline would bring more than 500,000 cubic meters of natural gas a day to this area. People living in the city will also be encouraged to use liquefied petroleum gas in the place of coal, kerosene or firewood. Vehicles playing on highways in the vicinity of Taj Mahal is also encouraged to use low sulfur content diesel because we have already studied that sulfur on oxidation forms SO2 and that is a serious pollutant. With this, we have completed the tropospheric pollution. Now let us see the stratospheric pollution. First one is the formation and breakdown of ozone. As we know, the upper stratosphere, it consists of considerable amount of ozone and it helps in protecting us from the harmful UV radiations which is coming from the sun. And these radiations are causing skin cancer, and skin cancer has a technical name, that is melanoma. Therefore, we have to be protected from the harmful effects of this ozone, right, of the harmful radiations. So we have some ozone layer in the stratosphere which is a product of UV radiations acting on dioxygen molecules. So in the presence of UV radiation, it is forming nascent oxygen. Now this nascent oxygen is reacting with O2 to form O3. This O3 is thermodynamically unstable and thus it decomposes to molecular oxygen. Hence we can say there is a dynamic equilibrium that is existing between the production as well as the decomposition of oxygen and ozone. In the recent years, there have been reports of the depletion of this ozone because of the presence of certain chemicals in the stratosphere. Now, the main chemicals are the chlorofluorocarbon, also known as freons, and these are non-reactive, non-flammable, non-toxic organic molecules and therefore are used in refrigerators and air conditioners. Now, what is happening is that the chlorofluorocarbon, that is CF2Cl2, that can result in a homolytic cleavage leading to Cl free radical and CF2Cl free radical. This Cl free radical is going to react with the ozone, and as a result of which it is going to split the ozone to form O2 and ClO free radical. Now this ClO free radical is going to react with another molecule of oxygen, and as a result of which it is going to degrade. It is going to react with another molecule of nascent oxygen, and as a result of which it is going to again generate Cl free radical and O2. Now what is happening? This Cl free radical again is going to destruct the ozone. So the amount of oxygen is decreased. The amount of ozone is decreased, the amount of ozone is decreased, and the amount of oxygen, that is dioxygen and oxygen, nascent oxygen, that is also increased. These two are increased. As a result, what has happened? The thickness of the ozone layer gradually gets decreased, and this decrease in the thickness of the ozone layer can result in ozone layer depletion. So let us learn about ozone hole. In 1980s, the atmospheric scientists working in Antarctica reported about the depletion of ozone layer, which is commonly known as ozone hole, over the South Pole. It was found that a unique set of conditions was responsible for the ozone hole. In the summer season, nitrogen dioxide and methane is going to react with the chlorine monoxide, that is ClO, and chlorine atoms, forming chlorine sinks, preventing much of the ozone layer depletion. Whereas in the case of winter, what is happening? There is a special type of clouds which is known as polar stratospheric clouds that is formed over Antarctica. And these polar stratospheric clouds provide the surface on which the chloride nitrate gets hydrolyzed to form hypochlorous acid. So these are the set of reactions that is happening. First we have ClO free radical in the presence of NO2 will form ClONO2. That is this particular reaction. Chlorine nitrate to form hypochlorous acid. And now what is going to happen? The chlorine free radical can react with the CH4. It can form CH4, CH3 free radical and HCl. ClONO2 can also react with water and it can form HOCl and HNO3. ClONO2 can react with HCl to form Cl2 and HNO3. So when sunlight returns to Antarctica in the spring, what happens is that the sun's warmth is going to break down this ClONO2 and it is going to form HOCl and Cl2. Now these are photolyzed again. As per these two reactions, we have HOCl converted to OH free radical and Cl free radical, and Cl2 is also giving rise to 2 Cl free radical. So both the Cl free radical, they are going to again initiate the chain reaction for ozone depletion. So what is happening? Once again, we'll just have a quick recap. In the summer season, what is happening? In the summer season, nitrogen dioxide and methane is going to react with the chlorine monoxide, and as a result of which they are going to form the chlorine sink. And this chlorine sink is responsible for majority of the ozone layer depletion. Now, during the winter, what happens is that there is a special type of clouds which is known as polar stratospheric clouds, and these polar stratospheric clouds are responsible for the reaction of chloride nitrate, that is going to react with water to form HOCl, and it can also react with HCl to form Cl2. Both of these, during the sunlight, in the presence of sunlight, they will get converted into chlorine free radical, and this chlorine free radical is again going to result in the depletion of ozone hole. Now let us study the effects of depletion of ozone layer. With the depletion of the ozone layer, more UV radiations filters into the troposphere. UV radiations leads to the aging of skin, cataract, sunburn, skin cancer, killing of many phytoplanktons and damage to the fish productivity, etc. It has also been reported that the plant proteins get easily affected by UV radiations, which can lead to harmful mutation of the cells, and it can result in the evaporation of surface water through the stomata of the leaves and decreases the moisture content of the soil. Increase in the UV radiation can also damage the plants and fibers, and as a result of which they get faded faster. Let us now move on to water pollution. But before we move on to the water pollution, we have to talk about particulate pollutants as well. So let us talk about particulate pollutants and also about the photochemical smoke, about the smog in general. So let's start with the particulate pollutants first. Now, what are particulate pollutants? These are basically minute solid particles or liquid droplets in the air. Now, these are present in the vehicle emissions, they are present in the smoke particles from fires, or even the dust particles and ash from the industries. Particulates in the atmosphere, they can be of two types. Either they can be viable, that means living, or they can be non-viable, which means non-living. Now, viable includes bacteria, fungi, molds, algae, and these are some of the examples of viable pollutants, and we have some non-viable pollutants as well. Now, these non-viable pollutants are of the following type. We have smoke particles, which is consisting of solid or mixture of solid and liquid particles, which is formed during the combustion of organic matter. Second is dust, which is consisting of fine solid particles over 1 micrometer in length, or we can say 1 micrometer in diameter. Now the third one is mist, which is formed by the particles of spray of liquids and condensation of vapors in the air. Now the fourth one is the fumes, which are obtained by condensation of air of vapors during sublimation or distillation, boiling, and other chemical reactions. So we can say generally organic solvents, metals and metallic oxides from the fume particles, they are going to be falling under this particular category. Now, the effect of a particulate pollutant are largely dependent on the particle size. Airborne particles such as dust, fumes, mist, etc., these are dangerous for the human health. Now, if you have a particulate pollutant which is bigger than 5 microns, that is likely to lodge into the nasal passage, and as a result of which they are going to disrupt the pathway of air, and if it is of the length of 10 micron, then it is going to enter into the lungs easily. Now, lead is used as a major air pollutant is emitted by the vehicles. Now, leaded petrol is the primary source of airborne lead emission in Indian cities. So, to overcome that, nowadays we are using unleaded petrol. So, that is an important point. Nowadays we are using unleaded petrol, and as a result of which we can reduce the lead pollution. Now, what is the harmful effect of lead? Lead will interferes with the development and maturation of RBC. So, this particular point is very important from Neet point of view. Lead interferes with the development and maturation of RBC. So let us now move forward to smog. This is the most important topic from this chapter. Most important topic from this chapter is smog. Now, smog is a combination of smoke and fog, and this is the most common example of air pollution that occurs in many cities throughout the world. There are two types of smog. The first one is known as smog. So remember C for C. So classical smog occurs in humid climate, cold and humid climate, and it is a mixture of smoke, fog, and sulfur dioxide. So we can say it is a reducing mixture, and hence it is also a reducing smog. So these characters of reducing as well as oxidizing smog is very important. Classical smog occurs in cool, humid climate, and it is a mixture of smoke, fog, and sulfur dioxide, and it is a reducing mixture, and hence it is known as a reducing smog. Now, what about photochemical smog? Photochemical smog occurs in warm, dry, and sunny climate. The main components of the photochemical smog result from the action of sunlight on unsaturated hydrocarbon and nitrogen oxides, which is produced by the automobiles and factories. Now, this photochemical smog has high concentration of oxidizing agents, and as a result of which it is known as the oxidizing smog. Let us now move to the formation of a photochemical smog. More than this particular part is the important one. So let us now just go through the formation. When fossil fuels are burned, a variety of pollutants are emitted into the Earth's troposphere. Two of these Two of these pollutants that are emitted are hydrocarbons, that is as a result of unburned fuels, and another is the nitric oxide, that is NO. When these pollutants build up to sufficiently high levels, a chain reaction is occurring. And as a result of this chain reaction, the NO is converted to NO2. This NO2 in turn will absorb energy from the sunlight, and as a result of which it is going to react to give NO and nascent oxygen, that is free oxygen atom. Now these free oxygen atoms are very dangerous because they are very reactive and they combine with oxygen to form ozone. The ozone that is formed, it is going to react with the nitrogen oxide and it is going to form NO2, and this NO2 is a brown gas that is sufficiently high levels can contribute to the haze, which we have talked before. Now, this ozone can also react with methane or acrolein to form PAN and formaldehyde. Even these are harmful substances, harmful pollutants. Now, what are the effects of this photochemical smog? Common components of the photochemical smog are ozone, nitric oxide, acrolein, formaldehyde, and peroxyacetyl nitrate. Photochemical smoke can cause serious health problems. Both ozone and PAN can act as powerful eye irritants, and ozone and nitric oxide irritate the nose and throat, and their high concentration can cause us headache, chest pain, dryness of the throat, cough, and difficulty in breathing. So both of these can result in cracking of rubber and also can cause extensive damage to the plant life, and it can also cause us the corrosion of metals, corrosion of stones, building materials, rubber, and painted surfaces. Now how can we control this? The methods are as follows. The first one is, if we control the primary precursors of photochemical smoke such as NO2 and hydrocarbons, and then the secondary precursors such as ozone and PAN, the photochemical smoke will be automatically reduced. So by using catalytic converters in automobiles, it can convert nitrogen oxide and hydrocarbons can be reduced, because nitrogen oxide get converted to nitrogen and dioxygen, which are comparatively less polluting, and hydrocarbons are completely combusted to form CO2 and H2O by the use of catalytic converters. So that is one method of reducing this particular type of photochemical smoke. Now another way is by the use of certain plants such as pinus, juniperus, quercus, pyrus, and vitis, which can metabolize nitrogen oxide, and therefore the plantation could help in reducing of the photochemical smoke. Let us now move further to the next part, that is water pollution. Now, as we know, water is very essential for life, and without water, there would be no life. We usually take water as granted for its purity, but it consists of very few amounts of pollutants as well. And this pollutants originates as a result of human activities through different paths. Pollution reaches the surface of groundwater. Easily identified source or place of pollution is called as a point source. Example, the municipal or industrial discharge pipes, where pollutants either enter into the water source. Now we have non-point sources as well. Non-point sources means which cannot be easily identified. For example, we have agricultural runoff from farms, animals, and croplands, acid rain, stormwater drainage, etc. These are some of the non-point sources of water pollution. Let us now see what are the causes of water pollution. The major cause is the pathogens. Now what are pathogens? Pathogens are basically the bacteria and other organisms which is causing diseases in humans. Example, we have Escherichia coli and Streptococcus faecalis, which is present in the human excreta, and it can cause gastrointestinal diseases. So this is important. Let us move on to the next topic, that is organic waste. The other major water pollutant is the organic matter such as leaves, grass, trash, etc. They pollute the water as a consequence of runoff. Now, extensive phytoplankton growth within the water, even that can be a cause of water pollution. The wastes are usually biodegradable. Now let us see the effect of population of bacteria on water. Large population of bacteria decomposes the organic matter which is present in the water, as a result of which they are going to consume oxygen which is dissolved in the water, and as a result of which the amount of dissolved oxygen is going to be declined. DO will decline, and as a result of which, what is happening, the aquatic life does not have enough oxygen to survive, and when they have no oxygen to survive, they die off. So the growth of fish gets inhibited. Oxygen reaches water through atmosphere or from the process of photosynthesis carried out by many aquatic green plants during daylight. During night, what is happening is that the process of photosynthesis will stop, but the plants continue to respire. And as a result of which, there is a reduction of dissolved oxygen. The dissolved oxygen is also used by the microorganisms to oxidize organic matter. If too much of this organic matter is added to the water, all the available oxygen is used up. This causes oxygen dependent aquatic life to die, as a result of which the anaerobic bacteria begin to break down the organic waste, and it will produce chemicals that have a foul smell, and these are harmful to the human health. Now the aerobic bacteria, that is helpful for us because it is helping in degradation of these organic waste, and they will help or keep the water depleted in dissolved oxygen. Now we have a term which is known as biochemical oxygen demand. What is biochemical oxygen demand? It is the amount of oxygen which is required by the bacteria to break down the organic matter which is present in certain volume of a sample of water. Now the amount of BOD in water is a measure of how much organic material is present in that particular water. If the BOD is greater, then we can say that it is more polluted. So BOD is directly proportional to polluting potential. That means if BOD is more, then pollution is also more, because pollution potential is also more. And BOD is inversely proportional to dissolved oxygen. That means if dissolved oxygen is more, BOD will be less, and if BOD is more, then dissolved oxygen will be less. So this is the two important relations. Now let us move on to the chemical pollutants. Now, as we know, water is an excellent solvent, so there will be many chemical pollutants as well. Let us see some of the chemical pollutants. These are the standard values, maximum prescribed concentration of some metals in the drinking water. Iron, it is 0.2. Manganese, it is going to be 0.05, very less. Then cadmium, as you can see, it is 0.00005, and zinc is 5.0, copper is 3.0, and aluminium is 0.2. So aluminium and iron has the same amount, and zinc up to 5 is possible, but cadmium should be the least, that is 0.005. Let us now see the major water pollutants. We have microorganisms, and it is produced from the domestic sewage. Organic waste, which is produced from domestic, animal excreta and waste, decaying animals and plants discharged from food processing factories. Plant nutrients, which includes chemical fertilizers, toxic heavy metals, which includes industries and chemical factories, sediments, which is caused by the erosion of soil by agriculture and stripe mining, pesticides, which is the chemicals used for killing insects, fungi and weeds, radioactive substances, which is caused by the mining of uranium containing minerals, so this is important, and last one is heat, which is released by the water for cooling in thermal industries. Now let us come back to the topic of chemical pollutants. We have a topic which is known as eutrophication. Now what is eutrophication? Eutrophication is the aging of lake. And why is eutrophication caused? It can be either due to natural processes, or it can be due to human processes. Whenever there is increased fertilizers, whenever there is a runoff of increased fertilizers, what is happening is that the phosphates and sulfates which is present in these fertilizers, they will help in the growth of algae, and ultimately the age of the lake will increase, as a result of which the clarity of the lake is lost, and this process is called as eutrophication. It can be of two types. One is known as natural eutrophication, if it is happening naturally, and if humans are helping in it, then it is known as cultured eutrophication. Now some of the major pollutants of water, chemical pollutants of water includes PCB, it is very important, polychlorinated biphenyls, which is an industrial chemical which is used as a cleansing solvent, detergents and fertilizers. They are a major constituent of water pollution. Also we have sodium and calcium chloride, even these are water soluble chemical pollutants, so this is also important. And these metals can have so many negative impacts, such as it can damage the kidneys, central nervous system, liver, etc. Let us now move forward to the international standards of drinking water. Fluoride. For drinking purposes, water should be tested for fluoride ion concentration. This is very important. Deficiency can result in tooth decay. Soluble fluoride often added to the drinking water to bring its concentration up to 1 ppm. The F- ion made on the enamel of the teeth is much harder by converting into hydroxyapatite. The enamel on the surface of teeth into a much harder fluorapatite. However, F- ion concentration above 2 ppm can causes brown mottling of teeth. So this is important. If there is enough fluorine, that is 1 ppm, then it can causes the hardening of the enamel. And if its concentration is increasing to 2 ppm, then it can result in brown mottling of the teeth. At the same time, if we have excess fluoride of over 10 ppm, then it can causes harmful effects to the bones as well as to the teeth, and this is reported in certain parts of Rajasthan. Let us now see about lead poisoning. Drinking water gets contaminated with lead when lead pipes are used for the transportation of water. So the amount of lead, the prescribed amount of lead is 50 ppb. This is important. And if it is exceeding this 50 ppb, what is happening? It can damage the kidney, it can damage liver, and also to the reproductive system. Now let us see the sulfate. Excessive sulfate, that is greater than 500 ppm in drinking water, can cause laxative effect. Otherwise, it is harmless. Moving on to nitrite. Nitrate has a limit of 50 ppm. Excess of nitrate can cause diseases such as methemoglobinemia, also known as blue baby syndrome, and this is also important. Now, other metals, maximum concentration of metals, which we have already discussed over here, this one, so this is also important. So let us now move on to the next, that is the soil pollution. Now, India is an agriculture-based economy, and green revolution has resulted in large amount of soil pollution as well. Although green evolution has increased in the yield of the plants, it has also led to a large amount of soil pollution because we have excess of pesticides, weedicides, and fungicides, which is contributing to this soil pollution. Prior to the World War II, many naturally occurring chemicals such as nicotine by planting tobacco plants in the crop field were used as pest controlling substances as the major crops. During World War II, what has happened? DDT was found out to be the major use for the control of malaria and also other disease causing microbes. Therefore, after the war, DDT was put in the agriculture to control the damage caused by the insects, rodents, weeds, and various crop diseases. However, due to adverse effect, it has been banned in India. And pesticides are basically synthetic toxic chemicals with ecological repercussions. The repeated use of the same or similar pesticides can give rise to pests that are resistant to those pesticides and can make these pesticides ineffective. Therefore, an insect resistant to DDT increased. Other organic toxins such as aldrin, dieldrin are introduced into the market by the pesticide industry. So now we can use aldrin and dieldrin. These are some organic toxins which are used in the pesticide industry. Most of the organic toxins are water insoluble. This is important, water insoluble, and they are non-biodegradable as well. The high persistent toxins are therefore transferred from the lower toxic level to the higher toxic level in the food chain, and this is known as biological magnification. This is known as biological magnification. At the molecular level, the toxicity is very less, but as we move to the higher trophic level, what is happening is that the toxicity increases. This is known as biological magnification, also known as biomagnification. Let us now talk about some important herbicides. The most important one is NaClO3, which is known as sodium chlorate. Similarly, we have sodium arsenite, These are some of the most commonly used herbicides. Now, what are herbicides? Herbicides are those which are used to kill the herbs which is living, or the weeds that is living in the fields, the unwanted plants, that is known as the weeds. Now, what happens is that most of these herbicides are toxic to the mammals and are not as persistent as organochlorides. So these chemicals decompose in a few months. Like the organochlorides, these two becomes concentrated in the food web. Some herbicides can cause us birth defects. Like we have the endosulfan, which can cause us birth defects. Studies shows that the cornfields sprayed with herbicides are more prone to insect attack and plant disease than fields that are weeded manually. So if we have weeds in the plant, that means the insect attack is less. But if we have no weeds, that is if we are adding herbicides, what is happening? The insects and other pests are acting. Though no more weeds are there, but now the insects and the pests, they are going to depend on the crop field alone, and as a result of which they are going to damage the crop field. So pesticides and herbicides, they are just going to represent a very small fraction of the widespread chemical pollution. A large number of other components that are used regularly in chemical and industrial processes for manufacturing activities are finally released into the atmosphere or into the water. Now let us move on to the industrial waste. Now when we talk about industrial waste, we can broadly classify them into two categories. The first one is known as non-biodegradable waste. Non-biodegradable waste are generated by thermal power plants which produce fly ash. Integrated iron and steel plants which produces blast furnace, slag and steel melting slag. Industries manufacturing aluminium, zinc and copper, they are going to produce mud and tailings. Fertilizing industries can produce as gypsum. Hazardous waste such as inflammables, composite explosives or highly reactive substances, these are produced by the industry, leading with metals, chemicals, drugs, pharmaceuticals, dyes, pesticides, rubber goods, etc. So these substances are not at all good, right? So if it is done by an improper manner, if it is disposed in an improper manner, what has happened is that it can result in pollution, and this is known as pollution by industries, also known as industrial waste or industrial pollution. So they have to be incinerated. The method in which these waste can be removed is incinerated, whereas small quantities of garbage, they can be either deposited in proper bins, but for solid waste, if not managed effectively, it affects the components of the environment. This is the important point. Now, waste recycling is what we are going to discuss next. Fuel that is obtained from plastic waste that has high octane rating. If it has high octane rating, what is going to happen? It contains no lead. That is the meaning. If octane, now these are available in India. Our cities and towns faced endless hours of power cut. We can also see piles of rotting garbage. There is a good news that we can get rid of both these problems simultaneously. Produce electricity from garbage. A pilot plant has been set up where removing plastic, glass, paper, etc. The garbage, it is used for producing methane, commonly known as biogas. Full thing, because you can convert garbage into electricity. Garbage is converted into electricity. So very see the strategies to control pollution. Now we were discussing about the types of pollution, and now the conclusion part, that is strategies to control environmental pollution. So after studying about the air, water, soil and industrial waste pollution in this unit, by now you must have started feeling the need of controlling environmental pollution. So let us see the methods. First one, we're going to talk about waste management. Solid waste is not only the waste which you see in your household garbage box. Besides the household discards, there are medical, agricultural, industrial and mining waste also. The improper disposal of the waste is one of the major causes of environmental degradation, and the management of these waste is of utmost importance. Now, collection and disposal. Now, we can keep separate waste bins, one for biodegradable and another for non-biodegradable, so that these two can be dumped separately, and as a result of which we can uh, cause the problem of soil pollution. We can pause the problem, or we can say check the problem of soil pollution, right? Therefore, all domestic waste should be properly collected and deposited. Poor management causes health problems leading to epidemics due to contamination of groundwater. It is especially hazardous for those who are in direct contact within the waste, such as the rag pickers and workers which is involved in the waste disposal, as they are the one who handle waste materials mostly without any protective devices such as gloves or waterproof boots and gas masks. So, to protect their health also, we have to be concerned, and we have to separate the waste into two. One waste bin should be kept for dumping the biodegradable, and another should be kept for non-biodegradable waste. Now, moving on to the last topic of this chapter, that is green chemistry. Now, in the late 20th century, by using fertilizers and pesticides, the amount of food that is produced in the country has been increased. But what has happened? There has been increasing soil pollution, there has been increasing water pollution, and also due to air pollution. So let us see how we can apply the concept of green chemistry to our day-to-day life. First one, dry cleaning of clothes. Tetrachloroethane, that is Cl2 C double bond CCl2, that was earlier used for the dry cleaning purposes. Tetrachloroethane. The compound contaminates the groundwater and is also a suspected carcinogen. The processes using this compound is now being replaced by a process where liquefied carbon dioxide with a suitable detergent is used. Replacement by the halogenated solvent by liquid carbon dioxide has resulted in less harm to the groundwater. So earlier we used chloroethane, and that is a pollutant, and now instead of that we are using liquid carbon dioxide, which is not at all a pollutant. Similarly, we can also use H2O2, that is hydrogen peroxide, in bleaching of clothes in the process of laundry, which can also gives us better results and also less polluting. And next one is in the bleaching of paper. Earlier chlorine gas was used, and that is a pollutant, and now we are using hydrogen peroxide with suitable catalyst which promotes the bleaching action of hydrogen peroxide. Next one is the further synthesis of chemicals. Ethanol is now commercially prepared by one-step oxidation of ethene in the presence of ionic catalyst in aqueous medium with a yield of 90%. So, similarly, we can say that green chemistry in a nutshell is a cost-effective approach which involves a reduction in material, energy consumption, and waste generation. So, it is helping in preventing, or we can say reducing, the pollution. So with this, we are completing the theory of this chapter. Now let us quickly check some important questions related to this particular chapter. Question number 1. The layer of atmosphere which extends up to 10 km from the sea level is called as troposphere. Troposphere pollutant it can contain dust, water vapor, and mist, so it should be all of these. Which one of the following is a secondary pollutant? Secondary pollutant means they have no direct contact with the atmosphere. Carbon monoxide has direct contact, so it is a primary pollutant. Ozone does not have a direct contact, but it convert the other compounds such as NO2. We have seen it is converted into NO3 minus, and this NO3 minus for more pollution. So this is a secondary pollutant. Lead and methane, on the other hand, these are primary pollutant. Next question, which of the following pollutant causes irritation in eye? This we have already studied. It is sulfur dioxide. Primary pollutant is CO is a primary pollutant, DDT is also a primary pollutant, and CO2 is also a primary pollutant. So the answer is option number 4. Let us move on to the next question. Which one of the following is a colorless, highly toxic gas which reduces oxygen carrying capacity? So by seeing this particular part, we can answer that it is carbon monoxide. Which one of the following affects chlorophyll? Now we have to study this. Exposure of plants to lower concentration of SO2 over longer periods hampers the production of chlorophyll. So the answer should be option number 1. Next question. Which of the following oxides produces brown or reddish brown haze? It is the oxides of nitrogen, especially NO2. Which one of the following gaseous pollutants is carcinogenic? We have arsenic, which is a carcinogenic substance. Next, photochemical smoke involves ozone, NO and NO2, so the answer is all of these. Select the viable pollutant. Viable means it is living. Smoke is not living, so this cannot be the answer. Mold is living, so this can be an answer. Mist is not living and fumes is also not living, so the answer is option number 2. Which of the following is not a property of classical smoke? It occurs at low temperature. Yes, classical smoke occurs at cool temperature. Secondary pollutants plays significant role. That is wrong. So this should be the answer. Photochemical smoke always contains ozone, so the answer should be 2. Depletion of ozone layer cannot cause. It cannot cause damage of DNA. Yes, it can cause damage of DNA. It can cause skin cancer. It can cause cataract, but it does not cause rickets because rickets is due to vitamin deficiency. Which of the following is known as a chemical weed in the troposphere? We know that the ozone in the troposphere is known as bad ozone, and that which is present in the stratosphere is the good ozone. Bad ozone is same as the chemical weed, so O3 is the answer. Depletion of ozone layer can causes increased transpiration, damages paints and fibers, this is also correct, causes aging of skin, that is also correct, so the answer is option number 4. pH of rainwater is 5.6 because of the presence of H plus ions that is formed by the reaction of water with carbon dioxide. Which of the following is not a cause of acid rain? CH4 is not helping in acid rain, whereas NO2, SO2 and CO2 has its contribution to acid rain. Acid rain causes chlorosis, increasing acidity of the soil, corroding of the bridges, so the answer should be all of these. Interference in the development and maturation of RBC is caused by, as we have already studied, it is lead pollution. Tooth decay is caused by the deficiency of fluorides. Cause of eutrophication is the natural or nutrient enrichment in the water bodies, especially due to nitrates and phosphates. Inorganic kidneys and the central nervous system, so the answer should be option number 4. Which one of the following is the least persistent insecticide? Least persistent is asked, so it should be carbamates. These two are highly persistent, even this is highly persistent, but this one is least persistent. And this we have studied in the previous chapter, benzene hexachloride, which is also known as gamaxine. Which one of the following is a herbicide? We have studied that the herbicides is sodium arsenite. Now the next question, in the place of tetrachloroethane in ethene in dry cleaning, we can use hydrogen peroxide and also liquid CO2 as well. Sharov won 2005 Nobel Prize for the development of metathesis method, which is a very important method in green chemistry. So with this chapter, and in the next video lecture we will be covering up the chapter haloalkanes and haloarenes. Please do not forget to like any important notifications and be a part of our Telegram app for the PDF of all these lectures and also every updates. So see you again in the next lecture. Till then, goodbye and happy learning. Hi everyone. Welcome to the Organic Chemistry Revision Lecture Series presented by Neetshala. In this lecture, we will be discussing the chapter haloalkanes and haloarenes. So let's get started with the chapter. The first part is about haloalkanes and haloarenes. We have to just deal with some nomenclature here. So if you look at the first compound, we can see it is CH3 thrice CBr. So if we look at its common name, it is going to be tert butyl bromide. The structure will looks like this: CH3C, CH3 and another CH3 is attached over here, and we have a Br attached. So this is a tert butyl bromide, and what happens is that on the second carbon we have a bromine and also we have a methyl group. So we can say it is 2-bromo 2-methyl propane. Now the next one is CH2 double bond CH CH2Br. Its common name is allyl bromide and its IUPAC name is 3-bromopropene. Now the next molecule, it is not an aryl chloride, rather it is a benzyl chloride, and its IUPAC name is going to be chlorophenyl methane. Now the next one is CH3 single bond CH Cl2. This is known as ethylidine chloride, which is IUPAC name is 1,1-dichloroethane. 2 chlorine is substituted on the same carbon. Now let us see the nature of the CX bond. Now if we take the CX bond, we know that the halogen is bearing a negative charge and the carbon is bearing a partial positive charge, as a result of which this bond is going to be a polar bond. It is a polar bond. Now what about the polarity of this bond? Since the size of the halogen atom is increasing as we move down the group, what happens is that the fluorine atom is the smallest atom and iodine atom is the largest atom. Consequently, there are certain effects on the bond length, there are certain effects on the bond dissociation enthalpy, and also on the dipole moment. So this is the table which is given in NCERT. From this we can expect questions like arrange the following in the increasing order of bond length, arrange the following in the increasing order of enthalpy, and also in the case of dipole moment. So let us take the first one, bond length. As we move down, the size of the halogen atom is increasing, and as a result of which the bond length of the carbon halogen bond is also increasing. So the order is CH3F is having the least, then it is increasing, and maximum is for CH3I. Now when we take bond enthalpy, we know that bond enthalpy is the inverse of bond length, so we get a decreasing order over here. Now let us talk about dipole moment. For dipole moment, there is a slight exception. Highest is for CH3Cl, as you can see over here, and then comes CH3F, then comes CH3Br, and last comes CH3I. Now let us move forward to the classification of haloalkenes and haloarenes. The first basis of classification on the basis of number of halogen atoms. The first one is monohaloalkane if we have a single halogen, dihaloalkane if we have two halogens attached, trihaloalkanes if we have three halogens attached. Similarly, we have monohaloarenes if we have one halogen attached onto the benzene ring. If there are two halogen atoms attached to the benzene ring, we have dihaloarene, and if we have three halogen atoms attached to the benzene ring, then it is known as trihaloarene. Let us now see another classification, that is compounds containing sp3x bond, sp2cx bond. So let us see the first one, that is vinylic halides. Now what are vinylic halides? Vinylic halides means if we have a carbon, double bond carbon, the halogen atoms is attached directly to the double bonded carbon. That is known as vinylic halides. Now what are aryl halides? Aryl halides means we are adding the halogen atoms directly onto the benzene ring. Then it is known as aryl halide. Now let us move on to the next one, that is allylic halide. Now what is allylic halide? If we have C double bond C, and if I am attaching a carbon onto this double bonded carbon, and if I am adding a halogen to this sp3 carbon, then it is known as allylic halide. Now what is benzylic halide? I have a benzene ring, and on the benzene ring I am going to arrange a carbon, and on this carbon I am going to arrange a halogen. So now this is known as an benzylic halide. Now we can also classify the alkyl halides into primary, secondary, and tertiary. This is on the basis of the carbon onto which it is attached. So as you can see over here, primary means we are attaching it to a primary carbon, secondary means we are attaching it to a secondary carbon, and tertiary means we are attaching it to a tertiary carbon. Now let us see the preparation of haloalkanes. First one is from alcohols. Now we have to understand that alkyl halides are best prepared. They are best prepared from alcohol. Now what is the reason for that? Because alcohols, as we know, is easily accessible. So here what is happening is that the hydroxyl group of an alcohol is replaced by halogen atom on reaction with concentrated halogen acids, or we can use phosphorus halides, or we can use thionyl chloride. So the most commonly used reagents for the conversion of alcohols into haloalkanes are concentrated halogen acids such as concentrated HCl, HBr, etc. Second is phosphorus halides, which is PX3 and PX5. And the last one is thionyl chloride, which is SO2Cl2. Now, thionyl chloride is the most preferred. What is the reason? Is because the byproducts that we are getting in the reaction, they are escapable gases. Hence, the reaction will give pure alkyl halides. Nearly 99% pure alkyl halides is obtained. So that is the best method of preparation from alcohols. Now, phosphorus tribromide and triiodide are usually generated in situ. That means it is produced in the reaction mixture by the reaction of red phosphorus with bromine and iodine respectively. So this is also important. Phosphorus tribromide and triiodide are generated in the container by the reaction of red phosphorus with bromine and iodine respectively. That is, P is going to react it with Br2 in the vessel to prepare the mixture. We are not taking PBr3. This is not taken directly, this is taken. Red phosphorus in the presence of halogen is taken. The preparation of alkyl chloride is carried out either by passing dry hydrogen chloride gas, or we can take a solution of alcohol and heat it in the presence of an concentrated aqueous acid. These are the two methods in which we can react it with the halogen acids. Now let us see the reactions related to this particular section. The first one is ROH plus HCl. So what is happening is that this OH group is substituted by Cl, but for this we need a reagent which is ZnCl2. Now this HCl and ZnCl2 together is known as Lucas reagent, and this test is known as Lucas test. Lucas test. This test can be used to distinguish between a primary, secondary and a tertiary. What is the reason for that? Because here we can see that the order of reactivity of alcohols with a given halo acid is tertiary greater than secondary greater than primary. That means tertiary is going to react maximum fast and primary is going to show minimum reactivity. So we can say that if it is reacting faster, we can say it is a tertiary alcohol, and if it is reacting very slow, then we can say it is a primary alcohol. So it can be used to distinguish between the tertiary, secondary and primary alcohol. Now the next reaction is ROH plus NaBr in the presence of H2SO4. So what is happening is that this Br is getting substituted in the place of the OH, and we get Na with this HSO4, and one molecule of H is removed, and that H is going to move with the OH to form H2O. So we get RBr, NaHSO4, and also we get water. Now we are taking 3 molecules of ROH and treating it with PX3. So the OH group from the alcohol is removed from the 3 molecules, and we are going to add halogen over there. So it is RX plus H3PO3. Now in the next reaction we have ROH plus PCl5. So this is how the reaction is going to happen. Just a short trick. We have PCl5. So let us take it as Cl3. There is another Cl and there is another Cl, just for convenience. Now we are going to take this R. I'm going to write the ROH like this, ROH, and one of the chlorine is going to be substituted on the R. Another chlorine is substituted on the hydrogen, and this oxygen is going to now get substituted to the phosphorus. So we get POCl3 as the product over here. So POCl3, RCl and HCl, these are the 3 products that we are getting in this particular reaction. Next, we are treating red phosphorus in the presence of halogen, which is used in the case of bromine and iodine to get RX. Now the next one is our OH plus SOCl2, which is known as thionyl chloride. Thionyl chloride. At this time what is happening is that SO2 gas is removed out and HCl gas is also removed out. We get the pure haloalkene. Now let us see some important theory portion given at the end of this paragraph, because this is also important. Presence of primary and secondary alcohols with HCl requires simple catalyst, that is ZnCl2. However, with tertiary alcohols, the reaction is conducted by simply shaking with a concentrated HCl at room temperature because it is very reactive. Constant boiling with HBr is used for the preparation of alkyl bromide. Good yields of Ri may be obtained by heating alcohols with sodium or potassium iodide. This is also important in 95% orthophosphoric acid. So the above methods are not applicable for the preparation of aryl halides because carbon-oxygen bond in phenols and that has a partial double bond character is difficult to break than a single bond. What does that mean? If we have a CX bond, this bond is easier to break. Whereas if I take a phenol, we have an OH group, or if it is an OH also, it is easy for us to break here. But here what happens, this bond is difficult to break because that is a double bond, right? It's a partial double bond and hence we cannot break it easily, and that is why these type of reactions which we have discussed so far will not be applicable in the case of aryl halide. Let us now talk about electrophilic substitution reaction. Now, what is electrophilic substitution reaction? This is for the preparation of haloarenes from benzene or benzene derivatives. So let us talk about the first one. We are going to treat it with X2 in the presence of Fe dark condition. So at this time what is happening is that we get ortho and para products because CH3 group, as we know, is a ortho para directing group. Since it is an ortho para directing group, to prepare a benzyl halide here, this is a this is an aryl halide. So to prepare an aryl halide, we can use this particular method. The condition is iron should be used in dark conditions and X2 should be used. Now, this ortho and para isomers, they can be easily separated. Reason is because they have a large difference in their melting point. Now, the reaction with iodine, as we have studied in the chapter hydrocarbons, they are reversible in nature and hence it will require certain oxidizing agents such as HNO3, HiO4, HgO also can be used here. So these are the reagents which we are using for carrying out the process of iodination. Fluoro compounds are not prepared by this particular method because they are highly reactive. This is important. They are highly reactive, and as a result of which we are not usually carrying out this particular method in the case of fluoroalkenes. Now we have Sandmeyer's reaction where we are starting with an aniline molecule. So we have an aniline. Benzene with an NH2 group is known as aniline. Now we are going to treat this with NaNO2 and HX. NaNO2, that is sodium nitrite, and HX at 273 to 278 Kelvin, that is 0 to 0.5, also we can say 0 to 5 degrees Celsius. 0 to 5 degrees Celsius is the temperature conditions which is required for this reaction. So when we are treating it 2 and HX, we are getting benzene diazonium halide. Now N2 with a positive, this is known as diazo group. So we have benzene diazonium halide formed over here. Since there is formation of a diazonium halide, we can say this is a diazotization reaction. So this is another important named reaction which is known as diazotization reaction. We have to understand the reagent and also the starting and the end product. We're starting with aniline and we are ending up in benzene diazonium chloride, and the reagent which is used is NaNO2 in the presence of HX at 0 to 5 degrees Celsius. Now let us take the second reaction. If we look at the second reaction, we can see it is benzene diazonium chloride. Now this benzene diazonium chloride is treated with Cu2X2, that is copper chloride, and we are getting an aryl halide from it. The X is getting substituted over here, the remaining part is removed, and N2 is also moving out. CuCl2 is also moving out and N2 is also moving out. We will be getting an aryl halide over there. This reaction is known as Sandmeyer's reaction. So this is another named reaction. So far we have studied about Lucas test. Second one which we discussed was diazotization. The third named reaction that we are discussing is the Sandmeyer's reaction. Now let us move on to the fourth reaction, which is this replacement of the diazonium group by iodine. It does not require the presence of cuprous halide. This is also an example for Sandmeyer's reaction where we are just taking the benzene diazonium salt and we are simply shaking it with Ki to get iodobenzene. Now let us move on to the next reaction, that is from alkenes. From alkenes we can prepare by the addition of hydrogen halides, and this we have already studied in the chapter hydrocarbons. We are adding this molecule. If it is symmetric molecule, we will add hydrogen to one side of the double bond and halogen to the other side of the double bond, whereas if we have unsymmetrical compounds, two rules come into play. One is known as Markovnikov's addition and the other is known as anti-Markovnikov's addition. Now another is we can prepare vicinal dibromide also if we are adding Br2 or X2 in general. So this we have already discussed in the chapter hydrocarbons. Now the next one is halogen exchange method. That means we are converting one alkyl halide into another alkyl halide. For example, if we have RCl or RBr, we can convert it into Ri, right? RCl or RBr can be converted into Ri by treating it with sodium iodide in the presence of dry ethyl acetone. This is known as Finkelstein reaction. So remember, Finkelstein, F, and the first letter is I, so it is used for the preparation of iodine, right? Iodobenzene or alkenes, right? So we can say it is Fi. Remember it as a trick, Fi. And now the next one, what is happening? The next reaction is known as Schwarz reaction. Now in Schwarz reaction we are taking an alkyl halide, that is bromide. Now this bromide is converted into a fluoride by treating it with AgF, that is silver fluoride. We are converting it into CH3F by using AgF. Instead of AgF we can also use a mixture of compounds. We can use many compounds such as AgF, HgF2, Hg2F2, COF2 or SbF3. These are also the compounds which can be used for carrying out the Schwarz reaction. Now what is the use of dry acetone in the first one, that is Finkelstein reaction? It will facilitate the forward reaction according to the Le Chatelier's principle. So this is also important. Now the next one is Hunts-Decker reaction. This is two reactions which is beyond NCERT. If we are using RCOOAg and we are treating it with Br2 in the presence of HNu, we will be getting RBr, CO2 and AgX. This is known as Hunts-Decker reaction. That is, we are preparing it from the silver salt. Now if I am treating the silver salt with iodine in the presence of HNu, I will be getting an ester, RCOOR and AgI and CO2. So this reaction is applicable only for bromination, not for iodination, because iodination will give us ester. So this reaction is known as Bimbaum-Simony reaction. Now let us move on to the physical properties. The first one is melting and boiling point. We have a graph mentioned in NCERT which explains this melting and boiling point concept. So let us go through this graph. Now what is this graph stating? We have CH3X here, CH3CH2X, CH3CH2CH2X. First is the chloride, the red one is the chloride. Now bromide comes next and iodide comes next. So let us take it one by one. So if I am taking the first one, we can say that here it is increasing, right? The red one, that is increasing, and this is the boiling point. So the boiling point is increasing when the number of carbon atom is increasing. Similarly, when we take bromides also, the same trend is observed, and in the case of iodides also the same trend is observed. So we can say that as we increase the number of carbons, what happens to the boiling point? The boiling point also will increase. So this is the first important conclusion. And when branching is present, boiling point decreases, same as in the case of hydrocarbons chapter. Now, boiling point of isomeric dihalobenzenes are nearly the same. However, the para isomers are high melting as compared to their ortho and meta isomers. What is the reason for this? This is because of their symmetry of the para isomers, as a result of which their better fitting of the crystal lattice as compared to ortho and meta. So as you can see over here, this is the perfect fitting because their crystal lattice will be in an orderly manner, and whenever we have something in order, breaking the bond and boiling it is difficult, and that is why this is having the maximum boiling point and maximum melting point as compared to the ortho and para isomers. Let us now talk about density. Bromo, iodo, and polychloro derivatives of hydrocarbons, they are heavier than water. This is important. And as we move down the group, that is CH3Cl, next one is CH3CH2Cl. So if you're moving like that, we can see that with increase in the number of carbon atoms, with increase in number of halogen atoms, and also if there is a increase in the atomic mass, then what can be observed? We can observe that the density also increases, because density, as we know, is mass by volume. So mass is increasing, so we can say that the density is also correspondingly increasing. Now the next one is solubility. Haloalkanes are only slightly soluble in water. So if it have to be soluble in water, what happens is that the energy is required to overcome the attractions between the haloalkane molecule, and it also have to break the hydrogen bonds in between the water molecules. So less energy is released when new attractions are set up between the haloalkane and the water molecules, and these are not as strong as the original halogen bonds and hydrogen bonds in water. So the energy difference is not that much high, and as a result of which they cannot break the bond, and as a result of which the haloalkanes have a very poor solubility. So next topic is the reactions of haloalkanes. This we will be covering up in the next lecture. So till then, goodbye and happy learning. Now in nucleophilic substitution, what is happening is that we have a nucleophile. This nucleophile is reacting with the a negative charge. So that compound having from the carbon. There is a substitution of the nucleus. The halogen atom is moving out as a leaving group. So since there is a substitution of a nucleophile, this type of reactions is known as nucleophilic substitution reaction. And this is one of the most important classes of organic reactions of alkyl halides, in which halogen is bonded to sp3 hybridized carbon. So let us see some of the common for nucleophilic substitution. General nucleophilic reaction is Rx plus Nu giving Rnu plus X. So here we can see, if we are taking NaOH as a reagent, what will be the negative part in that? It is going to be OH minus. So we will substitute in the compound, so we get ROH as the product. Now if we are taking water as the reagent, we can say that the nucleophile is water because it has bond pairs present on it, and again we get ROH over here. Now NaOR minus, so there we will be getting OR minus or OR dash minus. So there the OR group is going to substitute with the R group, so we are getting ROR. Now the next one is NaI. So there the negative part is I minus, so that is getting substituted to the alkyl halide, so it is R. Minus is going and substituting over there to give us RNH2. Now let us take the next set, R dash NH. So there also the same thing is going to happen. The H plus is going to move out and the remaining part is the negative part, so that is going to get substituted over there. Now KCN, this is an important part, very important part from here. KCN, AgCN, KNO2 and AgNO2. So here we can say, if we have KCN, then the nucleophile is CN and it is getting substituted as RCN. Whereas if we take AgCN, again the nucleophile is RCN, but now the part is NC minus. In A and in KCN it is CN minus. So this type of compounds where both the atoms have equal chances of giving rise to a negative charge, this is known as ambidentate nucleophiles or ambident nucleophiles. So here what is happening, we get RNC, that is isocyanide over here, and if we have KNO2, it is going to give us RONO and AgNO2 is going to substitute to give RNO2. So this is the important part over here, and another important one is regarding LiAlH4. It is a good hydrogen providing agent, as a result of which we get RH over here. So let us see the reaction, let us see about ambidentate nucleophiles here. Ambident nucleophiles. Groups like cyanides and nitrides, they possess nucleophilic centers. If we take cyanide, we have carbon and nitrogen as the nucleophilic center. Two contributing structures cyanide ion. Linking through the carbon atom can result in the formation of alkyl cyanides, and through nitrogen atom can lead to isocyanides. Similarly, the nitride ion is also representing a ambidentate nucleophile with two different points of linkage. We have oxygen as one linking atom, and also we have nitrogen as another linking atom. So this is about ambidentate nucleophiles, and this is a example which is given in Ncert, which is asking haloalkanes reacts with KCN to form alkyl cyanides as the main product, while AgCN forms isocyanides as the chief product. What is the reason? KCN is ionic, and as a result they are producing cyanide ions in the solution, whereas AgCN is covalent and carbon Ag is forming a bond. So the nitrogen is free to donate the electron pair, and as a result of which it is going to form. So now let us see the general pathway, or we can say the reactivity order of nucleophilic reaction. We have two types of nucleophilic reaction. One is known as SN1 reaction and another is known as SN2 reaction. SN1 reaction means it is unimolecular reaction, and SN2 means it is bimolecular reaction. We will be discussing about all the types of reactions, what is electrophilic substitution, what is nucleophilic substitution, etc. in the end in a separate video. So the stereochemical aspects of this chapter, that is the nucleophilic substitution reaction, will be taken up in that particular video, so that we can have this chapter as a small chapter and easy to learn all the reactions together. So for the time being, we have to understand these two orders. For SN2 reaction, remember it is a bigger reaction, right? SN2 reaction is somewhat a bigger reaction, and there the order is primary greater than, secondary greater than, tertiary. Primary greater than, secondary greater than, tertiary. And for SN1 reaction, the order is going to be tertiary greater than, secondary greater than, primary. So these two orders are important, and another important order is given over here for alkyl halides. This is the order for both SN1 and SN2. This is the order. Ri is having the maximum reactivity towards any of the nucleophilic substitution reaction, followed by RBr, followed by RCl, and least is for RF. So this is also important. So these three orders are important from this section. So here we have a question based on that. In which of the following pairs of halogen compounds which would undergo SN2 reaction faster? Each of the following pairs we have to find which of these is undergoing SN2 reaction faster. So the first one, we can see it is a primary and this is a secondary. So we have already studied that primary will undergo SN2 reaction faster, so this should go faster. Now the next one, we have iodine and chlorine, so iodine will go faster. Now let us move on to the second type of reaction, that is known as elimination reaction. And here what is happening is we are having beta elimination. We have already studied about what is beta elimination. And here we have to study a rule which is known as Zaitsev rule. So let us see what is Zaitsev rule. In dehydrogenation dehydrohalogenation reactions, the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. Now what does that mean? On which side of the double bond are we having maximum number of alkyl groups? That is going to be the major product. So if I take over here, we can see 2 on the right side and 3 on the left side, and here we can see 1 on the right side and 4. So this is lesser, right? So since this is lesser and this is more balanced, Here it is like more balanced, but here it is less balanced on the either side. So this is going to be the major product and this is going to be the minor product. So that is what is known as Zaitsev rule. We have to balance it, right? Having almost equal number of methyl groups substituted on both sides, then we can say it is the major product. So this is known as Zaitsev rule. Now the next one is reaction with metals. Now here we have to talk about Grignard reagent. Now first of all we have CH3CH2Br. This is reacting with magnesium in the presence of dry ether to give us CH3CH2CH MgBr. This is known as Grignard reagent whose general formula is RMgX. Now this RMgX, in this the positive charge goes to the magnesium, negative charge go to R and X. When we are hydrolyzing RMgX, we will be getting an alkane and also we get MgOH. So we have to keep it in moisture free environment. The reason being it reacts readily with water and as a result of which we get alkanes and this particular product. Now when does this particular Grignard reagent react? Grignard reagent reacts when there is presence of active hydrogen. That is when there is presence of acidic hydrogen. If we have water, we can say we have H plus and OH minus, and this H plus is known as an acidic hydrogen and this can react with the Grignard reagent. So this is Grignard reagent R, Mg and X. So what is happening is that this positive charge, this is having the negative charge, right? So this part is going to go with the negative part, that is MgOH, and this is also having a negative part, so this is moving out as MgOHX, and to the negative side we are going to add the positive charge, so it is going to be RH over here. Now if I take another example, if we have amines RMgX plus NH2, we can take RNH2. So it is R plus NH2 minus. So this is the positive side and this is the negative side. So these two are going to react. We get RR dash and we get MgNH2X. So these are products that we are getting over here. Now let us move on to the last reaction over here. This is known as Wood's reaction. Alkyl halide reacts with sodium in dry ether to give us hydrocarbons which is having double the number of carbon atoms, and this is known as Wood's reaction. We have studied lots of things regarding Wood's reaction in the chapter of hydrocarbons. So comment below what are the abnormal products of Wood's reaction. Comment below what are the abnormal products of Wood reaction, and also you have to comment what is the intermediate. What is the intermediate of Wood's reaction, or what is the pathway of Wood's reaction? Is it electrophilic, is it free radical, or is it any other mechanism? This also you have to comment below. Now let us see the reactions of haloarenes. The first one is nucleophilic substitution. Aryl halides are extremely rare, or we can say less reactive towards nucleophilic substitution reaction. First reason is because of the partial double bond character, that is due to resonance effect. Second one is the difference in hybridization of the carbon atom. Here we have sp2 hybridized carbon, whereas if we take a haloalkane, that is going to be sp3 hybrid carbon. So we have difference in the hybridization, that can also be a reason. Third important reason is the inability of the phenyl cation, and the last important reason is because of steric hindrance, or we can say steric repulsion. Now let us see the first reaction, where we are going to react this compound with NaOH in the presence of H plus at 623 Kelvin and 300 atmosphere. So then what is going to happen, this Cl is removed out at this particular condition only, not simply by shaking. So this will be giving OH over here and we get a phenol here. Now let us see what is the effect of adding or substituting the different positions. So here we have an para substituted, and here we have an ortho and para, and here we have all the ortho and para, one ortho and para, and here we can see both ortho and para position is substituted. So here what is going to happen, this is a electron withdrawing group, NO2. So electron withdrawing group is occupied at the ortho and the para position, and this is going to increase the reactivity of haloarenes. So here we can say 443 Kelvin was needed for substituting this OH, but now 2 NO2 are there, so reactivity is increased further, and as a result of which lesser temperature is needed. And if we are taking 3 NO2 groups at ortho and para positions, then what is going to happen? We just have to take the warm solution and just shake it well to get the product, because that is maximum reactive among these three. So they can ask the order of reactivity as well, so this is important. Now let us move on to the electrophilic substitution reaction. The first one is known as halogenation. Now in halogenation, we have already studied in the hydrocarbons chapter that the reagent used is Cl2 in the presence of anhydrous FeCl3. So we will be getting an ortho product and para product and also an ortho product. Always remember, para is the major product. Para is always the major product. Now for nitration, we are taking HNO3 in the presence of concentrated H2SO4. We will be getting ortho as the minor product and para as the major product. In sulfonation, we are taking concentrated H2SO4, or even we can use oleum. So we will be getting minor product as the ortho product and para product is the major product. Now in Friedel-Crafts alkylation reaction, we are taking CH3Cl in the presence of anhydrous AlCl3 to get ortho and para products. And in the case of acylation, we are taking this compound, that is acyl chloride, in the presence of anhydrous AlCl3 to get a minor ortho product and a major para product. Let us move on to the last reaction of haloarenes, which is reaction with metals. Now the first reaction is known as Wurtz-Fittig reaction, where we are taking one molecule of an aryl halide and one molecule of an alkyl halide and treating it with sodium in the presence of ether. In this particular reaction, we will be getting this particular compound, because we have taken one aryl halide and we have taken 2 molecules of sodium, and we have also taken an alkyl halide. So this much part is moving out and this R is getting substituted over here. So we will be getting this as our major product. Now let us move on to Fittig reaction. Fittig reaction is also similar to the Wurtz reaction. Here what is happening, instead of Rx we are taking ARX, that is aryl halide. So when we take 2 molecules of aryl halide, this is first molecule, we have 2 molecules of sodium and we have another molecule of aryl halide. So when we are taking another molecule, this much part is moving out as 2NaX, and these two are going to join together to form diphenyl. So this completes the theory of this chapter. Now let us discuss some of the important questions related to this particular section. So let us start with the first question. Which of the following reactions is an example for nucleophilic substitution reaction? So we have already seen this in the table. So this is the example for nucleophilic substitution reaction. Let us see the second one. What products are formed when the following compounds are treated with Br2 in the presence of FeBr2? So here we can see we have 2 CH2 groups here. So with respect to CH3, we have to find which is the ortho and para directing groups. So here we can say this bromine is ortho with respect to this and ortho with respect to this, but this is para with respect to this, but we do not have a para with respect to this. So this cannot be the answer. Now this is para with respect to this, but this is ortho with respect to this. So one is ortho and one is para, and with respect to this we have an ortho here, and with respect to this also it is ortho. So that is not possible. We should get both ortho and para. So here what is happening, with respect to this is ortho, and with respect to this is para, and with respect to this is going to be para position, and to this is going to be ortho position. So both are ortho para and ortho para. So this should be the answer. Which of the following biphenyl is optically active? Now due to steric hindrance arising due to the presence of bulkier groups at the ortho positions, the biphenyl system is always non-planar, that is it is optically active. So this should be the answer. Now we have to say, when is this particular reaction fastest? So if you could recall the SN1 and SN2 reaction, this is an example for SN2 reaction. And if you don't know, we will be discussing this section in a separate video where we will discuss about the different types of organic reactions. So this is an SN2 reaction, and the condition for SN2 reaction is that it should be in a polar aprotic solvent, that is NN dimethyl formamide. Next, which of the following is a secondary alkyl halide? So if we take, this is a primary, this is also primary, this is also a primary, so this should be the secondary one. Which of the following may be classified as an aryl halide? Aryl halide is that onto which the chlorine is attached directly to the benzene ring, and so this is the answer. Which of the following is correct for the reaction? We have HBr in the presence of peroxide. Since we have peroxide, it is going to be anti-Markovnikov's addition. Now the next one is we have CH3 in the presence of Cl2 and H nu. We are getting P. We have to find what is the product P. Now we are getting 3 as the answer because it is CH3 present over here. So we have to substitute one of the hydrogen with a chlorine. Now here we have to treat this molecule with Br2 in the presence of H nu. So here also we can follow the same method, but here there is a problem. We have a free radical pathway, so we have to create a free radical, that is this. So onto this free radical we have to substitute the bromine, and as a result of which we are getting this as the answer. So the answer is option number 3. Which of the following is the most stable? Here you can see this is a conjugated system. What is conjugated? We have a double bond followed by a single bond. So this is known as a conjugated system. Double bond, single bond, double bond, single bond. This is known as a conjugated system. And in conjugated free radicals we have resonance, and resonance stabilization make this as the most stable among all the options. Now let us see the next question. C6H5CH3 in the presence of Br2 and FeBr3. This is an example for electrophilic reaction which we have already studied. Now this question we have to react it with KOH. So what is happening? We have to substitute it with OH, but this is an example for SN2, and in SN2 there is inversion of configuration, as a result of which its structure is changing. So this is SN2. Next, CH3 thrice Br is treated with KOH. So at that time we are having beta elimination. Bromine will go from this carbon and hydrogen is going to go from the next carbon, that is here. So there is a double bond formed over here. So this is the compound that we're getting, and now we have to carry out the anti-Markovnikov's addition because R2O2 is an organic peroxide. R2O2 is an organic peroxide, so we have to carry out anti-Markovnikov's addition, and after anti-Markovnikov's addition the bromine is substituted. This is deficit in hydrogen, that is we are getting this particular product. Sorry, bromine is added to that part which is excess in hydrogen, so this is the product. And in Markovnikov's addition, if there was no organic peroxide, we will be adding bromine to that part which is having lesser number of hydrogen atoms. And now let us move on to the last question of today's lecture. This is the question. We have to treat this alcohol with SOCl2, so we will be getting chlorine substituted in the place of OH, that is this, and now we have to treat it with KCN. So Cn will be substituted in the place of chlorine, and because it is SN2 mechanism, and after that what is happening, we are going to treat it with H plus, and that time we are going to get an acid, that is CH2COOH. So the answer is option number 3. So with this we are concluding the chapter halo. In the next lecture we will be discussing the chapter alcohols, phenols and ethers. So see you again in the next lecture. Till then, goodbye and happy learning. Hi everyone, welcome to the Organic Chemistry Revision Lecture Series presented by Neetshala. In this lecture we will be discussing the chapter alcohols, phenols and ethers. This chapter will be taken up in 2 lectures. In the first part we will be discussing about the preparation and physical properties of alcohols, phenols and ethers. So let's get started. The first topic that we have to discuss over here is the structures of the functional groups. So if I take the functional groups, we have ROH, that is alcohol. So we have ROH. Second one is AROH, that is phenol, and then we have ROR. So the most important question that we can get related to the functional group is the bond angle comparison. Now the bond angle will be minimum for alcohol. The reason is because we have R, O and H, and this oxygen has 2 lone pair. And because of this 2 lone pair, there is repulsion between the lone pair, and as a result of which this bond angle is reduced to nearly 108 degree. Whereas if I talk about AROH, what is happening? This is a little more bulkier group, and here the hybridization is sp2, the carbon onto which the oxygen atom is attached, that is sp2 hybridized, and as a result of which the bond angle is slightly higher to be nearly, as you can see over here, it is 109 degree. Now if I take the next molecule, that is ether, so if I take an ether, we can see that the bond angle is little more greater, and that is coming out to be 117 degree. So the bond angle will be in the order ROH, next will be AROH, and the last will be ROR. So this is important from this particular section. And in all these cases, we can see all the alcohols have an sp3 hybridized carbon attached to an sp3 hybridized oxygen. This is important. And also we have in ethers, we have one oxygen is bonded to two sp3 hybridized carbon. Whereas if I talk about phenol, we have the oxygen attached to the sp2 hybridized carbon. Now, let us talk about the preparation of alcohols. We can prepare alcohols from a variety of compounds. The first compound is alkene. So, how do we prepare alcohols from alkene? We have a compound like this. We have CH3, CH2, OH. So, I am going to write it as CH2 and an H here. So, this H and OH, if I am removing, then I will be getting an alkene, right? This is what we have studied over there. Now we have to do the reverse reaction. What is that? CH2 double bond CH2 we are having, and we have to convert it into CH3 CH2 OH. For that I can add a hydrogen onto this side, and I can add an OH to this side. That is, we have to carry out the addition of water. Now, addition of water cannot happen simply. We need a catalyst. So, we are taking H plus ions, or we can take any acid like HCl or H2SO4, etc. as the catalyst. So, this is known as acid catalyzed hydration because we are adding a molecule of water. H is going to one side of the double bond and OH is moving on to the other side of the double bond. So, we can say it is addition of water in the presence of an acid as a catalyst. Now, which rule is followed over here? We have studied two rules. One is Markovnikov's rule and the other is anti-Markovnikov's rule. Remember that whenever we have water, we are following Markovnikov's rule and not anti-Markovnikov's rule. But if they have given R2O2 or H2O2 or benzoyl peroxide in the arrow, then we have to use anti-Markovnikov's addition. So in the case of symmetrical alkanes, it is not a problem. We can simply add hydrogen to one side and OH to the other side. But in the case of unsymmetrical, like this, in the case of unsymmetrical, what we should do, we have to make the poor more poorer by adding the bulkier group onto that side. That means wherever the hydrogen is less, that is known as the poor side, and onto the poor side we are going to deposit all the bulky groups. So the OH will come over here and the H will come over here because this is a lighter group. Now let us see the next reaction, that is hydroboration oxidation reaction. Process hydroboration oxidation, we are going to add diborane. Now diborane, as you remember, is B2H6, or I can write it as BH3 twice, right? Or I can also say it as BH2H twice. This is another form of representing the same molecule. So we are going to add B2H6 onto this molecule according to anti-Markovnikov's addition. So first step, what is going to happen? We are going to add this molecule. So the hydrogen will go to that side which has lesser number of hydrogen because anti-Markovnikov's addition is followed over here. So we will be getting this particular molecule CH3, CH2, and here we have a CH2 and a BH2 is attached over there. Now this is reacted with a molecule of the same alkene, and as a result of which we will be getting this molecule here, and we have to treat it again with alkene. So remember, here we have two times of the same molecule. So if I am treating that again with the same alkene, we will be getting 3 times the same molecule, and the maximum covalency of boron is also satisfied. Now we have to treat it with H2O2 in the presence of water and a base. Base is also required, and in the presence of this things, it is getting converted into alcohol. Again, it is anti-Markovnikov's addition. In the last step also, it is anti-Markovnikov's addition. And the byproduct which we are getting over there is orthoboric acid. So this is known as hydroboration oxidation reaction. So we started with a 3 carbon containing alkene, and we are getting a 3 carbon containing alcohol. So this is what is known as hydroboration oxidation. We are getting corresponding alcohol by treating with B2H6, H2O and H2O2. Let us now move forward. This is a paragraph which is given at the end of that hydroboration oxidation. Let's just quickly go through this. Addition of borane to the double bond takes place in such a manner that the boron atoms get attached to the sp2 carbon carrying greater number of hydrogen atoms. So that is known as anti-Markovnikov's addition. The alcohol so formed looks as if it has been formed by the addition of water to the alkene in the same way opposite to the Markovnikov's rule. In this reaction, alcohol is obtained in excellent yield. So this is important. It is against the Markovnikov's rule, or we can say it is anti-Markovnikov's rule. Now let us see how we can prepare from carbonyl compounds. Now this is a very important paragraph. We can get theory questions as well, and also critical thinking questions from here. So let us read this carefully. By the reduction of aldehydes and ketones, we can obtain alcohols. Now, aldehydes and ketones are reduced to corresponding alcohols by different methods. First method is addition of hydrogen in the presence of catalysts. What are the catalysts? We have platinum, palladium, or nickel. These are finely divided catalysts, and in the presence of these catalysts, we are carrying out the process of hydrogenation. That is, this is the reaction, right? We are treating it with H2, and when we are treating it with H2, what is going to happen? This oxygen is now going to break its double bond, and it is going to form a single bond, and to the other side of the carbon, we will be getting a, because we have a molecule like this, right? CH and a double bond O. So now this bond is breaking. Onto this side one hydrogen will come and attach. Onto this side also one hydrogen will come and attach. So we are getting RCH2OH. This is hydrogenation, addition of hydrogen. It is an addition reaction. For carrying out this reaction, the catalysts are important: platinum, palladium and nickel. These should be finely divided catalysts so that maximum surface area is there and the reaction can be carried out easily. Now we have some reagents here. That is second method of preparation. We can use some reducing agents such as NaBH4 and LiAlH4. This is very important. NaBH4 and LiAlH4. These can be used for carrying out these conversions. If we have an aldehyde, aldehyde will give us primary alcohols, whereas ketones will give us secondary alcohols. Now, how is that happening? Why are we not getting any primary alcohol from ketone? If I look at the structure of ketone, we have, this is the structure, right? So when we are carrying out the process of reduction, what is happening is that hydrogen is getting added to these two sides. So one hydrogen will come over here, this hydrogen will come over here. So we are getting a compound like this. This is the compound that we're getting, and that is a secondary alcohol. Whereas if it was an aldehyde, we will write an H here, and here also we will write an H. So this is nothing but RCH2OH. This is RCH2OH, that is a primary alcohol. Now let us talk about the next method of preparation, which is from carboxylic acids and also from esters. Now as you can see that carboxylic acids and esters, they are having a double bond, double oxygen. Two oxygens are there. One oxygen is double bonded to carbon and another is single bonded to carbon. So here what is happening, we have to use a little more stronger reducing agent, and the reagent which is used over here is lithium aluminium hydride, LiAlH4. Lithium aluminium hydride. It can also write it as LaH, lithium aluminium hydride. So here what is happening, we are treating the acid RCOOH in the presence of LiAlH4. We are getting RCH2OH. That is, one oxygen is getting broken. This bond is getting broken. This oxygen is removed, and in the place of that oxygen we are just putting hydrogen. Oxygen is having a valency of 2, so we will just put 2 hydrogen over there, so we are getting RCH2OH. It's a very simple process. This is the trick to do this questions. Now here we can see that there is a limitation for this reaction. So let us see what is the limitation for this reaction. The major limitation is that LiAlS4 is a very expensive reagent, and as a result of which it can be used for preparing special chemicals only. However, if we have to prepare it commercially, acids are first reduced to alcohols by converting them into esters. So first we are going to convert them into esters. How can we create esters? That we will study in the next lecture. For the time being, just understand a little bit basics of esterification. We are treating a carboxylic acid with an alcohol. Carboxylic acid is treated with an alcohol. So what is happening is that one hydrogen will go from here and an OH is going to go from here, and the remaining part is joined. We will be getting RCOOR dash. This is an ester. Now this ester is treated with hydrogen in the presence of a catalyst. We are getting RCH2OH and R dash OH. That is, the bond cleavage is going to happen like this, and this part is going to give rise to the alcohol, and this part is going to give rise to the another alcohol. So we get 2 alcohols over here. Let us now move on to the most interesting compound, that is Grignard reagent. Now, there is a method for learning this Grignard reagent. If you learn the general mechanism, then it is very easy. If you learn this pathway, then for any compound you can attend the questions easily. So I will tell you a simple trick for that. We have carbon double bond oxygen. Here we have one group, here we have another group. We are not specifying here right now. We are going to treat it with RMgX. This RMgX is an organometallic compound, and this organometallic compound is known as Grignard reagent. Now what are we going to do? Here the oxygen is not a good fellow. He is not at all a good fellow. So let us use an emoji here. Okay, let us use this emoji here for oxygen. Now why I have put this emoji is because this person wants all the electrons from the double bond. So he is going to take all the electrons from the double bond. Now what is the condition of our carbon? Carbon is very caring and he is ready to give the electrons, but not willingly. Now the carbon will start crying because it has lost its electron, it has lost all its wealth. So it will start crying and the carbon will be like this, right? So now we have another caring person over here, and that is our R group in the organometallic compound. So what he will say, let us put a suitable emoji for this as well. Let us give this one. He is ready to help everyone. Okay, and this part is a very cunning fellow. He will say, the R group will say, don't worry carbon beta, I will give you electrons. So now this R group is going to donate the electrons to the carbon, as a result of which there is a formation of bond between the carbon and R group. So what is happening? I will just make the arrangement here. We have a carbon and the R group is attached. Now we have a single bond oxygen, and now as soon as this R is ready to give the electrons, this much part will say, if you donate any electrons to carbon, then we will go away. Okay, so these are also very greedy people because this R is rich in electrons, so these people also will get the benefit of this, right? So now when R is no more, they will not get the benefit. So as a result of which they will tell, we are going to leave you people. So they are very cunning fellow. So let us use another emoji here. We can use this. They are very cunning fellow. Now what is happening is that all the cunning fellows, that is this and this and this, will join together, and as a result of which we have OMgX. This is an intermediate compound. This is an intermediate compound. Also, we can call it as an adduct. Now, to this adduct, we are going to add water. So, when we are adding water, what is happening? The H plus is going to add on this side, and the OH is going to add on this side. Why am I adding it like this? Why not the opposite? I will tell you. Water, as you know, is having a formula H plus OH minus. Now, if this bond is cleaving, this person will be having a delta positive charge and this is having a delta negative charge. So the negative charged species will form a bond with the positively charged species, and the positively charged species will form a bond with the negatively charged species. And as a result of which, this much part is going to move out as MgOHX, and this much part is going to form an alcohol. Now look at the alcohol that is formed over here. The alcohol that is formed over here is something like this. Right? This is what we are having. This is the alcohol that we are having. Now imagine I have an R group here. I have another R group here. I will be getting a tertiary alcohol. Now if both are R groups, then it should be a ketone. So ketone will give rise to a tertiary alcohol. Now if I have an aldehyde here, a general aldehyde here, then I will be getting, we have onto this carbon two alkyl groups are attached. So this is going to be, sorry, this is OH, right? This is OH. So what is happening is that we have a secondary alcohol. So secondary alcohol is given by aldehyde, any aldehyde. But if we need to get primary aldehyde, we have to use a specific aldehyde, and that is methanol. Methanol is going to give us primary alcohol. So this is important. So let us just quickly recap what has happened. The thing that has happened is we have this oxygen, very greedy person, and he is going to take away all the electrons from the double bond, and as a result of which the carbon is deficit in electrons. So the sharing person, that is the R, is going to donate the electrons to the carbon, and due to this donation, now there is a bond that is formed between, they are having good friendship in between them, and as a result of which they are going to have a friendship between carbon and the R group. So now the greedy people, that is MgX group, that is going to come and attach to the oxygen atom, and as a result of which we get an adduct. Now to this adduct we will add water molecule. We are going to add water molecule, and when we are adding water molecule, the negatively charged part, that is OH minus, is the negatively charged part, that is OH, is going to attach to the magnesium, and the positively charged part, that is hydrogen, is getting added to the O. As a result, we will be getting an alcohol. Now if we are using a primary alcohol, if we need a primary alcohol, we have to use methanol. If we need a secondary alcohol, then we must use any other aldehyde, and if we need a tertiary alcohol, then we will be using a ketone. So this is the important point. And now this is a point which is given in NCERT in the side, so this is important. This is a quick recap. Reaction of Grignard reagent with methanol produces a primary alcohol, with other aldehyde secondary alcohol, and with ketones we get tertiary alcohols. We have a question here. Give the structures and IUPAC names of the products expected from the following reactions. Question number 1, catalytic reduction of butanol. So when we are carrying out the catalytic reduction of butanol, let's just draw the structure of butanol first of all. We have CH3, CH2, CH2, CH double bond O. So this bond is cleaved. Hydrogen will come to this side and hydrogen also will come to this side, and as a result of which we are getting butan 1-ol. Now let us look at the next question. Hydration of propene in the presence of dilute sulfuric acid. If you remember, this is a acid catalyzed hydration, and as a result of which it is addition of water in accordance with Markovnikov's rule. So first let us make the structure of propene. CH3, CH double bond CH2. We have to add water. This is the deficit side. To the deficit side we are going to add OH. To the rich side we will add the hydrogen. Double bond is broken. we will be getting CH3, CH-OH, CH3, that is propan 2-ol. Let us now discuss the next question. Reaction of propanone. Propanone means it is a ketone. This is treated with magnesium methyl bromide followed by hydrolysis. So propanone means we have CH3, CH3 double bond O, and we have CH3 MgX. So this is going over here, and the CH3 group is going to attach over here. Then this MgX is going to attach on the oxygen. Hydrolysis will give us MgOHX, and whatever is left over here, if we are joining, we will be getting a tertiary alcohol, and the tertiary alcohol will have the formula CH3 thrice COH, and that is 2-methyl propan 2-ol. Let us now move on to the physical properties of alcohols. So before that, we will just look at the preparation of phenols, and after that we will come to the physical properties. Now there are 4 methods of preparation of phenols which is discussed in NCERT, so we will stick on these 4. The first one is from haloarenes, which we have already discussed in the previous chapter. We are taking chlorobenzene, and this chlorobenzene is treated with NaOH at 623 Kelvin, 300 atmosphere. What is happening is that this NaO group is going to substitute over here, and the chlorine is moving with the hydrogen as HCl. Now this molecule is reacting with the HCl that is present in the solution, and as a result of which, what is going to happen, the Na is moving out with the Cl to form NaCl, and the hydrogen is substituted over there to get OH. So this is phenol. Very simple reaction. Second reaction is we are taking benzene and we are going to treat it with oleum. We are getting SO3H. This process is known as sulfonation, and now this benzene sulfonic acid is treated with NaOH in the presence of H+. So what is happening is we get the OH substituted over here and we get the phenol again. Let us now move on to the next one, that is from diazonium salt. In the last chapter, we have discussed what is diazotization. So by the process of diazotization, aniline, that is benzene with NH2, is converted into benzene diazonium chloride, that is N2Cl. Now that is treated with warm water will give us phenol along with byproducts, that is N2 and HCl. Let us now talk about the last method, which is the most famous or the most worldwide method of preparation of phenol, that is from cumene. Now what is cumene? Cumene is basically isopropyl benzene. Isopropyl benzene is known as cumene. That means we have a benzene ring, and onto the benzene ring we have a carbon. Onto this carbon we have 2 methyl groups. So this is known as isopropyl group. Isopropyl group attached to the benzene. That's why propyl benzene, or its common name is cumene. First, we are going to carry out the oxidation of cumene. When we are carrying out the oxidation of cumene to this carbon, to this particular carbon, we are going to add 2 oxygen atoms. As a result of which, we get cumene hydroperoxide, that is this. And now what are we going to do is we need this OH group. So we are going to remove the remaining part, and that is going to move out as CH3COCH3, and we are left with a phenol here. So these are the different methods of preparation of phenol. Now let us see the physical properties of alcohols and phenols. The first physical property is boiling point. The 2 points that we have to remember is it will increase with the increase in the number of carbon atoms, and it will decrease with the increase in branching of the carbon chain because of the decrease in van der Waals forces with increase in surface area. This we have been discussing for the last 2-3 chapters. The OH group in alcohols and phenols is involved in intermolecular hydrogen bonding. As you can see over here, there is intermolecular hydrogen bonding in both these molecules, and as a result of which the boiling points of alcohols and phenols are higher in comparison to the other classes of compounds such as hydrocarbons, ethers, haloalkanes, and haloarenes of comparable molecular masses. So this is an important thing. The maximum is for maximum boiling point is for alcohols and phenols compared to the other molecules. So this is the most important physical property, and let us now talk about the next physical property, that is solubility. Now when we talk about solubility, the solubility of alcohols and phenols in water is due to their ability to form hydrogen bonds with water molecules. It can form hydrogen bonds with And if it can form hydrogen bonds with water, is that there is solubility, and this solubility decreases with increase in size of the alkyl or aryl groups. So this is important. When the size of the alkyl or the aryl group is increasing, what is happening? The solubility is going to decrease. So the lower groups, lower molecular mass alcohols, they are miscible with water in all proportions. This is important. Let us now discuss a question related to arrange the following set of compounds in the order of their increasing boiling points: pentan 1, butan 1, butan 2-ol, ethanol, propanol, methanol. First, check the number of carbon. We have a 5 carbon, 4 carbon here, 4 carbon here, 2 carbon here, 3 carbon here, and 1 carbon here. So the least is for methanol, then comes ethanol, then comes propanol. Now the thing is with these two. Check for branching. Branching is more in butan 2-ol, and as a result of it, that will have lower boiling point, and then will come butan 1-ol, and finally it will be pentan 1-ol. Next, and 1 contain pentanal and CE. So we have an alcohol, hydrocarbon, aldehyde. So highest is for alcohol, next is for aldehyde, next is for ether, and least is for. So we have another questions here. Yes. Show how the following alcohols are prepared by the reaction of a suitable Grignard reagent on the methanol. Okay. So this much part should be there. We have to keep the RCH2OH group aside because we have methanol, right? Since we have methanol arrived at the complete step, so that it is easy for you to understand, we have C double bond O, sorry, C double bond O. This is treated with RMgX. Now this group is coming and attaching over here, so we'll get the adduct. What is the adduct? Adduct is C single bond O, MgX, and we have an R here. This much group is moving out as MgOHX, so we are left with this, right? And what is the corresponding? We have methanol here, right? We have a methanol here, so this is H and this is also H. Now we have to compare this molecule. This is same as RCH2OH, so we have to compare this with this, right? So what is the R group? The R group is going to be this isopropyl group. So we are getting CH3 CH3 MgX. That is the corresponding Grignard reagent. And here also, if I compare this with RCH2OH, what is the R group? R group is the cyclohexane, result of which the Now let us do the next question. Write the structures of the following reactions. Hydration. So this is a unsymmetrical molecule, so the H plus will come onto this side and OH will come over this side. It is solution. If we have esters, we have to use LiALH. Now the next question, here we have an aldehyde group, so that is converted to CH2OH group. The complete group will be there along with the question in textual questions. So let us move on to the next part, that is first we have two methods. The first one is dehydration of alcohols. So alcohols have if using it at a very high temperature of 443 Kelvin in the presence of H2SO4, we have already studied that we are getting ethene over there. But if I am using the same thing at 413 Kelvin, what is happening? We get, see the mechanism. So what is happening is that first we have CH3 CH2 OH plus H plus. Oxygen is rich in electron, so what is happening? It is going to take up the H plus, and as a result of which we get this particular molecule. Now what is going to happen? another molecule of alcohol is going to react with this. Now we have this OH. This O is having electrons, so this is going out as water. So now this group is attached to this group, and as a result of which we get CH3CH2O with a single electron. That is, it's a free radical. Sorry, it is having a positive charge now, and we have H here and CH2CH3 over here. So to become stable, this hydrogen is moving out as H plus, and now we are getting the corresponding ether over here, right? No need of studying the mechanism, but for the board students, for the board examination, this is important. Simple si baat. First thing is we have to treat it with an H plus. Second step, we have to treat it with the same alcohol again, and in the next step we have to deprotonate. That's the method that is happening. Protonation here, formation of carbocation in the next step, and in the last step we have deprotonation. That will give us the corresponding product. Let us now move on to the next one, but before that we have a paragraph here, and this is important. Alkene is also associated with substitution reaction to give an ether. This method is suitable for the preparation of ethers having primary alkyl groups only. We need only primary alkyl groups out this particular reaction. The alkyl group should be unhindered and the temperature should be kept low. This is important. Temperature should be low. Otherwise, what is going to happen? Otherwise, it will favor the formation of alkene. Now, the reaction follows SN1 pathway. This is important. SN1 pathway. When the alcohol is going to result in elimination, and that will result in the formation. That's why we are not carrying out this process here. Right? We are not going to carry out SN1. SN1 will happen if there is secondary. So we are restricting this to primary alcohols, because primary alcohols will favor two mechanism as we have studied, right? SN2 mechanism order, reactivity order we have studied yesterday. Primary greater than secondary greater than tertiary. So what happens? The primary, if only primary alkyl groups are present, then that will favor SN2. And if there is SN2 mechanism, there is formation of ether. SN1 mechanism can result in elimination, and so that is not the desired product. Now talk about Williamson synthesis. In Williamson synthesis, we have taken RX and RONA, sodium. So here what is happening? Alkyl halide. So always go by the mechanism like this, otherwise it is going to be difficult. So first of all, we have CH3, CCH3, CH3, ONA. This is treated with CH3Br. So as we know, this oxygen is electronegative, so it will try to donate the electron to the methyl group, and as a result of which this bromine is going to pull the electrons from the methane, because now this bromine will say that you are getting enough from oxygen, so why do you need my electrons? So it is going to take up the electron, and this is going to move out as Br minus. Now what is going to happen? This part is going to join with this, and as a result of which we have CH3O, CCH3, CH3, CH3, and Na is also going to move out. This part is also going to move out, and this CH3 is going to attach over here. Sorry, this CH3 is going to attach onto this oxygen atom. So we get the corresponding ether over here. Better results are obtained if alkyl halide is primary. This is important. If we have a primary alkyl halide, then the result is better. But if we are having a tertiary alkyl halide, what is happening? Let us. In that particular case also, we have electron. Here what is happening is that the alkene is the reaction product. So and as a result of which there is beta elimination reaction happening over there, and as a result of beta alkene over here. Bases also they are out beta elimination also. If there is a possibility for beta elimination, the result as a result of that we can get alkenes also. So phenols also can be converted into ethers by this method. Here we are going to take it as phenoxide, and now this phenoxide is treated with Rx. So now this NaX is moving out and we get the corresponding ether over here. The physical properties of carbon, what is happening? When of carbon is happening, the increases, right? But compared to alkaline point is hydrogen bonds between the water molecules. So let us discuss some of the important. Which of the following reagents can be used to oxidize primary alcohols? We have not discussed yet. So let us keep it on a hold. This we have not discussed. Let's move on to the next question. Second question is, RCHO means it is an aldehyde. So aldehyde should be converted into corresponding alcohol. If we have to convert aldehyde into alcohol, we can use hydrogen in the presence of palladium. We can use NaBH4. We can use reaction with RMGX followed by hydrolysis will give us secondary alcohol. This will give us secondary alcohol. So that is not possible because we need a primary alcohol here. So we need a primary alcohol over here. LiAlH4 can also be used. So this is a multiple exemplar. The answer should be 1, 2 and 3. Let us see the next question. Which of the following reactions will yield phenol? So if we look at the first question, first option here, we have fusion with NaOH at 300 atmosphere. Yes, this is going to give us phenol. Now here treating it with NaNO2 in the presence of HCl, this is known as diacetization, and after that we are treating it with warm water. Yes, we will get phenol over here. Next we are going to treat it with oleum. We are getting benzene sulfonic acid, and that is treated with NaOH on heating will give us phenol. Next we have chlorobenzene, that is treated with NaOH at 298 Kelvin. No, this is wrong because we need nearly 623 Kelvin is needed. Let us now move on to the next question. We have to arrange the following in the increasing order of boiling point. Very simple question. First step, we have to count the number of carbon atoms. So when we are counting the number of carbon atoms, we have 3 here, 4, 4 and 5. So we are asked the increasing order. So least will be for propan 1 all. It cannot be pentan 1 all. So these two options are eliminated. Now maximum is for pentan 1 all. And now the problem is with the 4 carbon, which has more branching. Butan 2 all has more branching, and as a result of which that is going to have lesser boiling point. So this should be the answer. Answer is option number 1. Let us move on to the next question. Which of the following compounds will react with soda? Next part. Which of the following alcohol? In the next lecture, we will be discussing the chemical properties and reactions of alcohols, phenols, and ethers. So, see you again in the next lecture. Till then, goodbye and happy learning.
Hello everyone, welcome to the revision lecture series of organic chemistry. In this lecture, we will be discussing the chemical reactions of alcohols, phenols, and ethers. This is the part 2 of this chapter. So let's get started with the very first topic, that is acidity of alcohols and phenols. Now, first we have to study about the reaction of alcohols and phenols with metals. So if I react an alcohol with metal, what happens is that I get sodium alkoxide. And what is the formula for sodium alkoxide? It is RONA. This is going to be the formula for sodium alkoxide. Now, if I have a tert butyl alcohol, as you can see over here, that will react with an aluminium to form aluminium tert butoxide. So we can see that they are reacting with metals and they are going to give us a salt. Along with that, there is liberation of hydrogen gas as well. So this is what we are expecting when we are reacting an acid with a metal. If we are reacting an acid with a metal, what happens is that we get a salt and we also get hydrogen gas over there. So the same reaction is happening here also. So we can say that alcohols and phenols are acidic in nature. This is the first point. First reason why we can say that alcohols and phenols are acidic in nature. So if I take another example, here we have phenol reacting with sodium to give sodium phenoxide. That is another example. And here we can see another very important example. If I take phenol and react it with NaOH, I will get a salt, that is sodium phenoxide, and there is elimination of water. Now here you can see we have a base here, and when we are reacting the phenol with a base, we are getting a salt and we are getting water. And what is the general neutralization reaction? If you could remember from the lower classes, the general uh, sorry the general neutralization reactions is acid plus base gives salt plus water. So here I took a base, that is NaOH. I am getting a salt and I am getting water here. So our phenol in that case should be acidic. So this is another example where we can say that phenol is acidic in nature. Let us now see another case. Above reaction shows that alcohols and phenols are acidic in nature. Therefore, we can say that alcohols and phenols, they are Bronsted acids. Now, what do you mean by Bronsted acids? They will donate a proton. They will donate a proton, an H plus, to a stronger base. That is why they are known as Bronsted acids. So, this is very important. Alcohols and phenols are Bronsted acids. Let us now talk about acidity of alcohols. Now, if I consider primary, secondary and tertiary alcohols here, we can understand that the bond, the OH bond, is polar. And this polarity of the OH bond is responsible for the acidity of alcohol. Second reason. What is the reason? We have oxygen, which is an electronegative atom, and we have hydrogen, which is an electropositive atom. So this bond is going to cleave because the electron is going to try to pull the electron. All the electrons in the bond are pulled towards the oxygen atom. As a result, this hydrogen can come out as H plus, and that H plus is responsible for the acidity of alcohols. Let us now talk about another reason, that is acidity of phenols. If we see the decomposition of phenol, we can see, or not decomposition, it is splitting. Okay, H plus is moving out, so we get a phenoxide ion here, right? This phenoxide ion is less stable. This is less stable. Okay, sorry, phenoxide ion is more stable, and as a result of which it will help in the ionization of phenol. So that is another reason why phenol is more acidic. So three reasons we have studied. First reason is reaction with metals. When they are reacting with metals, they are giving hydrogen gas. When we are reacting it with a base, what is happening? We get water over there as well as a salt over there. And the third reason is because of the more stability of the phenoxide ion. More than phenol, phenoxide ion is more stable, so it will split up, it will give out the H plus ion. It will we can say polarize or ionize the phenol molecule, and it will releases the H plus and it will form phenoxide ion, and this phenoxide ion is more stable. Now, for the exam, they will ask us questions based on what is the effect of withdrawing group and donating group. What will happen when there is a withdrawing group and what will happen when there is a donating group. Now we have to understand it with a trick. Withdrawing group will increase as acidity and donating group will decrease as acidity. So this is important. Okay, so see here. Here you can see a which. This is a which. Now look at the first two letters of the which. It is W and I, right? So W stands for withdrawing and I stands for increases. So whenever there is a withdrawing group, that will increases the acidity. So the which is having a dog and that is a dumb dog. So you can study D and D, right? D and D. So D stands for donating and D stands for decreasing. So this is a trick. Which has a dumb dog? Which has a dumb dog? So W stands for withdrawing, increases, D for donating, and this D for decreases. Now the next reaction that we are going to study is esterification. Now what is esterification? Esterification is the formation of esters. It is the formation of esters. And how are esters formed? Esters are formed when alcohols or phenols react with either carboxylic acid or acid chloride or acid anhydride. Now, here what happens is that in the case of acid and acid anhydride, in both these cases what is happening, we will be getting the corresponding esters over here, right? And here we are getting R-COOH as the remaining product. And here we are getting H2O as the byproduct. But here in the case of R-COCl, that is in the case of acid chlorides, what happens is that there is liberation of HCl molecule. And since there is a liberation of HCl molecule, we need a base, that is pyridine, to neutralize this HCl. So this is very important. To neutralize the HCl molecule, we need pyridine. Let us now see another very important equation, that is this. Here you can see salicylic acid. Now what is salicylic acid? We have COOH at the first position and OH in the neighboring carbon. That is reacted with this compound and we are getting acetyl salicylic acid. You have to study the formula for acetyl salicylic acid. This acetyl salicylic acid is used for the preparation of a drug, and that drug is known as aspirin. So this is a very important equation. So we have to study that acetylation of salicylic acid produces aspirin. Let us now see the next reaction. That is reaction of alcohols with hydrogen halides. So if I take ROH plus HX. Okay, so here you can see ROH plus HX. This is going to give us RX plus H2O. Now, this reaction is known as Lucas test. We have already studied it in the previous chapter, that this is Lucas test. Now, this Lucas test can be used for distinguishing primary, secondary and tertiary. Because what is the reason? The reactivity of alcohols, this is very important, the reactivity of alcohols is in the order tertiary greater than, secondary greater than, primary. It is following the order tertiary greater than, secondary greater than, primary. That means tertiary is most reactive towards this particular reaction and primary is least reactive. Secondary is intermediate of tertiary and primary. So we can say that tertiary does not require any catalyst. It can carry out if we take the tertiary alcohol and the corresponding acid in a test tube and simply shake. That much is enough for converting it to an alkyl halide. But in the case of secondary and primary, we must need any catalyst, and the most preferred catalyst is anhydrous Cl2. Anhydrous Cl2 is used in the case of secondary and primary. So if it is reacting comparatively faster, then it is secondary in the presence of anhydrous Cl2, and if it is not reacting that much fastly, then we can say it is primary. Hence it can be used to distinguish between primary, secondary and tertiary alcohols. Next important reaction is dehydration. Now here also we have a very important order, that is this: tertiary greater than, secondary greater than, primary. This is the order of dehydration. So tertiary needs minimum reaction conditions for carrying out dehydration, and hence we will use milder oxidizing agents, dehydrating agents, such as 20% of H3PO4 and at a lesser temperature, that is 358 Kelvin. On the other hand, if we have secondary alcohol, we need little more stronger conditions for carrying out dehydration. That is why we are using 85% of H3PO4 solution. And in the case of primary, they are least reactive towards dehydration, and that is the reason why we have to use another strong acid, that is H2SO4, and the condition used is 443 Kelvin. So the condition we have studied. Now what is happening in the process of dehydration? In dehydration, there is removal of an H plus from one carbon and OH from other carbon. The carbon onto which the OH is attached, that is known as the alpha carbon, and the carbon onto which the hydrogen is attached just near to the OH containing carbon, that is known as the beta carbon. So we can see that in the presence of these dehydrating agents, these particles are going to move out. What particles are moving out? H2O is going to move out. There is an elimination of water, and that is why the process is known as dehydration. Okay, so this is known as dehydration, and dehydration is basically a beta elimination reaction, because from the alpha and from the beta, compounds are moving out, or groups are moving out. That is why it is known as beta elimination reaction. We have already studied so many beta elimination reactions previously, so kindly check the previous videos for that. Let us now talk about oxidation. Oxidation is the most important reaction from here. Now, oxidation is also known as dehydrogenation. What is the reason for that? Reason being, it will eliminate H2. It will eliminate H2, because here we have RCH2OH, here we have only RCHO, here we have 3 hydrogen, here we have only 1 hydrogen. So H2 is being removed, and that is why it is called as dehydrogenation reactions. Now, if we use mild oxidizing agents, alcohols can be converted into corresponding aldehydes. If we use stronger oxidizing agents, alcohols can be converted into carboxylic acids. If we use milder oxidizing agents on aldehydes, then also we can convert it into carboxylic acid. Now, suppose we have a primary alcohol. We have any alcohol, and if I treat it with CrO3, I will be getting RCHO. RCHO is obtained over there. But if there is a compound containing double bond, then we have to use PCC, and PCC is most preferred for primary alcohols. It is most preferred for primary alcohols. Okay, so it does not affect the double bond. That is the most important thing. Now, if we have a primary alcohol, we will get an aldehyde. If we have a secondary alcohol, we will get a ketone. And if we have a tertiary alcohol, and if we carry out the process of oxidation, we can use copper for the process, we will be getting an alkene over here. We will be getting an alkene. So that is important. Okay, there is beta elimination happening over here. This carbon onto which the OH is attached, that is going to be the alpha carbon, and this is going to be the beta carbon. So from these two, we are moving a water molecule, and the process is called as dehydration. So copper at 573 Kelvin, in the case of a tertiary alcohol, is going to carry out dehydration and not oxidation. That is important. Okay, so copper can be used for converting primary alcohol to aldehyde and secondary to ketone. So we studied so many reactants here. Okay, so many reactants we have studied here. Oxidizing reagents. First one was CrO3. CrO3 can convert into aldehyde, so it is a milder oxidizing agent. Now we have already studied about KMnO4, right? In the topic of alkanes also we have studied. KMnO4 is a strong oxidizing agent, and as a result of which it can directly convert it into an carboxylic acid. So that is important. Another important reagent that we have studied is PCC. Another important one is copper. Okay, so these are some of the important oxidizing agents that we are studying over here. Now you can download a special organic revision note which we have uploaded at the Neetshala app. You can go to the Neetshala app. In the concept booster series of chemistry, you can get this note where we have included all the oxidizing agents, all the reducing agents together. So it will be really helpful for your NEET preparation. So let us now talk about the reactions of phenols. We have finished with the reactions of alcohols. Let us now talk about the reactions of phenols. The first one is electrophilic aromatic substitution. Now, phenols are ortho-para-directing. The OH group is ortho-para-directing group, right? We have already discussed about that in the benzene part. It is ortho-para-directing group. So if I use dilute HNO3, that is going to carry out the process of nitration. We do not require H2SO4 here. What is the reason? Is because we have the OH group, which is a strong protonating group. It can protonate the dilute HNO3 to give NO2 plus. Now what do you mean by this protonation? Protonation basically means that if I have HNO3, this HNO3 is going to give me NO2 plus plus H plus. This process is called as protonation. So in the case of benzene, we can say that we need some agents, right? What was the agent that was used? H2SO4, right? But here we have OH, and this OH, in the presence of this OH, so you can consider this phenol as a what you say, Vishwamitra. Okay, so whenever this HNO3 is there, he is scared of Vishwamitra. So if there is any other saint, poor saint is there, means the compound is not at all scared of him, and he needs some other people to get protonated. But in the presence of strict persons like Vishwamitra, what happens is that they will carry out the protonation on themselves. So they will give us NO2 positive, right? They are going to give us NO2 positive, and this NO2 positive will be substituted at the ortho and para positions to give the corresponding products. Now, how can we separate these two, ortho and para products? It's very simple. If I take the ortho product, we can say that they have intramolecular hydrogen bonding. Whereas in the case of para-nitrophenol, there is intermolecular hydrogen bonding. Now, whenever there is intermolecular hydrogen bonding, two people are held together. Two people are held together. So when two people are held together, they are very good friends. So one friend does not want to leave another friend, right? So they are not at all volatile, very less volatile. Whereas even if there is intramolecular hydrogen bonding, the hydrogen bonding is present within the same molecule. So there is no problem in volatility. So this is volatile, this is less volatile. So we can easily separate them by steam distillation method. So this is important. They can ask, what is the method used for separation of ortho and para isomers of nitrophenol? So that is important. Now I used dilute HNO3 for carrying out the reaction of nitration. What if I use concentrated HNO3? If I'm using concentrated HNO3, I will be getting picric acid. What is picric acid? 2,4,6-trinitrophenol. So in three contexts you are studying picric acid. What are the three contexts? Last chapter we have studied. If I have Cl here, NO2 here, NO2 here, okay, this is benzene, and here also I have an NO2 group. So how to convert this into picric acid? We have already studied, right? We have to treat it with NaOH. So heat it, we will be getting picric acid. This was the reaction that we studied in the previous chapter. And now we have studied here, treated with concentrated HNO3. But the yield of this reaction is very poor. So what should we do? To increase the yield, what should we do? First, we have to carry out the sulfonation. For sulfonation, what we should do? We have to treat the phenol with sulfuric acid. We have to treat the phenol with sulfuric acid, and we are getting this compound. This is the compound that we are getting. And to this compound, this is known as phenol 2,4-disulfonic acid. Okay, this is known as phenol 2,4-disulfonic acid. Now, this we have to treat it with concentrated HNO3. So when we treat it with concentrated HNO3, we will get picric acid. So this is mentioned in NCERT and they have asked to write the equation. So you can write it now easily, two-step process. So this is important. Let us now talk about the halogenation. Now halogenation also, earlier we need a Lewis base, right? We need a Lewis base for the protonation. Br2 should convert to Br plus Br minus, and this Br plus is required for carrying out the process, right? Process of halogenation. But here, since it is phenol molecule, the Br2 is also feared of our Vishwamitra. So what is happening? It will get protonated easily. So we will carry out it in the presence of a low polarity solvents such as CHCl3 or carbon disulfide medium. So these are low polarity solvents at low temperature. We will be getting ortho and para products over there. Now what if I'm treating it with bromine water? If I treat it with bromine water, what happens is that I get 2,4,6 tribromophenol. 2,4,6 tribromophenol. This bromine water is reddish brown in color and this is going to be white in color. So this can be used as a distinguishing test for phenol. Now this is a question given in NCERT. Write the structures of the major products expected from the following reactions. Mononitration of 3-methylphenol. So there is a methyl group present. So it will come like this, right? The para product will be obtained over here. Now if we have dinitration, what happens? Then also we will get ortho and para product over here in the first case. Second case, there is dinitration. If it is dinitration, we will be getting both ortho and para position will be filled. Now another one is mononitration of phenyl methanoate. So when we have mononitration of phenyl methanoate, it will come only in the para position. So this is important. Let us now talk about the Kolbe's reaction. Now whenever we hear about Kolbe, remember that we need CO2. We need CO2 in his reaction. He is very fond of CO2. So here what happens? We have phenol treated with NaOH. We will be getting sodium benzoate, and we have to treat it with CO2. We will be getting salicylic acid. We are getting salicylic acid. So this is known as Kolbe's reaction. This is important. They can give directly this equation and ask what is the reaction. Now here we have another very important reaction, that is Raymer-Tiemann reaction. In Raymer-Tiemann reaction, what happens is that this compound will react and it will form CCl2. This is the electrophile in the reaction. Carbene. Dichlorocarbene is the intermediate, or we can say the electrophile. It is the electrophile. And what is the intermediate? They can ask what is the intermediate. Intermediate is known as benzyl chloride. It is not benzyl chloride, it is benzyl chloride. This benzyl chloride is now treated with NaOH. So we will be getting this compound over here. And finally we have to treat it with any of the acids. So we will be getting salicyl aldehyde. We are getting salicyl aldehyde over here. Okay, so this is known as Raymer-Tiemann reaction. They will give the reaction directly and they will ask us to identify the reaction. So this is very important. Named reactions are very, very important. Let us now talk about the oxidation. This we have already studied, reaction with zinc dust. When we are treating phenol with zinc dust, we will be getting benzene, already studied in hydrocarbons chapter. Now, what about oxidation? Oxidation is carried out. Oxidation of phenol is carried out by using Na2Cr2O7. So this is another oxidizing agent, important. So this will give us benzoquinone. Next is the chemical reactions of ethers. So when we talk about the chemical reactions of ethers, the first one is reaction with HX. What is HX? HX can be HCl, HBr, anything. And what is the order of reactivity? HI greater than, HBr greater than HCl. This is the order of reactivity. So what happens when we are treating an ether with HX? When we are treating an ether, that is ROR dash plus HX, what are we getting over here? We will be getting R dash OH. This group will go with this R dash O and H, plus we get RX over here. Now the most important thing is that they will give one group as tertiary. This is the most important part. If they give one group as tertiary, then we have to take it as we have to add the halogen atom to the tertiary side. That is the most important point. We have to add the halogen atom to the tertiary side. This is the most important question that we can expect from here. Okay, so let us now talk about the next reaction, that is electrophilic substitution. In electrophilic substitution, again we have to study that OR group, that is, it can be OCH3 or C2H5, all these type of groups can be present. These are again ortho and para directing group, and since they are ortho and para directing group, whenever we are carrying out halogenation, we will be getting para and ortho product, and para is the major product. Now look at the reagent here, Br2 in ethanoic acid, we are taking low polarity solvents again. Friedel-Crafts alkylation and Friedel-Crafts acylation. Here you can see we are getting ortho and para products in both cases, same as that of benzene. There is slight difference, that is we have to carry out these reactions in CS2 medium, that is the only difference. So last one is nitration. Nitration, here we have to use H2SO4 and HNO3 because OCH3 is not that much polarizing group, it is not that much strict as our phenol group. So we will be getting the same products over here, but the mixture is important. Mixture is important, they can ask about the mixture. So this completes our chapter. Now let us do some of the questions related to this chapter. Neet 2018 question. Compound A on treatment with sodium gives B. Okay. With PCl5 it will give C. B and C together to give diethyl ether. A, B and C is in the order. So here if I am checking the options, 3 options are saying C2H5OH and 1 is saying C2H5Cl as A. So let us take both. First let us take C2H5OH and let us treat it with sodium. Will the reaction occur? Yes, reaction will occur. We get C2H5ONA, right? C2H5ONA is obtained. Next, what are they saying? If I treat this C2H5OH with PCl5, I will be getting C2H5Cl, right? C2H5Cl. Now they are asking me to react this with this. So there we are getting C2H5 or C2H5. What is the process? The process is known as Williamson's ether synthesis, right? Williamson's ether synthesis. So the answer should be A should be C2H5OH. So we can eliminate this option because that last one does not react with sodium. So that cannot be the answer. So next option should be C2H5ONA because that we are getting over here as B, and C we are getting as C2H5Cl. So the answer should be option number C, 3. Now for doing this question we can use the trick which has a dumb dog. So here you can see that CH3 is the group present. CH3 is the group, means it is a donating group, so it will decreases, right? It is decreasing. So the order is going to be this. Phenol is going to be more acidic, and then we have the meta, ortho and para. Now remember that whenever we have groups like CH3 which is donating group, whenever we have donating group it will follow the order MOP, meta, then M, P and O, meta, then para, and least for ortho. And in the case of withdrawing group it is OPM. This is the order, decreasing order. Next, OCH3 is treated with CH3Br and FeBr3. What is the major product? Very simple question. We just have to add. This is a basic process of alkylation. So we have to add CH3 group to the para position because para is the major product. So it is option number 4. Next, this is an important question. Usually what happens is that everyone will do it like this. This group is going to go with H, so they will form CH3 CH2OH plus CH3I. This is the first product. Everyone will get up to that, and they will stop with option number 2 because option number 2 says CH3I plus CH3 CH2OH. They have given that HI is taken in excess. Now since it is taken in excess, what we should do is this one again we have to treat it with HI because there is a possibility that alcohols can also react with HI, right? So we have to carry out that reaction because even after doing the first round of reaction there is enough of HI left for carrying out another round of reaction. So when we are carrying out another round of reaction, what is happening? We get CH3 CH2I. So we get CH3I as the first product and CH3 CH2I as the second product. So the answer should be option number 3. Let us now talk about the next question. Here what is the product A is asked. So in the first step, what is happening? Nitration is carried out of benzene, so we get nitrobenzene. Treated with SN plus HCl, we get aniline. We will study this reaction later. And next we have to carry out diacetization, we get benzene disonium chloride, and that is treated with H2O, we get phenol. Next, identify the major products PQR in the following reaction. So first we have to treat this with anhydrous AlCl3. So what is the process? The process is going to be this is the compound, so it is alkylation. It is alkylation, and after that we have to carry out oxidation. Okay, so let us see the process here. Here we get this compound over here, and now we have to carry out the oxidation, and we get cumene, right? This is known as cumene. So cumene is carried out oxidation, and we are getting cumene hydroperoxide, and then we are carrying out the hydroperoxide rearrangement to give us phenol, right? So this is important. Now here the thing is that people make mistake in this part, right? So I will do that again. What is the compound that is given for us? Here it is CH3 CH2 CH2Cl. So CH3 CH2 CH2Cl, what is happening? This is going to react with AlCl3 to form AlCl4 minus and CH3 CH2 CH2 with a positive sign. Now this is a primary. Let us check whether there is any possibility for getting a secondary. Yes, if I am shifting one hydrogen from here to here, I will get a positive sign over here, so I can remove this over here and I can add a hydrogen over here, right? So this is what I am getting over there. We get a secondary carbocation that is more stable. So this secondary part is going to substitute on the benzene ring, and as a result of which we are getting this compound over here, cumene over here. And now this is carrying out oxidation. So what happens? Remove this H and we have to add OOH. Now what we should do? This much part we are removing, and OH we will keep it as such. So we get a ketone also, that is propanol. Now let us talk about this question. Which of the following is the most acidic compound? It should be option number 4. Heating of phenyl methyl ethers. Phenyl methyl ether means this is the compound. So what happens is that this group is going to go with I. So this is the product that we are getting, and the answer should be phenol. Next, what is this reaction? Yeah, this type of questions we can expect plenty of questions for the NEET exam. What is the reaction? First step, we are treating with NaH. We are getting RONA. This is of general form, RONA, and MEI is same as CH3I. So that is treated with RX. RONA plus RX. It is Williamson's ether synthesis. So option number 2. Among the following ethers, which one of the following will produces methyl alcohol on treatment with hot concentrated HI? So whenever I have a tertiary, I told you that this will go with the iodine. So the other one will go with OH. So it will be CH3OH. Methyl alcohol is produced in the case of option number 2. Next, this question we have already done. And let's see this question over here. Which one of the following compounds has the most acidic nature? First one is CH2OH. This is phenol, right? So phenol is most acidic among the following. Anyway, it cannot be these two. Here we have CH2OH and this one. So due to inductive effect, we can say phenol is the answer. Which one is the most reactive towards electrophilic reagent? So whichever is having higher electron releasing effect, that is going to be showing electrophilic reagent. More reactive towards electrophilic reagent. So the answer should be option number 1. Now the next one is para-nitrophenol. We have to find what is the acidity order. So if we talk about the acidity order, I have told you that whenever we have, here we have methyl group, here we have nitro, and here we have nitro. Nitro is a withdrawing group, and CH3 is a donating group. So whenever there is a withdrawing group, it will increase us, right? It will increase us, and donating group will decrease us. So what could be the least? Least could be this. It could be least because it will decrease. Then comes phenol. So B should be the least. Then comes phenol. Sorry, this is the simple. Then comes C because meta will come, and least will be, sorry, maximum will be for para product. So it should be D. So D, C, A, B, option number 1 is correct. Yeah. So with this, we are concluding this chapter, alcohols, phenols, and ethers. In the next lecture, we will be taking up the chapter aldehydes, ketones, and carboxylic acid. The long chapter, lengthiest chapter of organic chemistry, aldehydes, ketones, and carboxylic acid, we will be taking up in the next lecture. So see you again in the next lecture. Till then, goodbye and happy learning. Hello everyone. Welcome to Neetshala Organic Chemistry Revision Lecture Series. In this lecture, we will be taking the chapter aldehydes, ketones, and carboxylic acid. Now, in the previous chapter, you have studied about alcohols, phenols, and ethers. In all those compounds, you have seen that the carbon is attached to oxygen by means of a sigma bond. Now, if we take the compounds aldehydes, ketones, and carboxylic acid, you have carbon attached to the oxygen by means of a double bond, one sigma and one pi bond. So that is the difference between these two. And these compounds are commonly called as carbonyl compounds. So let's get started with the chapter. First, we will study about the structure of the carbonyl group. First important point is that the carbon-carbon bond, the carbonyl carbon atom is sp2 hybridized. That is the first important point. And how many sigma bonds are there? There are 3 sigma bonds, as you can see, 1, 2, and 3. 3 sigma bonds will be there, and 1 pi bond will be formed between the carbon and oxygen atom. So what will be the hybridization? Hybridization is coming out to be sp2, and if it is sp2, it is 120 degree. 120 degree is coming out to be the bond angle, and you can see all are lying in the plane, right? All are lying in the plane, so we can say it is trigonal coplanar in structure. Now if we take the compound, we can see that oxygen is present, and this oxygen is highly electronegative. Since the oxygen is highly electronegative, it will try to pull away the electrons from the double bond like this. So there is a possibility that the oxygen will get a negative sign and carbon will get a positive sign. So we can say it is a polar bond. That is an important point. It is a polar bond. And this oxygen, it is ready to form a negative sign. So we can say this oxygen is a nucleophilic center. Nucleophilic center. And what about the other one? The carbon is coming out to be the electrophilic center. So that is an important point. Oxygen is acting as a nucleophilic center and carbon is acting as an electrophilic center, or the Lewis acid. Let us now talk about the general methods of preparation of aldehydes and ketones. First one, by the oxidation of alcohols. This you have already discussed in the previous chapter. How to do? If we have a primary alcohol will give us aldehyde. It will give us aldehyde, and secondary alcohol will give ketones. Secondary will give ketones. This is what you have studied. Second process is dehydrogenation of alcohols. Now how can you carry out dehydrogenation? By using copper. By using copper you can use dehydrogenation. That is nothing but removal of hydrogen or oxidation itself. So the same process is going to happen. The primary is going to convert into aldehyde and secondary is going to convert into ketone. Now from hydrocarbons, how can you prepare? The first one is ozonolysis. So if I have an alkene, I can prepare aldehydes by using the method of ozonolysis. So we have already studied about ozonolysis. Let's just recap that here. If I have a compound like CH3, CH, double bond CH2, what I should do? Write an oxygen above the double bond, write an oxygen under this carbon, write an oxygen under this carbon, join these two, form an ozonide, and then break from the roof to the base, and whatever is left you have to join to get the compound. So this is CH3CHO, and this we will write it as HCHO, methanol, and this one is ethanol. So this is what is known as ozonolysis. Now how to prepare aldehydes and ketones from alkyne? alkyne. So it is CH3 C triple bond CH, right? We have to add water to it in the presence of Hg2 plus and H2SO4. Okay, so at that time what happens is that there is Markovnikov's addition. So this side is deficit of hydrogen, right? We have to make the poor poorer. So we have to add the OH group here, and we have to break the triple bond and make it a double bond. To this side we will add hydrogen because this is excess in hydrogen, so we will add more hydrogen to that. We have to make the rich richer. So we will be getting CH3 COH double bond CH2 as the compound, right? So this is what we have got over here. Now this one can be arranged, or we can say rearranged. What is the rearrangement? Let us bring, I'll take another color. Let us bring this double bond over here, and this oxygen let us give to the carbon. This is nothing but ketoenol tautomerism. This is the enol form. How can I say it is the enol form? I can see a double bond here, right? So en, and we have an OH here, all. So we have enol, right? Now how to convert it into keto form? You have to shift the double bond to the carbon that is here, and the hydrogen on the oxygen should be given to the other carbon, that is like this. And now what am I getting? I will get CH3 C double bond O single bond CH3. So I got a ketone here. So this is the another method of preparation from alkyne. So we have completed this topic, general methods of preparation of aldehydes and ketones. So this is easy, right? And in this, most important one is this ozonolysis and hydration of alkynes. This one is very important, so I will put a 2 star for this, and I will put a 3 star for this. Very important reactions. You can expect one among these for the exam. Let us now talk about, so I'll just clear the slide. Okay, so let us move on to the general methods of preparation of aldehydes. Now this chapter is very famous chapter. What is the reason? It has so many named reactions in it. So many named reactions are present in this chapter. So how to deal with named reactions? There is only one way to deal with it. Make a chart. Make a chart of named reactions where you will have one column for the reactant, another column for the product, another column for the reagent that is used, and also you have to specify the name. If there is any limitation, you can specify that also in a separate column. So if you learn like that, it is easy for you to understand what is converted to what. That is the most important thing that is asked from a named reaction. And if you have downloaded the revision book, we have uploaded a revision book in the Neetshala app, in which you can get all the named reactions together in the form of a table. So if you have not downloaded that, you can go to Neetshala app. You can go to the concept booster series, concept booster notes, chemistry. So you can download the note from there. Let us now talk about preparation of aldehydes. So when we talk about the preparation of aldehydes, the first one is from acyl chloride. Now what is acyl chloride? General formula is RCOCl, that is acyl chloride, or we can have benzene with a COCl, that is known as acyl chloride. So that is now treated with hydrogen in the presence of palladium and barium sulfate or quinoline. This is known as Rosen-Mundt reaction. What is happening is that this Cl is going to be removed and hydrogen should be placed over here. So that is why we are getting benzaldehyde over here. Okay, this is Rosen-Mundt reduction. So we have to study what is the catalyst which is used for this particular process. It can be palladium or barium sulfate, and we have to add hydrogen, right? It is addition of hydrogen, that means it is reduction, right? Chlorine is substituted by hydrogen. It is reduction reaction. Let us now talk about second method, that is from nitriles and esters. This is important. So many reactions are coming, so this is important. What are we going to do? First one, we are going to treat the nitrile, that is RCN, with SnCl2 and HCl. This is again a reducing agent. Okay, SnCl2 plus HCl is a reducing agent. So when we are treating RCN with SnCl2 and HCl, we will be getting RCH double bond NH. This compound is known as imine. This is known as imine. Okay, compound where there is carbon double bond nitrogen, that is known as, this type of compounds are known as imine. Now this imine on hydrolysis, what will you get? This on hydrolysis will give us the corresponding aldehyde. Okay, so this reaction is known as Stephan reduction. So in Stephan reduction, you will use SnCl2 and HCl. RCN is converted to RCHO. Let us now talk about the next reaction. What is the next reaction? The next reaction is treating with Dibal H. What is Dibal H? Diisobutyl aluminium hydride. Diisobutyl aluminium hydride, or Dibal H. Either you can write it as Dibal H, or you can write it like this. This is another method of representing. So what is happening? RCN is converted to RCHO, and here you have an ester, right? RCOOR dash, that is an ester. So that can be also converted into a corresponding aldehyde, right? This much group will be converted to an aldehyde. This much will be removed and that will become an alcohol, and the other part we will add a hydrogen and we will get a corresponding aldehyde over there. So that is about the preparation of aldehydes from nitriles and esters. So let's remove this blank slide, and here we go. Third method, from hydrocarbons. So when we talk about hydrocarbons, we are mainly focusing on aromatic. We can do it for our aliphatic also, but mainly we are discussing about aromatic here. First one, we are taking toluene. Toluene is treated with CrO2Cl2. CrO2Cl2, what is that? Chromyl chloride, right? We are treating it with chromyl chloride in the presence of a low polarity solvent such as CS2, carbon disulfide medium. We get a complex like this, and this complex on hydrolysis will give us benzaldehyde. This reaction is known as Itard reaction, another named reaction. We studied Rosenmund reduction, then we discussed Stephan reduction, and now we are discussing Itard reaction over here. Let us now talk about the next one, that is use of chromic oxide. So if you have toluene, you can convert it into benzaldehyde either by using chromyl chloride. This one was chromyl chloride, and or you can use this compound, that is CrO3. CrO3 can also be used, or you can use side chain chlorination followed by hydrolysis. What is side chain chlorination? We are treating this with Cl2/HNu. Cl2/HNu is there. Now somebody may be asking that can I substitute the chlorine directly on the benzene ring? No, because we need a Lewis acid over there, right? And hydrous AlCl3 should be there if we have to substitute it on the benzene ring. So here we have Cl2/HNu. So it is going to replace the hydrogen from the methyl group. So it will form CHCl2, 2 times of chlorination we are conducting. So we will be getting this compound, benzyl chloride here. Now this benzyl chloride on hydrolysis will give us benzaldehyde. So this is another method of preparation from toluene. So from toluene you can prepare by 3 means. Either we can use chromyl chloride CrO2Cl2, or we can use chromic oxide CrO3, or we can carry out side chain chlorination and you can carry out the hydrolysis after that. Let us now talk about the Gattermann-Koch reaction. Now what is Gattermann-Koch reaction? In Gattermann-Koch reaction, you're taking benzene, okay? You're taking benzene, you have to treat it with CO, HCl, CO and HCl, carbon monoxide and HCl. Okay, you need an acidic medium here, and we are also using anhydrous AlCl3 and CuCl. Okay, so we are getting benzaldehyde over here. Now look here, this one has 6 carbon, but this one has 7 carbon. So it is an ascend of series, right? This is the first ascend of series that we have studied. Ascend of series. Now earlier we have studied one reaction, this one. This is a descent of series. Why is it a descent of series? Because this one has, here it is 10, 11, 13 carbon was there, but here it has only 11 carbon, right? So it is a descent of series. So now let us move on to the preparation of ketones. So when we talk about the preparation of ketones, the first one is from acyl chloride. So acyl chloride is treated with R2CD. Now what is R2CD? Dialkyl cadmium. Dialkyl cadmium. So if we treat it with dialkyl cadmium, we will be getting a ketone. How? CdCl2 is removed. You have to take two molecules of this one. I will take a reaction. R C double bond OCl. This is acyl chloride. This have to be treated with CdCl2. So I have to take two molecules. So this Cl and this Cl I can remove along with, we have R2CD and we have RCOCl, right? So it is R2CD. So this cadmium is going to take up these two chlorine and moving out as CdCl2, and whatever is left, this chlorine is left, this much part is moving, and this R2 we are going to add over here. One R will come over here and another R will come over here. We will get two molecules of ketone over here. That is the reaction that is happening. Now from nitriles also we can prepare by treating it with Grignard reagent. So again Grignard reagent is coming over here. We have nitrile treated with C6H5 MgBr. What is happening? We have to attach the NMgBr. Okay, NMgBr is coming over here, and C6H5 we have to attach to the carbon, right? So now this is hydrolyzed to give us this compound. Okay, so it's a very easy reaction. We have already studied how to deal with Grignard reagent. Let us now talk about method of preparation of ketone from benzene. Now how to prepare it from benzene or substituted benzene. Whenever we have benzene or substituted benzene, it is treated with acid chloride in the presence of anhydrous aluminum chloride, that is RCOCl plus AlCl3. So that time also we will be getting this compound over here. So this is basically our Friedel-Crafts acylation reaction, right? It is also known as Friedel-Crafts acylation reaction. Let us now talk about the physical properties of aldehydes and ketones. Now here first point is regarding the state. Methanol is a gas at room temperature. I'll just zoom this page. I hope this is clear for you now. Methanol is a gas at room temperature. Ethanol is a volatile liquid. Other aldehydes and ketones are liquid or solid at room temperature. Now, if I take the boiling point of aldehydes and ketones are higher than the hydrocarbons and ethers of comparable molecular masses. What is the reason? Reason is because of the weak molecular association in aldehydes and ketones, that is due to dipole-dipole interactions. Also, the boiling point is lower than alcohols. What is the reason? Reason is because of the absence of intermolecular hydrogen bonding. Okay, so this is some of the important point to note over here. Now, if I take the next paragraph, here you can see that the lower members are miscible in water. This is important. Lower members are miscible, their size is less, so they can break the bond and they can form hydrogen bonds over here, and they are miscible in water. Whereas the higher elements, they are not miscible. Now, the solubility of aldehydes and ketones decreases rapidly on increasing the length of the alkyl chain. All aldehydes and ketones are fairly soluble in organic solvents such as benzene, ether, methanol, chloroform, etc. Lower aldehydes have sharp, pungent odors. They have a very foul smell. As the size of the molecule increases, what happens is that the odor becomes less pungent and more fragrant. Right? We have seen that aldehydes usually it have a sweet smell, but lower elements have a pungent smell. Okay, so that is why it is used in perfumes and flavoring agents like vanilla flavor, right? Vanilla is basically an example for aldehyde. Okay, so that is the important point to note over here. Let us now talk about the next reaction. The first one is reduction reaction. So when we talk about reduction reaction, first one is reduction to alcohols, which we have already discussed. We can use either sodium borohydrate NaBH4, or we can use lithium aluminum hydride, that is LaAlH4, or we can also use LaH. Or we can carry out catalytic hydrogenation, that is hydrogen in the presence of platinum. All these can be used for this conversion. We have already studied this in the previous chapter. This also we have studied. Reduction to hydrocarbons. If we have carbonyl compound and if I treat it with zinc amalgam and HCl, we get CH2. This is Clemmensen reduction. If I have carbonyl compound treated with hydrazine, in the presence of KOH, that is basic medium, I will be getting Wolff-Kishner reduction. And these has some exceptions. Here we can see HCl, so it is acid, right? So if there is any acid sensitive groups which is present in the compound, then it will misguide the reaction. So that is the disadvantage of Clemmensen reduction. And Wolff-Kishner reduction is not undergone by base sensitive groups. So this is important. We have discussed in detail of these two topics and the limitations in the chapter of alkenes. Okay, so let us now talk about oxidation. Now reduction we have studied. Reduction will give us alcohol, and now we are going to discuss about oxidation here. Now how oxidation is carried out? Okay, here you can see if I have an aldehyde, it will undergo oxidation to form RCOOH. Whereas if I have a ketone, I will be getting a mixture of carboxylic acids over there. This is the most important point. Now let us see the different tests. First one is tolerance test. It can be used to distinguish between aldehydes and ketones. Okay, tolerance test means what is happening, we are treating aldehyde. Remember that we are treating aldehyde. Okay, aldehyde is treated with freshly prepared ammoniacal silver nitrate solution. Ammoniacal silver nitrate solution means this AgNH3 twice plus. This is the formula of ammoniacal silver nitrate solution, that is known as tolerance reagent. So when we are treating with that, what is happening, RCHO is converted into RCOO minus, that is the oxidized product. This compound will dissociate to form ammonia, and also you can see a silver mirror here, right? This is silver mirror because of the deposition of silver at the bottom. So this is known as silver mirror test. Tolerance test is also known as silver mirror test. Now the most important point is that this reaction is carried out in alkaline medium. So that is the important point, alkaline medium. Next, Felling's test. What happens in Felling's test? We have two solutions, Felling's A and Felling's B. What is Felling's A? Felling's A is copper sulfate and Felling's B is alkaline sodium potassium tartarate, also known as Rochelle salt. These two solutions are first mixed. Okay, these two solutions are well mixed, and if we are carrying out the reaction and getting a positive result, we are expecting it to have a red precipitate. This is important. We will get a red precipitate over there. What is the reason for that red brown precipitate? It is because Cu2O is settling at the bottom. Cu2O is settling at the bottom as the precipitate, and that is the reason for the reddish color over here. So here we have Cu2 plus and RCHO is again converted to RCOO minus. Now most important thing is aromatic aldehydes. Aromatic aldehydes will not give this test. This is important. Aromatic aldehydes will not give this test. That is also important. Ketones and aromatic aldehydes will not give. Only aliphatic aldehydes will give us Felling's test. So that is a very important point. Next, let us talk about next reaction, that is haloform reaction. Now in haloform reaction, what is happening? We are treating methylated ketone. It's very important. We have to take methylated ketone. Methylated ketone means it is having a general formula RCO. Here we do not need any other group. We need CH3 alone, right? So this group will be moving out as CH3. We are treating it with halogen. If I am treating it with iodine, it is iodoform reaction. So we will be getting CH3 and the remaining compound is going to form a sodium salt. This is the reaction and it will form a yellow precipitate. It will form a yellow precipitate as you can see over here. So this yellow precipitate indicates positive result for a haloform reaction, right? So haloform reaction condition is important. It needs methyl ketones. Methyl ketones. Because we need alpha hydrogen, that is the reason. Let us now talk about the next very important reaction, that is aldol condensation. I will teach it with the help of a simple trick. If I take a molecule CH3 CHO and another molecule of CH3 CHO, Do I have alpha hydrogen in both? Yes. Always remember, aldol condensation happens in those compounds where alpha hydrogen is present. This is very important. Okay, so what am I going to do? This is the carbonyl carbon. From the carbon, adjacent to the carbonyl carbon, I am going to take out one of the hydrogen, one hydrogen, and I am going to attach that on the oxygen. This is not mechanism, this is a trick. Okay, from the carbon adjacent to the carbonyl carbon, we have to take out a hydrogen and we have to substitute on the oxygen, and now you have to write it as a single molecule. What am I getting now? CH3, CHOH, CH2, right? We have removed a hydrogen, so we are left with CH2 and we have a CHO, right? Now what is this compound? This is our alpha carbon, this is our beta carbon. So it is beta hydroxyaldehyde, right? It is beta hydroxyaldehyde. This beta hydroxyaldehyde is known as aldol. This is known as aldol. Okay. Now this compound I can also write it as this. So if I am heating this compound, what is happening? These two molecules are going to move out. Elimination of water is going to happen, and we will be getting CH3, CH, double bond CH, single bond CHO. This is what we are getting in aldol condensation reaction. Now always remember the reagent also. Reagent used is dilute NaOH. Dilute NaOH is used for carrying out aldol condensation reaction. Let us now take another example. CH3, CH2, CHO plus CH3, CH2, CHO. So this is the carbon, this is our alpha carbon. So take out one of the alpha hydrogen and substitute over here. So we will be getting CH3, CH2, CH with an OH. Next we have to write this CH. Onto that CH we have to attach this CH3 and CHO. That is important. Okay, and now we have to remove this hydrogen and OH. We have to join these two with the help of a double bond. So we will be getting this compound over here. You can arrange it and you will get a compound. That means you have to put the CH3 over here. If you arrange it as a straight chain compound, put a CH3 over here, and straight to this carbon you can put a CHO. This is the product that you're getting. So this is the trick for doing this type of problems. Now, what about cross aldol condensation? In cross aldol condensation, I am taking two different aldehydes. Okay, aldehydes or ketones we can take. The same process is going to happen for ketones as well. Now what is going to happen is that first I will be getting the self aldol condensation product of this as my product A. Next I will get a product B, which is a self aldol condensation product of CH3, CH2, CHO. Next is a cross aldol, taking this molecule as the first molecule and this as the second molecule, and that is our C. So C is 1, 2 and D is formed if I consider this as my first molecule and this as my second molecule. So let us take it as 2, 1. We have to do the condensation like that. So we will get 4 products over here. This process is cross aldol condensation. So here is a DIY for you. Try out the cross aldol condensation of CH3 CHO and CH3 CH2 CHO and comment the 4 products below. Use the trick above and comment the products below. Okay, so let us talk about the next reaction, that is Cannizzaro reaction. Now, Cannizzaro reaction is important. This is carried out by those where alpha hydrogen is absent. So here you can see formaldehyde and benzaldehyde. In both these compounds, alpha hydrogen is absent. So in those compounds, we are treating it with concentrated KOH. Earlier we used dilute NaOH or KOH for aldol condensation. Here we do not need alpha hydrogen, and here we are taking concentrated KOH over here. We will be getting an alcohol, so that is important. First product is an alcohol and second product is sodium or potassium salt of carboxylic acid Okay, so that is about this reaction, that is Cannizzaro reaction. Let us now talk about electrophilic substitution reaction. In electrophilic substitution reaction, what is happening? We have an aromatic aldehydes and ketones. This CHO group is meta-directing. Remember that. It is deactivating group. So it is meta-directing group. So it will always give us meta products in all types of electrophilic substitution reaction. That is the important point. Now, it does not undergo Friedel-Crafts reaction. You have to find out the reason. Comment below what is the reason why electrophilic substitution reaction is not given by aldehyde. Sorry, Friedel-Crafts reaction. Friedel-Crafts alkylation and acylation is not given by aldehydes and ketones. What is the reason? You have to comment below. Try it, find it out, and comment below. Let us now talk about carboxylic acids. Now, when we talk about carboxylic acids, again we can say that there is a carbon double bond oxygen and also we have a carbon single bond oxygen. Both are present over here. And what is the bond angle? The bond angle between them is 120 degree. Again, it is the same 120 degree. So that is an easy topic. Let us now move on to the methods of preparation. Methods of preparation. First one is from primary alcohols and aldehydes. So how can we prepare it from primary alcohols and aldehydes? From alcohols, if I have to treat, I need to treat it with a strong oxidizing agent. Strong oxidizing agents includes potassium permanganate, CrO3, that is known as CrO3 in the presence of H2SO4, that is known as John's reagent, or we can use potassium dichromate. These are the strong oxidizing agents. So we will be getting acids over there. Let us now talk about alkyl benzenes. So whatever be the alkyl group that is converted to an acid if I treat it with KMnO4 in the presence of KOH. That is important. Very, very important. Let us now talk about nitriles and amides. How to prepare these two? We have to carry out the hydrolysis first. We will be getting an amide. So amide on hydrolysis will give us acid. So if I have an amide, directly I can treat it with H2O+. We will be getting ethanoic acid over there. It's a very simple reaction. From Grignard reagent, how to prepare? We can treat it with CO2. Okay, treating it with CO2, we will be getting RCOOH. You can try out with a trick. We'll get RCOOH over there. Let us now talk about, and here also we have to remember that this is ascent of series. Ascent of series, this is important. Next is from acyl halides and anhydrides. So there also we have to carry out the hydrolysis, right? Hydrolysis have to be carried out. In the presence of basic medium, we'll be getting the acid over here. Okay. Anhydride also on hydrolysis will give us benzoic acid, and here we have esters that will also give us the same. Next, esters, here you go. Esters also we have to carry out hydrolysis. We will be getting corresponding acid over there, or we can treat it with NaOH. We will get the sodium salt of carboxylic acid, and that on hydrolysis will give us acid. These are very easy process if we have esters, or if we have acyl halides, or if we have anhydrides. We can carry out nitriles, amides. We can carry out the process of hydrolysis. Okay, so let us now talk about physical properties. So when we talk about the physical properties of carboxylic acids, the first one is that they are having comparatively higher boiling point, comparatively higher melting point, and they are soluble in water because of ability to form hydrogen bonds. So that is important. Let us now talk about the various chemical reactions. The first one is formation of anhydride, which you have already studied. If we have two molecules, I'll take it over here, acidity we will do it in the end. If I have two carboxylic acids, like this, I have to treat it with P2O5. What is happening is that I have to remove an water molecule. So whatever is left, I will just join that. I will be getting an anhydride over there. So this reagent is important. Let us now talk about the next reaction. The next reaction is coming out to be esterification reaction. Esterification reaction. Now what is esterification reaction? If we have RCOOH that is treated with an alcohol, we will be getting esters over there. Plus H2O is obtained over there. This is esterification. Now let us talk about the next reaction. The next reaction is going to be reaction with PCl5. So if we have RCOOH treated with PCl5, we will be getting RCOCl plus POCl3 plus HCl. If I treat it with PCl3, I will be getting RCOCl again. And if I treat it with SOCl2 also, I will be getting RCOCl. Acyl chloride is obtained over there. Let us now see the reaction with ammonia. What is happening? We will be getting ammonium acetate first, right? NH3 have to be added, and after that we have to remove H2O we have to remove. We will be getting amide over there. Okay, so if I have benzoic acid also treated with ammonia, we will be getting ammonium benzoate. Remove a water molecule, we get benzamide. And here you can see, if I have dicarboxylic acid, both sides we have to add NH4 plus, remove 2 molecules of water, we get amide. On strong heating, they are going to eliminate a molecule of NH3 like this. NH3 is going to be removed out, and we get a phthalimide here. Phthalimide synthesis. This is not Gabriel phthalimide synthesis, that is different. This is phthalimide synthesis. Let us now talk about reduction reaction. In reduction, we can use RCOOH have to be converted to RCH2OH. So we can use LiAlH4 or we can use B2H6. These are commonly used reagents. Next important reaction is decarboxylation, which you have already studied. What is decarboxylation? We have to remove a molecule of carbon dioxide, right, or carbon. So RCOONA is treated to give RH plus Na2CO3. What is the reagent that is used? The reagent that is used is NaOH in the presence of CaO. The ratio in which these two molecules are taken is important. They have to be taken in the ratio of 3:1. This is known as decarboxylation reaction. Next is halogenation. We have a name for this reaction, Hell-Volhard-Selinsky reaction. In Hell-Volhard-Selinsky reaction, what is happening? We have a carboxylic acid. There is a problem with the PDF. That is why it is jumbled like this. So you can see the reaction over here, halogenation reaction over here. RCH2COOH is treated with X2 in the presence of red phosphorus. So you have to add the halogen like this. This is what you're getting over here. Let us now talk about the electrophilic substitution reaction. Okay, so as you know, COOH is a meta-directing group and it's a deactivating group, right? But it does not undergo Friedel-Crafts reaction. What is the reason? Deactivating group and the catalyst aluminum chloride gets bonded to the carboxyl group. This is the reason why aldehydes, ketones and carboxylic acids do not react with Friedel-Crafts reaction. Remember the question I asked before? It was the same, right? It will react with the carbonyl carbon and it will form salt. That is the reason it will not react with Friedel-Crafts reaction, but it will carry out nitration, halogenation, sulfonation, etc. and we will be getting meta products over here. So this completes our chapter. We have one more topic left, that is our acidity concept. So I'll just go through that as well. Here you can see that first RCOOH on hydrolysis will give us H3O plus plus RCOO minus, right? So we can see that pK is equal to minus log Ka. So we know these concepts, right? Strong acid pK will be less than 1 and Ka will be high. If it is a moderate acid, then pK value will be 1 to 5. Weak acid means pK value is 5 to 15. Extremely weak acid means it is greater than 15. So how can you confirm that a carboxylic acid is acidic in nature? We can react it with a metal, it will release hydrogen gas. If I treat it with a base, we will get water over here. If I treat it with a salt, I will be getting H2O and CO2 over here. So all these will show that carboxylic acids are acidic in nature. But they are more acidic than phenol because phenoxide ion is comparatively lesser stable as compared to carboxylate ion. That is the important point. Next, effect of substituents that we have already studied, which has a dumb dog. Withdrawing group will increases and donating group will decreases. Now here I have an order which I have given over here. I'll just put it in a box. Effect of groups in increasing the acidity order. This is the order. Okay, so if you have CF3, that is going to show the maximum acidity, and if you have phenyl groups, that is the minimum acidity. Now this is the decreasing order. This order is important. You have to read this order. It is given in NCERT. We have to by heart that order. It's very, very important. Now phenyl groups and vinyl groups increases the stability thereby they are going to increase the acidity. This is also important. Phenyl and vinyl groups because of resonance. So these are some of the important points related to acidity. Most important, what is the effect of EWG and EDG? What is EWG and EDG? Electron withdrawing group and electron donating group. So let us now move on to the questions. Before we move to the questions, please keep an OMR or a paper ready. You can either keep an OMR or you can keep a paper ready so that you can attempt these questions in the form of a test. So let's start with the test. There are 20 questions. Certain questions have multiple correct answers as well. So in those questions, if you get all the correct answer, 2 answers will be correct for that questions, for every questions. So if you are attempting a question correctly, you can put a +1, +4, and if you are getting a negative wrong answer, then we have to put a -1. Okay, so you can put it like that, and finally you can get to know your score and comment your score below so that I can understand that you have seen this video till the end and have attended the test. So let us start with the first question. These are some of the questions from the Neetshala app. You can get more such questions. You can practice unlimited number of questions for every chapter from the Neetshala app. So let us see this question. An aldehyde which undergoes Cannizzaro reaction and reduces Schiff's reagent but does not reduce Felling's solution is. You have time, think and give the answer. And it's a very simple question. It does not reduces Felling's solution. It undergoes Cannizzaro reaction. It undergoes Cannizzaro reaction means it will not have an alpha hydrogen. Does not reduce Felling's solution means it will be C6H5CHO. The answer is option number C. Benedict's solution provides. You can answer now. I think this much time was enough for that question because Benedict's solution is very simple. You just have to know what is the ion present, and that is copper. Next question. Acetone reacts with iodine to form iodoform in the presence of. You need 3 seconds to answer this question. 1, 2 and 3. The answer is NaOH. These are direct questions. Now there are some questions for you to think. Question number 1, that you can do it as a question number 4. Okay, in your paper it should be question number 4. Addition of water to alkynes occurs in acidic medium in the presence of Hg2 plus ions as a catalyst. Which of the following products will be formed on addition of water to but1-wine under these conditions? Take a moment, write down the reaction once and you will get the answer. You can pause the video and give a trial. Yes, let us just do this once. It is given that the compound is but1-wine, so it is CH3CH C triple bond, C triple bond CH. This is treated with H2O in the presence of Hg2 plus. So we have to add water here. This side hydrogen, this side OH will come and this side hydrogen will come. Triple bond is broken, double bond is present. This bond will come over here. Right, this will come over here and the hydrogen will go to this carbon. And now what are we getting? We will get a C double bond O CH3. This is what we are getting. So the answer should be option number 2. Next question. Which of these compounds is most reactive towards nucleophilic addition reactions? Now, the reactivity towards nucleophilic addition reactions. You can pause and give a trial. Yes. So the explanation is it is based on 2 factors. One is steric factors and the other is electronic factor. So here we can use steric factor to explain this, because if you are comparing the groups which are present on the left side and the right side of the carbonyl group, whichever is less sterically hindered, that will allow the nucleophile to attack easily. So here you can see this is a very bulky group, though this is a normal group. This is bulky, this is also bulky. This is bulky, this is also bulky. So anyway, these 2 cannot be the answer. These 3 cannot be the answer. So here we have a less bulky group and least bulky group. So the nucleophile can come and attack easily. So this is going to be the answer. Option 1 is the answer. Now let us move on to the next question. Question number 3. Correct order of increasing acidic strength is. You can pause the video and give your answer, and let's see the explanation. Here there is a simple method to do this. You don't have to think too much. Of course, you have to think a little that if we have a deactivating group or a withdrawing group will increases the acidity, right? So in that case, chloroacetic acid should be more acidic than acetic acid. So if you look at the options, you can see only option 3 has such a condition. So the answer should be option number 3. Now let us talk about the next question. Next question is a question from NCERT Exemplar, but that is a beyond NCERT question. Okay, so this question you can take it as a bonus. You can give 4 marks everyone. This reaction is known as Schotten-Bowman reaction, and the reaction is this. We have phenol treated with RCOCl or ARCOCl, that is known as benzoyl chloride, in the presence of pyridine. In the presence of pyridine, we will be getting this compound over here. So this is Schotten-Bowman reaction. So the answer should be option number 2. Phenol and benzoyl chloride in the presence of pyridine. Next question. Yeah, this you can give a trial. Reagent which do not react with both acetone and benzaldehyde. The answer should be option number 3, Fehling solution. Next one, Cannizzaro reaction is not given by. Very easy question. You have to check which compound has alpha hydrogen. That will not give us Cannizzaro reaction. So the answer should be option number 4. Let us now talk about the next question. Another very easy question. Which products is formed when the compound ArCHO is treated with concentrated KOH solution? Remember the main products. We have an alcohol and we have a sodium salt of carboxylic acid. So what should be the answer? We have an alcohol. It cannot be option number 1. It cannot be option number 3. It cannot be option number 4. So the answer should be option number 2. Let us now talk about question number 8. You can pause the video and you can attempt it. We have already discussed this type of question before. In the beginning of the lecture, I have discussed this question. I have discussed what is the type of isomerism that is shown and what is the product that is obtained. You can watch it again if you have a doubt in this section. It is keto-enol tautomerism. So it cannot be option number 1 and it cannot be option number 3. Either it can be 2 or 4. In that, which one is the answer? En and ol should be present at different positions, right? So it should be option number 4. Next question. CH3CHO is treated with CH3, MgBr and H2O. You have to get A. That is treated with H2SO4. Heat will give us B. And then you have to carry out hydroboration, oxidation. You will get C. You have to try out the reagents. What should be A? A should be this should be A. Dehydration should be carried out. So this should be B. And after that, you have to carry out hydroboration oxidation. So to this side, it will be H2 and here it will be, this bond should be broken and we will be getting OH over here, right? So A, we got it as this, and C we are getting as this. So it is positional isomerism, option number 2. Which is the most suitable reagent for the following conversions? What is happening? CH3 should be converted into OH. What should be the reagent that should be used over here? This is an acid, this is a ketone. How to do this conversion? It should be option number 3, iodoform test. Next, which of the compounds will give butanone on oxidation with alkaline K1O4 solution? Pause the video and give the answer. What is the compound that we need? This is the compound that we need, right? Butanone. And we have to take which alcohol is needed. So this should be the alcohol. And what is that? It is butan-2-ol. Next question. In Clemmensen reduction, carbonyl compound is treated with. Very easy question. You just need 1 second for attempting it. Zinc amalgam in the presence of HCl. Next. Which of these compounds does not undergo aldol condensation? Check which of these does not have an alpha hydrogen. It is option number 2. Right, option number 2 is correct. What about option number 4? Option number 4 is also correct. So it is a multiple correct answer question. It is a multiple correct answer question. Option 2 and 4 is correct. Next, this is also a multiple correct answer question. You have to treat the given molecule with NaOH. So what is happening? You will get sodium phenoxide. So this side will go with H and this side will go with ONA, and we will be getting sodium benzoate also. So 2 and 3 should be the answer. Question number 15. Which of the following conversions can be carried out by Clemmensen reduction? Pause the video and give a trial. Clemmensen reduction means you will have an aldehyde or ketone that is converted to a corresponding alkane, right? So first one is wrong. This one is also wrong. This can be correct, and this one also can be correct. So 2 and 4 should be the answer. Next, through which of the following reactions the number of carbon atoms can be increased in the chain? Increase in the chain means it is ascent of series. It is ascent of series, and I have taught you ascent of series in 2 places. What is that? Grignard reaction can be one of those, right? Grignard reaction can be one of those, and in aldol condensation also we have studied it is ascent of series. Next, benzophenone can be obtained by benzophenone. Benzophenone can be obtained by benzoyl chloride and diphenyl cadmium. That is possible. Even benzoyl chloride and benzene plus AlCl3, Friedel-Crafts acylation, that can also be used for this process. So with this we are concluding our chapter aldehydes, ketones and carboxylic acid. So in the next video lecture we will be discussing the chapter of amines. So see you again in the next lecture. Till then, goodbye and happy learning. Welcome to Neetshala Organic Chemistry Revision Lecture Series. In this lecture, we will be discussing the chapter of amines. So let's get started with the chapter. What are amines? Amines are basically considered as the derivatives of ammonia. These are the derivatives of ammonia, and these are obtained if we remove 1 or 2 or 3 hydrogen atoms of ammonia with alkyl groups. That means I can either remove this hydrogen, or I can remove this hydrogen, or this, or all the 3. I will be getting an amine if I substitute a CH3 group at all these positions. So that is known as amines. So let us now talk about the next one, structure of amine. So it is almost similar to the structure of ammonia, where the nitrogen atom is trivalent and it carries unshared pair of electrons. Nitrogen orbitals in amines are therefore sp3 hybridized. That is important. It is sp3 hybridized, and the geometry of amines is going to be pyramidal. This is important. The shape is pyramidal, and each of the 3 sp3 hybrid orbitals of nitrogen overlap with the orbitals of hydrogen or carbon depending upon the composition of the amines. The 4th orbital of the nitrogen of all amines, they contains an unshared pair of electrons that we already know from the structure of ammonia. It's almost similar to the structure of ammonia, but there is slight difference, like the bond angle is slightly different. In the case of trimethylamine, we are having a bond angle of 108 degree, and in the case of other we are having less than 109.5 degree, because of the unshared pair of electrons. It is slightly deviated from the tetrahedral angle. Let us now talk about the classification of amines. We have already studied this in previous chapters also. We have ammonia, and if I remove one of the hydrogen and substitute an R group over there, we are getting a primary amine. And if I am removing two hydrogen and substituting two alkyl groups, then I am getting a secondary amine. And if I am removing all the hydrogen of ammonia and substituting it with alkyl groups, then I will be getting a tertiary amine over there. Let us now move on to the next slide. Preparation of amines. So let's start with the first method of preparation of amine. The first one is by the reduction of nitro compounds. So how can we prepare amines by the reduction of nitro compounds? It's very easy. If we have nitro compounds, we can use finely divided nickel, palladium and platinum, and we can pass hydrogen gas. Hydrogen in the presence of platinum, palladium, nickel. That is the first method. Second method is by the reduction with metals in acidic medium. Okay, so here we can see Sn plus HCl or Fe plus HCl, that can also give us NH2. So NO2 group is converted to NH2 group. The process is called as hydrogenation, or we can say it is reduction of nitro compounds. Let us now see the second method. The second method is known as ammonolysis. Now what is ammonolysis? It is the process of cleavage of CX bond by ammonia molecule. If we have CH3X, we are going to break this bond by using ammonia. That is known as ammonolysis, and here NH3 is going to act as a nucleophile. That is the important point over here. The primary amine that is obtained behaves as a nucleophile in the second case. So now this RNH2 can react with another molecule of Rx. So I'll just remove this. Okay. So here you can see that the RNH2 is going to react with Rx. So here RNH2 can now act as a nucleophile. So that can react with the Rx to form R2NH. This R2NH can now act as a nucleophile, and that can react with an Rx to form R3N. Now this R3N can also act as a nucleophile, and it will react with Rx to form R4NX. That is known as quaternary ammonium salt. So this is known as quaternary ammonium salt. This formula is important. And how to get free amine from that? How to get amine from quaternary ammonium salt? The method is very simple. We can treat it with NaOH. If you are treating the quaternary ammonium salt with NaOH, we will be getting RNH2 plus H2O plus NaX. It's very simple, right? Let us move on to the next slide. This is the disadvantages of ammonolysis. So I'll give the heading disadvantages. Now when we talk about the disadvantages of ammonolysis, it has a disadvantage of yielding a mixture of primary, secondary and tertiary amines and also quaternary ammonium salts. Okay, but the merit is that we are getting primary amine as the major product if we take large excess of ammonia. And what is the reactivity order? The reactivity order is coming out to be Ri greater than Rbr greater than Rcl. This is the reactivity order. Let us now talk about the next method, that is the reduction of nitriles. So whenever we have nitriles, we have to use hydrogen in the presence of nickel, or we can use sodium amalgam in the presence of ethanol. Both of these can convert the Cn group into CH2NH2 group. So here we can see if we have CH3Cn, it is converted to CH3CH2NH2, right? So here we have 2 carbon and here also we have 2 carbon, right? But see here, the reaction is used for ascent of amine series. This particular reaction is used for ascent of amine series. That means if we have 2 carbon over here, we have to get 3 carbon over here, right? Because the R group will have only 2 carbon, right? Here the R group will have only 2 carbon and another carbon is from the cyanide group. Now that is also going to go with the R group. So in the case of the R group, one more carbon is getting added, and that is why it is said that it is an ascent of series. So what are the reagents that is used? H2 in the presence of nickel, or we can use sodium amalgam in the presence of ethanol to convert nitrile to amines. Let us now talk about reduction of amides. So for reduction of amides, we can convert it by using lithium aluminum hydride and water. This simple reaction. So this is corresponding. right? Because here if we have 5 carbon, here also we will get 5 carbon. The same number of carbons will be there. But we have another method that is known as Hofmann bromamide degradation. There, this CO group will be removed. So that is a descent of series. Let us learn about that now. Before that, we have Gabriel thalamide synthesis. Now, what is happening in Gabriel thalamide synthesis? This is used for the preparation of primary amines. This is an important point. It can be used only for the preparation of primary amines. Thalamide on treatment with ethanolic potassium hydroxide. What is that? KOH. It is basically KOH. So this is our thalamide molecule. Yesterday we studied how to prepare thalamide and we have to treat it with KOH. At that time, what is happening? This H from here is going to be as water and this K will get substituted over here. So this is what we are getting over here. Now what we should do, to this compound we have to add Rx, right? Because this one is now going to act as a nucleophile. So this reaction will lead in the formation of N-alkyl thalamide. That means the K should be substituted with R. Now this is treated with NaOH. When this salt is treated with NaOH, what is happening? Both these compounds are broken and that is going to form an RNH2 and we get this byproduct over here. So this is used for the preparation of primary amine. So first step we will use KOH, second step we will use it RX, and the last step we will use NaOH. So this is how you have to remember this reaction. Most important point is this: aromatic primary amines cannot be prepared by this method. What is the reason? Because aryl amines do not undergo nucleophilic substitution with the anion that is formed by the thalamide. That is this portion. This reaction will not occur. Okay, this part will not react. That is the reason why it is not used for the preparation of primary aromatic amines. Let us now move on to the next reaction. Yes. So the next reaction is Hofmann bromamide degradation reaction. So when we talk about HBD reaction, we can abbreviate it as HBD reaction. So what is happening in HBD reaction? Hofmann developed a method for preparation of primary amines on treating an amide with bromine in aqueous or ethanolic solution of sodium hydroxide. Here you can see Br2 plus NaOH is the main reagent for bromamide degradation reaction. So here what we should do, we are removing the CO group and whatever is left we will just join to get the amine. So we can say this is one carbon less than that present in the amide. So it is a descent of series. It is a descent of series. So let us move on to the next slide. That is the physical properties of amines. The first one is the color and state. Lower aliphatic amines are gases with fishy odor. Primary amines with 3 or more carbon atoms are liquid and still higher ones are solid. Aniline and other aryl amines are usually colorless but get colored on storage due to atmospheric oxidation. So that means if we are keeping it in air, what happens is that they get colored, usually a brown color, brown or reddish color it is obtained over there. Let us now talk about solubility. Now, lower aliphatic amines are soluble in water. What is the reason? It's because they can form hydrogen bonds. However, solubility will decrease with increase in molar mass of the amines. What is the reason for that? Because as we increase the number of carbon atoms, what happens is that the size of the hydrophobic alkyl part का size increase हो जाता है and as a result of which the solubility is going to decrease, because solubility as we know is inversely proportional to hydrophobicity, right? Hydrophobicity, inversely proportional to hydrophobicity. Higher amines are essentially insoluble in water due to the same reason. Amines are soluble in organic solvents such as alcohol, ether and benzene. So the most important point over here is this. Let us now talk about the boiling point. Now when we talk about boiling point, primary and secondary anilines are encased in intermolecular association due to hydrogen bonding between the nitrogen of one and hydrogen of the other. That means there is intermolecular hydrogen bonding. That is the important point. Due to the presence of this intermolecular hydrogen bonding, there can be very high boiling point. And the order of boiling point of isomeric amines is following this order: primary greater than, secondary greater than, tertiary. This order is very, very important. Tertiary does not have intermolecular association due to absence of hydrogen, and as a result of which they are having minimum boiling point. Let us now talk about some of the important distinction tests. First one is the carbyl amine reaction. Now when we talk about carbyl amine reaction, we have to study the reaction first. RNH2 plus CaCl3 in the presence of KOH will give us RNC, that is isocyanide. We are getting isocyanide over here along with KCl and H2O. So that will give us a foul smell. So this smell will help us identify whether the reaction has happened or not. Is that here we can see, yes, so here you can see one important point, that is secondary and tertiary amines do not show this reaction. This reaction is known as carbylamine reaction or isocyanide test and is used as a test for primary amines only. So aliphatic and aromatic primary amines, they will give the positive result for this reaction. So near to every test we have to write which compound is undergoing this reaction. So when we talk about carbylamine reaction, we have to write that it is only for primary aromatic and aliphatic amine. They will undergo this particular reaction. Now, when we talk about next test, that is known as Lieberman's nitroso test, reaction with nitrous acid. Here also we can see that the primary aliphatic amines is undergoing the reaction. It is same as diazotization. We get ROH in the final step. Here we get N2Cl and that on treatment with water will give us ROH. Here we have aniline, that also will give the same result as we expect from diazotization. So this is also given by only primary aliphatic and aromatic amines. Secondary and tertiary reacts with nitrous acid in a different way. So that will give different products. So we can easily identify the products over there. Now, if we have to know how can we distinguish between a secondary and a tertiary, we have to carry out this test, aryl sulfonyl chloride test. So here what we have to do, this reagent is known as Hinsberg's reagent. So this test is known as Hinsberg test. So what we should do is we have to treat the primary or secondary amine with this compound, and then we will be getting this compound over here that is soluble. So primary and secondary is soluble in this particular compound, whereas tertiary is not soluble in benzene sulfonyl chloride. So this is used for distinguishing between primary, secondary and tertiary. Only primary and secondary will react with aryl sulfonyl chloride and tertiary will not react with aryl sulfonyl chloride. So that is the important point. So you have to understand that the first test that we studied was carbylamine test. So in carbylamine it was given by primary only, nitroso test, primary only, aliphatic and aromatic. And the last one was Hinsberg's test. Hinsberg's test was given by primary and secondary. So tertiary will not undergo any of these reactions, so we can distinguish them very easily. So if we have a secondary, first carry out carbylamine test. If it is giving a negative result in the carbylamine and a positive result in the Hinsberg test, then we can conclude that it is a secondary amine. Let us now talk about the next one, that is about the tertiary amines. Tertiary amines do not react with benzene sulfonyl chloride. This is a very important point. And also aromatic will not react with benzene sulfonyl chloride. Next is about the basicity. This is very important, the basicity orders. In gaseous phase the order is tertiary greater than, secondary greater than, primary greater than NH3. This is the order. We have to by heart this order. But in the case of aqueous solution, this is in the case of aqueous solution. So in the case of aqueous solution we have to study the order as secondary, then tertiary, then primary, and then ammonia. So in the case of ethyl substituted amines, it is STP, that is the decreasing order, and here it is SPT. The primary and tertiary will be just the ulta. So that will be the order for secondary secondary amines. Next, let us talk about the effect of substituted anilines. So here we can use the same trick that we studied before, which has a dumb dog. So there we have studied that withdrawing group will increases the acidity. So we can say withdrawing group will decreases basicity, just the opposite, right? So if we have electron withdrawing groups, they are going to decrease the basicity, and donating groups or releasing groups, they are going to increase the basic strength. So this is important. Let us now talk about the next one, that is the electrophilic substitution reaction. The first one is bromination. So here what is happening, aniline reacts with bromine water at room temperature to form 2,4,6 tribromoaniline. That means ortho and para positions are substituted at the same time. So at that time, what is happening, we get a product like this. But if we have to get only one product at a time, then what we should do, first step is we have to treat it with CH3CO twice O, that is known as acetic anhydride, and whatever product that we are getting over there, treat it with Br2 in CH3COOH. We will be getting this as the major product, and that on hydrolysis will give us 4-bromoaniline. So this reaction you have to by heart. Sometimes they can ask, how can we get this single product? Let us now talk about nitration. Now what happens in nitration? In nitration also we get a mixture of products. We get para, ortho and meta also, right? But here ortho is minimum, just 2%. Meta is 47 and para is 51, right? So if we need to get para only, here also we have to first treat it with CH3CO twice O, and then we have to carry out the nitration again, and then we have to carry out the hydrolysis. We will be getting para-nitroaniline alone. Let us now talk about sulfonation. So when we talk about sulfonation, also we are getting something different. First we will be getting NH3HSO4. That on strong heating we will get sulfonilic acid, and this can exist in a Zwitter ion form, which you have studied in bio as well. So the H will move over here, the H plus will move over here, so this side will get a positive sign and this side will get a negative sign. But overall the molecule is neutral. So that is not a Zwitter ionic form. Let us now talk about Friedel-Crafts acylation and alkylation reaction. Aniline does not undergo Friedel-Crafts alkylation and acylation reaction. What is the reason for this? Because the salt formation with aluminum chloride. Okay, so the NH2 group that will reacts with the AlCl3 group and it will form a salt. So it will not carry out further reaction, and it is acting as a very strong deactivating group for the further reaction. The nitrogen of the aniline is going to be a very good deactivating group, and as a result of which it does not carry out Friedel-Crafts reaction. Let us now talk about diazonium salts. This is a very easy topic, in fact the easiest topic of organic chemistry. It has a general formula of RN2X. This is the structure. It will have an N2 plus group. This is known as diazo group. N2 plus group is known as diazo group. If we have C6H5N2Cl, then it is known as benzene diazonium chloride. If we have HSO4 minus, then it is known as benzene diazonium hydrogen sulfate, and so on. Let us now talk about the preparation. Preparation is very simple. It is prepared by a technique that is known as diazotization. Now what is diazotization? In diazotization we are taking aniline, treated with NaNO2 and HCl at a temperature of 273 to 278 Kelvin, and we are getting the benzene diazonium chloride and NaCl and water over there. So this is how we are preparing the benzene diazonium chloride, and the process is known as diazotization. Let us now talk about the physical properties. Very simple. It is a colorless crystalline solid. It is readily soluble in water and is stable in colder conditions, but with warm water it is reactive. It decomposes easily in the dry state. Benzene diazonium fluoroborate. This is important. That is, we have this compound N2BF4. This compound is water insoluble and it is stable at room temperature. So that is an important point, exceptional point. So this is an exceptional point. This compound is stable at room temperature and it is insoluble in water. Other all are soluble in water. Let us now talk about the chemical reactions. Very easy. First one is we have to substitute it with the chlorine. So if we have to carry out, that means if we have to substitute this R ArN2X to form ArCl, then we have to carry out Sandmeyer's reaction. Now Sandmeyer's reaction, what we have to take, in the case of Sandmeyer's reaction, either we can take CuCl2 in the presence of HCl, then we'll be getting Cl substituted in the benzene ring, we'll get this compound. If I am taking CuBr in the presence of HBr, then Br will get substituted over here. And if you take CuCN in the presence of KCN, then Cn will get substituted over here. So it's a very simple reaction that is known as Sandmeyer's reaction. Now another one is Gattermann reaction. In Gattermann we can substitute either chlorine or bromine but not cyano group. So here what we have to do, we have to take copper in the presence of HCl. Here we took CuCl in the presence of HCl, but here we have to take Cu in the presence of HCl, or Cu in the presence of HBr, we will get Cl or Br substituted over here. Let us now talk about replacement by iodide ion. We can take ArN2Cl treated with Ki, we will be getting ARI over there. That means we get iodobenzene. So this is another simple reaction. So the importance of diazonium compounds is that they can be used for the preparation of many other compounds in laboratory. So it's very useful. Next one is preparation of fluorobenzene. Here you can see first we have to treat it with HBF4. We are getting ArN2BF3, sorry, and ArN2BF4, and that on heating will release us BF3 and N2. And whatever is left we have to join to get ARF. So this is another simple reaction. Next is replacement by hydrogen. We can treat it with H3PO2, we get benzene over here, or we can treat it with alcohol, ethanol, there also will be getting benzene. Next is the replacement by hydroxyl group. There we have to treat it with water, we will be getting AROH, that is phenol. And the last one is replacement by NO2 group. There we have to treat it with HBF4. Then we will be getting this compound. This I have already told you, it is insoluble. And then we have to treat it with NaNO2 in the presence of copper. So we will be getting NO2 over here. Now let us talk about coupling reactions. Coupling reactions is very simple. We have to remove one H from here and Cl from here. Write down the molecules together. Remove an H from here, Cl from here. Here also we have to remove an HCl. And whatever is left, we have to join. So if we are treating it with phenol, then we will be getting an orange dye because of para-hydroxyasobenzene. And if we are treating it with aniline, we will be getting para-aminoasobenzene, which is responsible for a yellow dye. So this is about coupling reactions. So with this, we are concluding this chapter. And now let us do the questions related to this chapter. So let's do this question. Which of the following is a tertiary amine? So it is triethyl amine. Sorry, primary amine is asked over here. So it should be triethyl amine, because what is the structure of triethyl amine? We have CH2CH3, CH2CH3 and another CH2CH3. This is the structure of trimethylamine. So answer should be option number 2. Next question. Amongst the following, the strongest base in the aqueous medium is? What should be the answer? It is aqueous medium, right? It is aqueous medium, and it is also saying that it is, all these are methyl substituted. 3 are methyl substituted, but one is, yeah, all are methyl substituted and one is aryl substituted. So if we take this third one, that should be the answer. This is the most basic, because we have studied that S is the most basic, right? STP will come in the case of ethyl substituted and SPT will come in the case of methyl substituted. So anyway, secondary will be the most basic. So it should be option number 2. What is the correct IUPAC name? So you can try this now. It should be N-methyl prop 2 in 1 amine. Option number 4 is the answer. Let us now move on to the next question. Which of the following is a weak Bronsted base? So here we have to understand that aniline is the weakest Bronsted base among the given compounds because of resonance. Resonance is present. So since resonance is present, the lone pair is less available for the donation to the acid, and as a result of which it is going to be the weakest Bronsted base. Let us now talk about the next question. Benzyl amine may be alkylated as shown in the following equation. What is the mechanism that is followed? Which of the following alkyl halide is best suited for this reaction through SN1 mechanism? So, SN1 mechanism, as you could remember, is through the formation of carbocation. It is following carbocation mechanism. So, we have to find which one can form the best carbocation, the most stable carbocation, and that can be formed by third one. So, that should be the answer. Next question. Which of the following reagents would not be a good choice for reducing an aryl nitro compound into an amine? So what could be the answer for this? First one we can use, it's a good reagent. But second one is not a good reagent. It cannot be used for the conversion into ether. No reaction will occur in the presence of LiLH4 in ether. So the answer should be option number 2. Let us move on to the next question. In order to prepare primary amine from alkyl halide with simultaneous addition of one CH2 group in carbon chain, the reagent used as a source of nitrogen is. So the answer is potassium cyanide, KCN, because we have a compound like this. So this have to be first treated with KCN. So we will be getting CN, and now we can treat it with sodium in ethanol. We will be getting a primary amine over here. NH2 over here. Next one. Source of nitrogen in Gabriel thalamide synthesis. What will be the source of nitrogen? Source of nitrogen will be potassium thalamide. Option number 4. Let us now talk about the next question. Amongst the given set of reactants, the most appropriate for preparing secondary amines is. What could be the answer for this question? It should be third one. Third one is the better method for preparation of amines. We are taking a primary RNH2 plus RCHO. So that time we will get an imine, and then we have to treat it with hydrogen in the presence of platinum. We will be getting a secondary amine. So that is the best method of preparation of amines. We have to prepare secondary amine. So that is the best method. Let us now talk about the next question. The best reagent for converting 2-phenyl propanamide into 2-phenyl propanamine. Propanamide should be converted into propanamine. So that can be converted. It's a corresponding series. It's not ascent or descent. So it should be lithium aluminum hydride in ether. Best reagent for converting 2-phenyl propanamide into 1-phenyl ethanamine. So that should be a descent of series. For descent of series, we can use Hofmann-bromamide degradation reaction. So the answer should be option number 2. Hofmann-bromamide degradation reaction is shown by amides only. So it should be option number 2. Next question. The correct increasing order of basic strength for the following compounds is. Most basic is going to be when there is a CH3 group, right? Releasing group will, or we can say donating group will increases the basicity. So 3 will have the maximum. So only one option is coming, that is option number 4. Next, methylamine reacts with HNO2 to form. So what is it going to form? It is going to form an alcohol, right? We have studied that in Lieberman's nitroso test, a primary amine is going to form an alcohol, and the secondary amine is going to form a diazonium salt. So here the answer should be option number 3. Next one. The gas evolved when methylamine reacts with nitrous acid is. Methylamine is reacted with nitrous acid, so we will be getting nitrogen gas in the process. Option number 2. In nitration of benzene using a mixture of concentrated H2SO4 and concentrated HNO3, the species which initiates the reaction. What is the reaction that is happening? The reaction that is happening is electrophilic substitution reaction. So electrophile should be generated, and the electrophile is NO2 with a positive sign. nitronium ion. So answer should be option number 3. Let's see this question now. Reduction of aromatic nitro compounds using iron and HCl is. So what could be the answer for this question? Reduction of aromatic nitro compounds will give us aromatic primary amine, right? So it should be option number 3. Most reactive amine towards dilute hydrochloric acid. Towards dilute hydrochloric acid, it should be a tertiary amine. So that is important. It is following the order tertiary greater than, secondary greater than, primary. So greater the base strength of the base, greater will be its reactivity towards dilute HCl. Next, acid anhydrides on reaction with primary amines. What will it give? It will give us amide. Next reaction. Next question is the reaction ArN2Cl in the presence of Cu and HCl will give us ArCl plus N2 plus CuCl. This reaction is known as Gattermann reaction. Best method for preparing primary amines from alkyl halides without changing the number of carbon atoms in the chain. What should be the answer? Without changing the number of carbon atom, we have to prepare primary amines. So we can use Gabriel phthalimide synthesis. Hoffman will give descent of series, and this is not used for the process of preparation of amines. Which of the following compounds will not undergo azo coupling reaction with benzene diazonium chloride? So here, if you look at the first one, it will. Second one also will undergo. Third one also will undergo, but nitrobenzene will not undergo the coupling reaction. That is an important point. Nitrobenzene will not undergo because diazonium cation is a weak electrophile. It's a weak electrophile. Diazonium ion electrophile is weak in diazonium ion. So electron rich compounds can react, but electron withdrawing group will not undergo coupling reactions with this weak electrophile. So that is an important point. Now the last question, which of the following compounds is the weakest Bronsted base? The weakest Bronsted base in the following is, it should be option number C. Phenol is the weakest Bronsted base because after losing H plus, it will produce the least stable conjugate acid among all these. So that should be the weakest Bronsted base. So the answer should be option number 3. With this, we are concluding this chapter and also we are concluding this series. Hope you like this series. Please do share, like and comment below your queries and your suggestions so that we can come up with new series like this in future as well. So thank you and have a great day ahead, and stay home, stay safe. Happy learning.